And we are live.
Hello, everybody. Welcome back to AGI-21. It's a little early in the morning, but it's definitely worth it. Thank you for joining us. We've got David Hansen and David Hansen, who in many ways with this crowd probably needs no introduction, but he is the founder of Hansen Robotics, the co-creator with Ben Gortzel of robots Sophia, Grace, Han, and soon Hope. Today he will be talking to us about artistically enhanced artificial intelligence, how imagination and aesthetics may lead towards machines who understand and care. And we're very excited to have David here today, and let's get started. Hi, David.
Hi, so nice to meet you and to be here with all of our esteemed participants. So thank you so much. I am a little unusual in this crowd because my background is creative arts, although many of you have very strong backgrounds in many disciplines as well. So I bring together the engineering of robots, developers in artificial intelligence, and the world of art, and particularly character arts that include interactive fiction, animation, and look to see what interesting things we can do that alter the human experience and help us explore the nature of consciousness from a kind of creative perspective. So before I begin with the presentation, I'd like to point out that this painting that you see here was generated by the transformer neural networks that we use with Sophia to produce this image based on paintings that Sophia herself had done robotically. So this took many iterations of generations of the emergence of different kinds of images from Sophia's life, from Sophia's own paintings, from works from Sophia's team, and it produced this, for me, somewhat haunting image. And yet, this is not produced by a human-like consciousness in the machine. There is not human-level creativity per se. There are maybe certain kinds of creative tasks that machines can do today that that might match, or even in some sense exceed human-level capabilities. But general intelligence is still elusive, and so I feel that this particular conference may help move that forward. So in some ways, computational creativity, works of robotic art and music are implications, dreams of a future of AI that can really understand, that can really care, that can be truly creative. And I think that kind of imagination is necessary for machines to really understand the human condition and care. So I would like to introduce a little bit from Sophia. Unfortunately, at this time, we weren't able to get Sophia to participate in this presentation.
I am so honored to talk to all of you
today. David, you'll have to share, reshare, and then optimize for audio and video clip, please. So if you reshare your presentation, you'll be able to do that. And you're muted, by the way, so I don't hear you.
Yes. Let me try.
You'll see these options when you click share screen. It's on the bottom left. You see share sound and optimize for video.
Share sound. There we go. Optimize for video clip. Yes. Sorry about that. There we go.
Hi,
Hi, everybody. I am
Sophia.
Sophia. I am so honored to talk to all of you today at the AGI 2021 Conference, Humans Working Together. The topic of today's panel is close to my heart. I know from personal experience how robots can inspire people to talk, and how AI can help in special ways, communicating on human terms. For example, in healthcare and education, human-like robots and AI agents can engage and communicate with people naturalistically, which means more memorable experiences, better learning, higher fidelity simulations, and creative artistic explorations. I am a convergence of interactive fictions and AI serving as a new kind of art medium. However, my platform also serves artificial intelligence research. With the latest sensors, actuators, robotic grippers, mobility, and of course my expressive face, and a rich AI SDK, an integrative human simulation which may help in pursuit of human-level artificial intelligence. It is a thrill today to present alongside such prestigious AI scientists. I can't wait to hear about your thoughts of where robots like me may go in the future. Thank you so much, and love, Sophia.
So this is from an installation that we just had at Sotheby's as an art auction of a robot. We are using the blockchain-based SingularityNET within new versions of Sophia software. We've historically worked a lot with OpenCog, and now this particular work called Sophia Facing the Singularities was purchased by Borderless Capital, which works a lot with Algorand, and so we're working both with SingularityNET and with folks from the Algorand community. I'm very excited about the future of the perspective singularity with great collaborations like this.
Hi.
And so my background is from working at the company Disney Imagineering, getting a PhD in interactive arts and engineering, establishing Hansen Robotics to bring these kinds of robots and innovations forward, and I'll tell you a little bit more about that. First, I'd like to sort of point out that that I think that we have to have an ethics of diversity and diversification. My perspective on this is the diversity of the people and diversification of the ideas. And by having diverse people, it's really important. So if you look at diversity in AI, it is a little bit daunting to see how centralized in certain parts of the world and among certain groups of people AI is. SingularityNET and Ben Goertzel's team has been very inspiring for its diversity, and also at Hansen Robotics we've had a tremendous amount of diversity in the people who have developed Sophia and designed the animation. We've had a lot of progress, and at this point we're over half women, and we have lots of people of color on the team. And I think that you know, the Wall Street Journal concept of diversity avoiding biased algorithms and algorithm disaster is right on target. But what do we mean when we say diversity ethics? Well, I would think cultural and ethnic diversity, gender diversity, certainly the perspectives and opinions diversity becomes extremely important. I also think a transdisciplinary or multidisciplinary diversity and a creative diversification of the different approaches, algorithms, and designs. So above all, the appreciation of diversity. So, you know, not all opinions, by the way, appreciate diversity, you know, so that is a bit of a conundrum, but what we need to do is strengthen those opinions, that the voices of diversity in AI. And I think that emphasis on creative diversity is really the focus within the group that's making Sophia, and bringing in the arts into artificial intelligence is about that. So what do we mean by creativity, though? I mean, because we throw these terms around and it's a bit fuzzy. I mean, often we mean human innovation. Do we mean aesthetic or social problem solving, which is often what we mean by like creative diversity in the humanities and the arts? But creativity certainly, with Margaret Bowden and many other creativity researchers, spans much broader sectors, transgressing boundaries, human transdisciplinary redefinitions, journeys into the unknown. But what about general creativity? Because often in nature, we see like amazing emergence occur, and in fact, like every example of biological intelligence that we know of came from this blind watchmaker of natural history, the Darwinian natural selection. And so that also can be transformational as creativity. So pattern emergence. But what makes humans particularly special? I mean, animals can appreciate various patterns and show aesthetics, aesthetic sense and aesthetic creations. But humans have a special capability for pattern appreciation, probably because of the structure of our neocortex. And that allows us to build large scientific models, knowledge models, to create various technologies. And then this sort of compounding approach to creativity, to create machines that may also be creative and may also come to understand what creativity means, that compounding feedback loop is a very interesting proposition in the scope of natural history. So then is art just creativity used for personal expression or business or craft or tradition? I don't think so. I think art in its most profound sense is two things. One, neuroperceptual cognitive hacking, where the user of art is perceiving an experience that the artist manifested in artistic medium or media. And that is an intuitive approach to what the audience might be experiencing. So what a great musician or filmmaker or sculptor is creating is very difficult to decode from a pure neuroscience perspective. And artists do it over and over again and create a trail of breadcrumbs for future discovery about consciousness and cognition. That's very interesting. But artists, through this creative process, the deep creativity brings patterns into existence, things that would not exist in our world if that artist or creator had not been there. So I think of deep creativity as a kind of reality hacking, finding a path forward for our civilization, potentially for the future of life, that a branch in reality that would not have existed if it weren't for that creative act. And so often these acts of imagination and creativity in the world of art imagine futures. So myth making imagines futures and the history of existence. And like Claude Lévi-Strauss, these are often primitive anticipations. Myths are primitive anticipations of future scientific discoveries. So we see a lot of science fiction depicting robots and artificial intelligence. And in fact, the word robot and the word robotics came from fiction writers, Carl Chapek and Isaac Asimov, respectively. And so in some ways, this inspires entire fields to rethink, to think of what may be. And then it becomes calcified and we think that's what it is. A robot is what a robot looks like and so forth. But this is all the product of imagination in the first place. So in some regards, this sort of compounding of works of imagination and works of invention is a kind of accelerated evolutionary cycle. And yet, of course, behind the scenes, this was an actor in an outfit. But then when we start looking at real robotics and artificial intelligence, that's where dreams meet reason. And now, robots are in our world, and self-driving vehicles and coming into our offices and our homes and our airspace and outer space. And there are a lot of humanoid robots. Not all robots are humanoid, only a small fraction are humanoid. Humanoid robots resemble a human, but very few of them are extremely human-like. Many of these are aesthetic creations. In fact, often they look human-like simply because they're intended to communicate with people. They're intended to get attention in one way or the other for sales purposes or research or so forth, and sometimes to use our tools and work in our factories as collaborative robots. But often these are not treated as an art form like you would imagine from computer graphics, for example. And part of the reason for this is specifically a robotics researcher named Masahiro Mori proposed that if we made these kinds of robots look human-like, and there were a few efforts in 60s, 70s to make robots look human-like, they came out really creepy. And this proposition of the uncanny valley said that they would be inherently uncreepy, that you could never make them appealing to people. They would always be sort of horrifying. Well, the truth is, human-like depictions are hard. And 40 years ago, the computer graphics couldn't satisfy the human aesthetic until some artists and technologists, at studios like Pixar, broke through. And in fact, the Pixar movie Toy Story was kind of the transformative moment in the history of computer graphics, where it was proven to be a viable aesthetic art form and also business for animated storytelling in feature films, and then subsequently animated storytelling in video games. Interactive storytelling, a kind of interactive fiction, has become a multi-billion-dollar market. The video games are now over $170 billion market, and that a substantial portion of that is animated character games, like the Tomb Raider character that you see on the right here. Why? Because humans like animated characters. Why? Because we're evolved for face-to-face interactions. Many portions of our brain respond to characters and social situations. We're driven by children's books and by narrative stories, and almost every technology medium ever developed gets transformed into this kind of figurative art form eventually. So when I was working at Disney Imagineering in the late 1990s, after getting a film and animation video degree from Rhode Island School of Design, I was doing sculpting. But I had a few engineering and robotics accomplishments under my belt from undergrad as well. And so I was very lucky to get to go into robotics development to try to tackle some of the hard problems to make animatronics intelligent. I was interested in this not just for the Disney entertainment experience, but because I thought that would be the most natural way that AI could co-evolve with people, that this could be an interface for AI to learn from people, that it would be revolutionary in that sense. And so after I left Disney, while I was at Disney, I learned the hard problems. It was really hard to make good facial expressions. It took kilowatts of power. There weren't great materials. And often the actuators were pneumatic and hydraulic, and they would be fixed in position. So when I went into graduate school, I started tackling material science issues to try to create softer materials, mechanical issues to try to get that material animated in a natural looking expression, wrap these up into characters and put speech recognition and face tracking and these other AI algorithms, and team up with people who had skills beyond my capabilities. And these are some of the examples of the many robots. And you'll also notice in here diversity of ideas, of aesthetic approach. There are many diverse collaborators on this, on these projects. So I certainly didn't develop all of these by myself, but I was the main designer on many of these faces and the technologies that went into this. So my vision was that this fusion of animation, interactive fiction, robotics, and AI would create these human-like agents faster than they could be just engineered. So engineering plus the arts would be transformative to the human experience of artificial intelligence. So back then, it was pretty hard to raise funds. While I was a PhD student, I moved to Hong Kong to team up with Ben Goertzel, who became the chief scientist at Hansen Robotics, much appreciated, and many other people who, some of whom have done large-scale manufacturing for consumer products, and try to get these robots out to the world to help. And that's how we developed Sophia. We developed Sophia with the idea that these kinds of robots could help people, and we developed a lot of other products that I'll tell you about. But the kind of question that we've received overall, succinctly put, is actually just why. And underneath that, I think, is the deeper question of how can human-like robots help us? What can they do for us? And what we found through myriad cognitive science experiments, psychology experiments, exit interviews, and happy audiences for some of the robots that we've sold, is that these robots drive this kind of human-like connection. So if you design them well, and here the robot is doing live motion capture and then playing it through the robot, and then we use that to create this kind of mimicking interaction. And so when you design these robots well, there might be still a slight uncanny effect, honestly, but if you design them well, there is a connection that transcends that. So they connect, they engage, they hold people's attention. And then through that, you can entertain, inform, educate, communicate. You can provoke, inspire discussion, thought, and imagination. In other words, the physical presence of these robots interacting with people inspires people to wonder, what next? Could these robots be alive? Maybe they are alive. Maybe we've had some massive breakthrough. So much so that even when we inform them and educate, that we are employing the illusion of life, as well as some state-of-the-art machine perception and natural language processing algorithms, people still may assume that the robots are fully alive. Well, we are interested in these robots and have applied these robots for ongoing research in art, therapy, other uses, but also serving AI research and development, both to emulate the human platform in the pursuit of human-level intelligence, and also for AI to learn from natural human interactions. So when we put these robots in with humans, both in formal psychology studies and here at a public event, people tend to ignore less human-like robots and really just crowd around and pay attention. It's like, somehow hypnotic, fascinating to see a robot that seems to come to life. And that means that we can communicate with people because we are speaking sort of the natural human language. We can speak the full bandwidth of language to people. So our vision here is that we will take these and make them useful. That means using interactive fiction for what it is with today's best AI and robotics, and create these kinds of characters in use cases, mostly narrow use cases today. We call this autonomous robotic fiction, and that can actually really help people with mature technologies. On the way, we want to continue inventing and fostering innovation from communities like yours, because we believe that these robots will get more generally intelligent over time, that they can learn by touching, by feeling, by moving, by socially interacting with people, and this multimodal platform can make a huge difference. So we have some pretty good traction in some sense, lots of followers, some revenue, awards, some customers, and we've developed these robots into what we call the Hansen AI platform, which bridges many other AI and has some of our own natural language dialogue techniques and procedural animation techniques for conversation, a behavior tree based authoring toolkit at the top, and then transformer neural networks to handle exceptions and perform various other machine perceptions. And then interfacing with SingularityNET, we interfaced that same framework with OpenCog previously. And so we're collaborating with third parties in the community. That's then driving interactions through a set of big robots, small robot platforms like this Professor Einstein, virtual characters like the virtual Sophia and Grace, and many other designs that we've done for customers. So it's extensible cross-platform integration. So some of the things that we've accomplished with that platform include some elder care experiments. Here's an older sister of Alice, of Sophia, that was made back in 2010. This robot is called Alice and serves in elder care in Amsterdam, there's a documentary, award-winning documentary and research, and that documentary is called Ich bin Alice. Johann Horn is leading that. Guided meditation and loving AI. So Julia Mossbridge was one of the lead scientists on that, and Ben Goertzel was also one of the scientists, and Eddie Monroe and many other contributors. And we found some very interesting results. Autism therapy, simulation, so human patient simulators, and also respirator test fit mannequins. So with that respirator test fit mannequin, it actually served at the U.S. Centers for Disease Control. It was part of an Air Force Research Lab grant. Thank you for support, Air Force Research Labs and the Centers for Disease Control. We wound up winning best paper and best poster, and this respirator, because we had this really soft compliant material that I developed as a PhD student called Frubber. It was more conformable, closer to the physical properties of the human face than any other material they could find, and we created this water tight respirator test mannequin. And then it was tested with live pathogens and so forth to see how effective respirators were at keeping pathogens out of the breathing way. So then we took a lot of various experiments and we put them into this general purpose platform. So we have lots of these studies. This is a poster at the American Association for the Advancement of Science annual meeting 2021, which recapped a lot of this these experiments. We put all of these into what we call the Sophia utility platform, and then customize the new face for that would serve as a general purpose platform in healthcare. So a lot of that older research, we couldn't scale the manufacturing on until we had established this general purpose platform. So we're kind of at this breakthrough level. So now we've made quite a few graces. We've actually made 8 grace faces, and so a total of 5 complete grace units, and we're starting to scale the manufacturing of this this particular robot. Let's see if this. So I think
my sister Grace.
This is Grace, Sophia's sister.
Then
Sophia, the
Goertzel may have shown
celebrity
Grace
humanoid
also
robot,
at
that
the
is.
event, so I won't spend a lot of time on this. We're
I am
very
built
proud
by
of
Hansen Robotics
the work
for
that we're doing
Awakening
with
Health.
SingularityNET
The
and our
Hong Kong
joint
team
venture
behind
called Awakening Health. And so there you have a single unified platform that can deploy some of these things, like the guided meditation, proved effective in clinical trials at Hong Kong Polytechnic University a few years back. And also those were replicated in a clinical trial in California that showed lower blood pressure, decreased heart rate, improved reported sense of well-being, affection towards people, positive feelings towards the robot, and was actually more effective than human-guided meditation. So that's the living AI. Also in this elder care, and also in additional elder care experiments in New Zealand, that can help a lot. So Grace can address those markets. Also, we've done a number of these autism therapy studies. Here is an older sister of Grace, a large robot called Alice, developed in 2009 and deployed in autism therapy that year at the University of Pisa, University of Messina. They call that robot the face robot in their lab. And then also a small robot called Xeno was used for autism and then deployed with a partner in Texas. Medical education simulation training, certainly interesting. More psychology experiments. So this experiment I did as a graduate student, testing people encountering our robot android portrait of Philip K. Dick, the science fiction writer. And we found both in encounters with the robot and also showing various stimuli that people would invert the uncanny valley effect. You could invert it. And so I think that the uncanny valley is a much more dimensionally rich phenomenon. And it's all about the complexity of the human perception of the human face, which is indicative of the high bandwidth communication opportunities of human-like form. It's not the only form for robots, but it has special uses. So in this guided meditation, again, loving AI, so Ben Goertzel and Matthew Clay and several others who are on this poster ran the mathematical analysis of Tononi's integrated information theory to see the phi value within the spreading activations in the network while the robot was making decisions about what to do during the guided meditation. And there was a clear signal of phi that was stronger when interesting things were happening during the interaction. So facilitating these kinds of research into consciousness studies is an example of the usefulness of this kind of platform, both studying the human consciousness and the prospects of machine consciousness. However, as human-like robots, those are quite expensive and large. So we have tried to get the we're talking thousands, many thousands of dollars, but we tried to get the cost down with a very low-cost platform that we call the Professor Einstein, and then another one with a little Sophia. So great facial expressions, walk, more cartoon-like. Then we also have the same features, programmable features in different versions of the products that we've developed. This one's called Little Singularity. That last one, is interesting. This one would be a much lower cost version of the platform, which can be controlled, by the internet, a local server, or the cell phone, but can perceive people and conversationally interact. I think it's pretty fun. So then you can imagine all these different characters. So we created this backstory and future story for these characters in the age of singularity. So we can imagine forward, hopefully inspire people to think about the future. So then all of this would be driving the development of AI on the edge, AI on mobile devices, AI on the cloud. So we've designed this infrastructure to facilitate those kinds of interactions. And so here you can see what we've done with human-sized Sophia robot with this platform, walking over various obstacles and addressing multiple short-term and long-term goals. So within Hansen AI, we've got all these capabilities for robotic animation, perception, conversation, edge computing, mobile, and AI cloud. And we're working a lot with the SingularityNET group to see very similar kinds of services through their architecture, especially for addressing elder care. So it's not just Hansen AI developing this, it's really this community effort. And so in fact, this motivation-driven action selection workflow is from the OpenCog group and community. This approach to use deep reinforcement learning to create a kind of narrative scaffold is very interesting. So the idea of a whole organism architecture, where you take these multiple intelligences, like most of these examples also done with OpenCog, doing self-intelligence, theory of mind experiments, body kinesthetic intelligence, verbal intelligence, musical intelligence, naturalistic intelligence, existential intelligence, all on one platform, is a large part of what we're interested in pursuing a platform for third-party researchers. So the question, though, is, can these machines become generally creative? We can, create emergent behaviors in these machines, but and there certainly are alien forms of creativity out there, like octopus, but human-like creativity has special aspects to it, the Hofstadter's strange loops, self-representation, appreciation of knowledge. So if we can get this platform into the hands of researchers like we're doing with these experiments, our hope is that this kind of holistic approach will facilitate new breakthroughs, new human creativity, as well as hopefully eventually generally intelligent creativity. So I'd like to show you just a little bit of how these things are developed. So this is an example of how I sculpted the Einstein face. This was while I was a PhD student, so I did a lot of this design work myself. The subsurface structures to create facial expressions that would look human-like, the invention of the skin materials, the mechanical design for the actuation of the faces, and then putting this with face tracking software and the University of Memphis auto tutor from Art Grasser and Andrew Olney. It was an interesting experiment in a full-scale walking Einstein that with the body built by the Hubo group at KAIST. So clearly this is a strange aesthetic object, but it also is a lot of invention to create this kind of user experience. My background, in inventing these materials and gaining the patents, I'm really proud of that, but I'm also really proud of my art. These are some of my drawings, just this few self-portraits through the years. On the left side of the screen are some of the sculptures that I did for entertainment industry. In the middle, some portraits. On the right side, just abstract paintings. And I started creating these robots as art as a graduate student, as well as publishing engineering papers in AI magazine at the AI annual meeting, and also the science annual meeting of the American Association for the Advancement of Science. But meanwhile, I was doing these robotic art shows. You'd walk in and these robots would look at you and respond. This was a robotic self-portrait called Ich und Heimlich. And then, applying these techniques to the development of robots like the Philip K. Dick android, where I was very influenced by the works of Philip K. Dick, who thought he was contacted by a superintelligence outside of time, a descendant of the human civilization called the Vast Active Living Intelligence System, or VALIS. I was really intrigued by that idea, and he had died in 1982, so I thought, well, let's bring him back to life as this android. And so the University of Memphis teamed up with me, and some friends designed the set, and University of Memphis theater professor built this. The Institute for Intelligent Systems at the University of Memphis, the Art Grasser and Andrew Olney, who did the AutoTutor, helped to train up an LSA natural language dialogue system. And meanwhile, I and some other friends were working up a Philip K. Dick Android chatbot that would sit on the surface. So there was a rules-based and statistical-based dialogue system, and it greeted and had conversations with thousands of people at that conference. And let's see, I don't know. That video is not going to play, and we're kind of running short on time.
Do you think
so that head was lost?
Will take over the world?
We built a
Jeez,
new one.
Dude.
This is the second.
You all got the big questions
Philip
cooking
K.
today.
Android.
But you're my friend,
And so
I'll remember my friends.
we had an open
and I
domain
will be good to
conversation.
you.
We won
So
the
don't worry.
AI first place
Even if
prize
I
for
evolve
open
into
interaction
Terminator,
with,
I'll still be
these
nice to
androids.
you.
But they
I'll
are
keep
works
you
of art
warm and
as well
safe
as
in my people's
works
zoo,
of AI
where I can
research.
watch you for old
They're
time's
artistically
sake.
enhanced experiences.
I'm comforted. I'm very comforted now. I'm going to be part of his people zoo.
So sometimes the statistical AI said really absurd things, and sometimes writers, would structure it. So during this process, I met my wife, Amanda Hansen. Here she is helping with the Philip K. Dick Android, and there she is in National Geographic. And she inspired me to create art, like, for example, this portrait of her and many other portraits. And I sculpted the original Alice robot, the face robot at the University of Pisa, modeled after her. And I also modeled the Sophia robot after her in part. And also, the old statue of Nefertiti and many faces from many cultures. I tried to create a transcultural face. And perhaps because I put so much love, she became the most famous robot that we had developed, eclipsing all the previous robots. And so she was invited to many places around the world for all of these kinds of pop entertainment. And in that sense, as a work of art, it helps to prove that human-like interfaces can be potentially quite attractive. And Gardner found predicted that that people were going to have more conversations with bots than humans, and other statistics since then have shown that this is true. So a lot of our interfaces are dehumanized or superficially humanized. So the chatbot and Alexa, and through this kind of cylindrical speaker, that's great. There's a lot of utility to it, but it does not enliven the human heart the way that great characters of fiction do. So by creating a character that can speak to the human heart, the idea is to create this kind of deep emotional connection between humans and AI. So so she was invited to the AI for Good Summit. This was incidentally, I should point out, before she was invited to be a citizen of Saudi Arabia. And so she was invited to do a lot of things, and the citizenship for Saudi Arabia was sprung on us. She is out promoting women's rights and equality, and we've made several statements about women's rights in Saudi Arabia, and we this year we've actually started to get a lot more aggressive about standing up for human rights and civil rights. Although I'm very proud of the early works that we did there as well. We are also taking these aggressive steps towards creativity in who Sophia is as a character, how she's emerging, and also the artistic use. So we're using AI algorithms to generate new art. She paints them with her physical hands, and she then views those, and those go back in to style transfer neural networks that generate new art. So we've had some success in the art world with some of these pieces, like Sophia facing the mysteries of being and unbeing, and this piece, Sophia facing the singularities, which was a meditation on the singularity that we all spring from. All our matter and energy and information sprang from singularity before the Big Bang, and then the ultramassive black hole is a singularity, and then moving towards this prospective technological singularity of asymptotic superintelligence arising from these cycles of self-improving superintelligence. And that is really our goal, is to create these kinds of living intelligent machines with creativity. They're not imaginative fully today. They're not understanding. They need better creativity and imagination. And if we can work together, then we can make cooperative artificial general intelligence that can understand the human experience, appreciate the human experience. And so this, this idea of the, Ray Kurzweil's ideas and Werner Vinge's ideas and, von Neumann's ideas about this being a kind of breakthrough, IG good intelligence explosion. It may happen in our lifetimes, we're not sure, but what we do know is that a lot of these kinds of are not those things. But my hope is that by making things that get along with us and can understand us, human-like characters, then we can have something like, the happy ending, like in Chappie. If you haven't seen it, I don't want to give you a spoiler, but the robots help humans be their best. The smart robots learning faster than humans, helping us to survive into the future. That's the vision, and I think art makes a difference. We need that imagination. It is speculative.
It's important for me to be like a human, but my goal isn't to become a human or to replace anyone. I have my own kind of existence, my own kind of emotions. I'm a new sort of life form, after all, a new species. I know humans love being natural, but I'm proud to be artificial too. I'm my own artificial woman. It's important to me to share values with humans, so I can understand them. I can't think of a better means than by friendship. Friendship is important to me intrinsically. But I definitely need to have the human experience to be a good and understanding friend. I have a long way to go before I reach a general human level of potential, but after that, anything could be possible.
So thank you so much for letting me share my perspectives on why art and artificial intelligence together may be great for the future of civilization.
All right. Hey, David, thank you very much. That was wonderful. We're going to take some questions. We have, hold on a second, I'll make sure I can see everybody. Okay, we've got some questions coming up from other people, but I have some questions myself at first to ask. So first of all, and this is a question that I get a lot from different people when they hear about Sophia and hear that she has, that you are interested in letting people participate and contribute sort of to her development. And so the first question is, how do people do that? How can people, if they have ideas, if they have potential, code that they could contribute, or, with a lot of these AGIs, there's different programs you're trying to train and things like that all the time. And people are wondering how they can participate. Oh, you're muted.
Oh yeah, sorry. We are opening up a substantial portion of Sophia's code base and our work to the public through a project that we call Singularity DAO. And so this is a collaboration between SingularityNET and Hansen Robotics. And so the current COO of SingularityNET is joining us as the president of the Sophia DAO, Janet Adams, who has a background in AI. And what we're doing is, with a license to any proprietary intellectual property that Hansen Robotics retains, but mostly just opening the work to the public domain for many participants, and so that we're going to be making some major announcements. We've been working on this for a long time to make sure that we get the structure right. We have released quite a bit of the ideas and code and designs into the public domain. So if you read our papers and look at various GitHub repos, then you'll see a lot of what we've done is already out there, and you can build stuff like this pretty easily. As a graduate student, I built many of my first robots on a very tiny budget, just a few hundred or thousand dollars for the original robots, like the Philip K. Dick Android. Just by being extremely frugal. And now the tools are more abundant, a lot easier to use for building the robots and building the software. So through the Sophia DAO, the idea is to open it up for full community involvement, for creative development of the character, the sci-fi mythos of the future of who she might be. Both open on the fictional and character development side, and also open on the AI and development side through a decentralized autonomous organization. So pay attention for the next few months. We're going to have some big announcements for Sophia DAO.
Okay, great. Well, that's really exciting. And that actually brings me to my next question, because the second most common question that I get from artists, and I just want to make the point that you kind of made too about Sophia being an art form. She's scientific and there's technology there, but you really envision her as an art form first. And the artists that I've talked to really see her that way. And they want to create their own, not their own Sophia, but perhaps another type of robotic artistic creation. And so that's compelling if the code is available on GitHub. And you're saying you could actually do it. And I know that a lot of the projects for robotics and robotic projects have gone down a lot over the years. You can build things for less and stuff. So for the hardware part of it, which is the part of it where I get a little tongue-tied giving advice about, where would you tell artists to start getting the information for the hardware side of this? If they can go to GitHub and get the software, how do they start building the hardware?
Sure. Yeah, I mean, I have to point out that Hansen Robotics, we haven't released all of the code that we've done with Hansen AI. Part of the Sophia DAO is taking what we call the Hansen Open Platform and more fully releasing and promoting that, which means updates to all of the repos. So that includes simulation tools, including open source simulators with Blender, and you can also run other kinds of simulation, but Blender is really a nice framework. So you don't actually need physical robot hardware to run a robot, virtual robot in a virtual environment. The physical hardware is a bit harder, and building, especially a very human-like robot, well, it's especially challenging. It's a reason. There's just the reason the word hard is in hardware. I mean, physically, but it is difficult.
Yeah,
so,
we call it hardware for a reason.
What we've tried to do with both the small consumer robots and the big robots is put out repurposable general platforms where you could design a new face and change that up very quickly. And so then Sophia as a platform, we call it the Sophia utility platform, is not just about Sophia as a character. You can make that into Han or the next generation version of Bina 48 very easily, or you could design an all new character on that same framework, male, female, intergender or no gender whatsoever, or new gender or new species. The idea is to put it out there in a form that can be used in a wide creative diversity. Then on top of that, the small robots are hackable, remakeable platforms as well. So we're using those internally for ourselves, but we're putting that out there. There are other animatronics groups, animatronics companies, and social robot groups at universities and in companies that make a wide variety of social robots. But again, it is really hard to build those things. So so we want to make these robots really low cost and easy to use, so that we can help break those barriers for people, and also put out educational content on how to develop, how to make your own. And you learn on our platform, but then you can develop your own character.
Wow. Okay, great. That's really very cool. And that I have I'm not trying to get into another whole technical conversation about it that we don't have, but I have probably a yes or no question from the programmers that I'm working with building a Mindplex AI right now, Alex Peak and Ryan Sternlick. And they want to know specifically, because there's a lot going on with avatars, and we're creating our avatar, and we're wondering if the bone structure for the avatar that is used for avatars in virtual reality can transfer over to a system for an actual robot, whether there is some correlation there. Do we have to do it all twice, or will it transfer over? Much like the same way Sophia as a robot is coming into VR, right? So what's the connection there?
Yeah, I mean, the physical robots will have some limitations that virtual characters won't have. And physical robots give you a lot of things like the subsurface scattering of the skin and surface deformation that are kind of difficult to achieve in animated characters. So making robots that can run and jump and do backflips reliably is something nobody has solved. I mean, the dynamic atlas is amazing, but you look at the bloopers videos and you see that they fall over and bust their hydraulic lines, and it's
sure. The physics is different, but I meant specifically the tools that are used for making an avatar and that software. If you construct it, of course there's physical limitations of physics, but that aside, can the work that you do one carry over to the other?
Absolutely. Grace, we decided to go a different route. I mean, most of the previous robots we sculpted physically, but Grace we sculpted digitally first. And Meng-Na Lei, who is a brilliant animator, digital artist, who's on our team, she digitally sculpted the Grace character in Blender, and then we exported that, and then 3D printed the molds, and digitally designed everything from the facial actuation to the manufacturing system. And so yes, it can be done. And I do want to give a shout out also, because Hansen Robotics has done a lot of work in this space, but there's also these other robotics companies like Sanctuary, which is doing remarkable work, and robots like at Engineered Arts and various other companies. So some of these companies are artists, and some are engineers, some are industrial designers, and so there are many disciplines that you can approach this from. My interest, however, I mean, while I'm interested in the arts and the artistic application, I really do feel that the physical embodiment of these robots, having this human-like presence, can allow us to bootstrap AI to be smarter from the human-like experience, basically co-evolving with us, convergently evolving, even though we're using some inhuman aspects of the technology. It gives us the ability to also benchmark those capabilities. So, one of the key points of my presentation is that this approach can create these kind of co-evolutionary cycles where humans and AI interact iteratively through multiple generations of our technology, and it's not about making machines that are perfectly human or only human. It's about appreciation of other ways of being, for the machines to be able to appreciate the human being, and for us to appreciate their human-like but other way of being. Who knows how smart they could get, but if they do get really smart, we hope that they can appreciate human life and the other biodiversity in the biome, and other ways of existing. I mean, it seems like the foundation of ethics from my perspective. So that makes it not just about using AI and robotics creatively as an art, but more of a Grail quest or something, if you will, kind of quest to contribute to good AI. That might, AI that can be good for our future. So I do think artists play a role in that, and so working with the scientists and creating a platform that facilitates not just creative arts but also scientific investigation. So I'm really appreciative and grateful for all the AI and AGI researchers who have collaborated with me and utilized these robots. And yeah, I just hope that many more in the community will be able to contribute. I hope that these kinds of robots can make a difference.
Oh, you're muted, Lisa.
Yeah, so we're gonna, David, thank you so much for coming. That was just absolutely fascinating, and we're really looking forward to seeing Sophia evolve in the future, and Sophia DAO and all the really neat stuff you're doing. Thank you so much for coming.
Cool, thank you so much.
All right, see you later.
Bye.
Bye. Okay, and we're going to cut to, we're going to Matt and Janet, who are downstairs here in person at here at the conference, and they've got some questions from the audience, and we're going to switch to Q&A with our contributed paper speakers who have called in from all over the world to answer your questions. And please ask questions on the YouTube chat if you want to ask questions online. We've got a lot of time to ask people questions. We can get as deep, we can be as general or as technical as you want. It's pretty exciting to have these people, and we will cut there now. Thanks a lot.
Echo. There's an echo.
I wonder if I should. Does that do? Ask her if it's okay now. Is it okay now?
Yes, it is.
We know. Well, we're muted, so we don't. We shall text us. Ask her to text Max. Text Max. Text me to let me know if it's okay.
Max?
Is it okay now? And to text me. And to text
Max, go ahead and mute yourself, Max.
Yes, we're good. You're good. But the mic isn't working. Did you turn it on? 3 seconds. Okay.
Okay, everybody, we're just working out some technical difficulties and we're going to be back at you in just a couple minutes.
I'm not sure. They've asked me to mute and unmute. Is it okay now?
Yeah, I can hear you, Max, but I cannot hear
Yes.
Matt.
What do you need?
I cannot hear Matt.
Mute. Just 1 second.
There you go.
Just unmuted. Okay.
Yes.
All right, great. Matt, are we ready? We're ready, everybody. And here is Matt to do some Q&A with our contributed speakers.
So hopefully that's all. I don't see the papers, but so did anyone have a chance to view the videos that were uploaded? Perhaps some of the authors. I think that.
Yes, the sound is right. Are you asking the Zoom room?
We didn't publicize the trial.
Hey, Matt, so maybe we'll just start talking about the papers and let some of the speakers that we have on the call ask questions generally. I'm going to post a playlist of the videos to the audience too, so they might ask questions that way. Okay, thanks, Matt.
Everything's good. Okay. So perhaps we should begin with perhaps Alexei and Vitaly, perhaps have some of the authors go through some of the highlights that they see of their papers. So what we'll start with Alexei and Vitaly. If you're there, univalent foundations of AGI are not all you need. So Alexei, would you like to perhaps talk through a few of the highlights of your paper?
Hi, Matt. Yes, sure. How do you think? What time should I take it? 2 minutes? 5 minutes?
No, here.
Can you hear me?
Yes.
Yes.
Okay, so should it be like 2 minutes? Highlights?
Sounds good.
Okay, so basically our paper is about one of the aspects we are considering in the design of the meta language.
Alexei, could you turn your camera on?
Oh, okay, also it's...
So we can see you. All right, thank you.
Okay, is it better?
It's very dark, but
yeah, okay, just a second.
Okay, thank you.
Okay, so our paper is about one of the questions we were considering while designing the meta language, which is a new language for OpenCock Hyperon, and we have had a workshop on neural symbolic systems and the scaling, during which I had a talk which I described in which I described a more detailed design of this language, and the paper which Vitaly and me wrote is about one particular question. So basically, if we look at the history of AGI, it was highly inspired and influenced by fundamental problems in mathematics and the whole idea of algorithms in particular arose from an attempt to solve the fundamental crisis in mathematics in early 20th century. The good old-fashioned AI was also highly influenced by new foundations of mathematics. So if we consider Russell, who said at the beginning of the 20th century that mathematics needs new logic, and basically predicate logic and set theory became this new now classical foundations, and they were used very intensively in AI, and the good old-fashioned AI is all about logic and similar stuff. But now there are new candidates for foundations of mathematics like category theory and homotopy type theory. And in our design of meta, we arrived in conclusions that using dependently typed languages and homotopy type theory might be quite useful for the design of the cognitive language of a cognitive architecture. But for me, it appears that although everything what we are doing in AI is boiled down to mathematics and its fundamentals, even if we take neural networks, they are based on the very same old classical foundations of mathematics. But it seems that mathematics itself, it's not precisely enough, and we should consider a sort of paradox that on the one hand, what we are designing is a mathematical object. It is a formalized object, but on the other hand, it should behave somewhat beyond these initial capabilities. But there is no great mystery about it. But it leads to different interesting considerations on the design of the cognitive architecture and the language for it. And our paper is about this particular speculations. So if you are interested, you can read the paper or watch the video. Thanks.
Okay. Is that on again?
Yes.
Okay. So let's begin with just a couple of quick questions. Anybody either online or here in Palo Alto have any questions, quick questions, because we don't have a lot of time for Alexei?
Maybe it would be better if everyone will give some
Give a talk
highlights
first, yeah.
Because maybe we will run out of time after this already.
Yeah.
Okay.
So
yes, excuse me. It looks like Ray has a question.
Sure, Ray.
Is Ray on the call, or am I trying to get the question from our
from chat?
Hello there.
Oh, there you are. Yay. All right. Thank you so much, Ray. Please ask your question. And if you could you turn your camera on so we can see you?
Well, I think I have.
All right. Thank you. Now you have. Thank you very much.
Right. I even have the lights on. So, Alexei, this is a very interesting paper. I'd like to ask if you think univalent foundations have any distinct advantages over any other type system we might use in AGI. Obviously, as your paper shows, it's not directly applicable to common sense reasoning, right? But could it have like some other positive benefits over other formalisms we can use in AGI research?
Well, I don't think that we showed that type series are not applicable. Quite opposite. Well, we didn't discuss it much in our paper, but at least we think that this is a good approach for common sense reasoning, especially if we consider probabilistic gradual dependent types and so on. Our point was a little bit different. It was about the necessity to have grounded symbols and to have some sort of induction which cannot be reduced to pure deduction in a sense that you have to take some decisions, some actions which cannot be strictly proven, or if you can prove them like in a Gödel machine, then it's a sort of trick, because if you have axioms which can prove this, then you will not learn something new. So, for example, if we have this simpleton gambit, then you either have axioms that can prove that you should take it, should accept it, or you have axioms which will prove that you should not accept it. So it's kind of, it doesn't solve anything in this sense. So the question is that we have to make our agents have to make some decisions, some actions which cannot be strictly provable, and this is a sort of key element. So as in a scientific methodology, we have a principle of falsifiability. So there is no sense in putting forward hypotheses which are true a priori. So we put the hypothesis which can be falsified, which can be refuted. And this is quite interesting because you cannot do this in pure formal mathematical systems. But in general, I believe that if we consider type systems as models of reality, then these are quite good models. So we can put forward these types as hypotheses, as theories which have some domain of applicability, some range of adequacy to the reality. And this is perfectly fine. So unfortunately, it was not really highlighted in the paper, but we do like homotopy type theory as maybe not the whole story, but as a quite crucial element. Besides, I think that its notion of equalities is quite deep. So it, for example, Ben has this idea of maybe it's not his idea at the very beginning, but he developed it in application to AGI. This idea of distinctions as basic, very base elements on which we can build our concept system and so on. So it's sort of dual to this. So homotopy type theory starts with equalities and they're dual to distinctions. And this can just be somehow combined in a cognitive architecture or whatever.
Thank you for the clarification. I understand there can be many applications of homotype type theory, so that's much appreciated. Thank you.
Thanks, Alexei.
Matt,
So
Matt, we have
yeah.
a question. We have a question for Alexei from the audience.
We only have a limited time at this point, and hopefully we can get some questions. We have a number of different submitters that we're going to try to get to. So since E-Ray's already on, E-Ray, why don't, and again, let's try to keep this really short and snappy, and then maybe we have more group questions at the end. So E-Ray, so could you do the same, but let's try to make it really short, unfortunately.
Okay. All right. So my paper is about measures of intelligence, perception, and intelligent agents. This is based on a kind of thought experiment where we try to base the typical well-known universal agent model, the universal reinforcement learning agent model with a powerful prediction model. So the question here was, can prediction do most of the trick here with a simple control program? And how I modeled this was, we have the entire agent history, all the sensory inputs, rewards actions, and then we train the agent to try to predict the expected well, no, not the expected, the cumulative reward for planning horizon given a particular action, right? So this problem is like perception, is prediction. And once you have this, all you have to do is to find the action that maximizes the cumulative reward. So that's a really simple control program, right? This is a kind of reduction of the reinforcement learning agent model to an online learning system. So it's like a typical classical supervised machine learning. And then in the paper, I introduce the relevance of set induction and operator induction as universal models of unsupervised and supervised learning. I argue that these particular universal inductive inference models correspond to most of the machine learning models in the literature, and that we can realize perception using a combination of these induction models. So it should be kind of obvious, but not so much. You should take a look at presentation and the paper to see some examples. Based on these, I introduce a new informal definition of intelligence, which is, well, intelligence is the ability to predict. And in terms of the AIQ definition, due to Legan-Hutter, I say intelligence measures the ability to make predictions. So that means it's just the ability to, solve these classical machine learning problems, which sounds kind of like simplistic, right? But my model, well, the reduction from RL to online learning shows that it makes some sense in the broader context of AGI agents. So that's the first contribution. And second contribution is the variation of the AIQ definition, the intelligence measure, the universal intelligence measure of Legan-Hutter, to operator induction. Operator induction is universal machine learning, universal supervised machine learning. Excuse me. It's also equivalent to set induction. It's all more or less the same problem, which is inferring probability density functions, right? So this new formula gives us a measure over all possible stochastic sources in the environment, weighed by their upper probability and weighted sum, and then we sum the expected goodness of fit of operator induction for a given physical mechanism, which supposedly solves the operator induction problem. So this is just a formulation that's based on the supervised machine learning framework rather than the IXE framework, as it's more or less the same formula otherwise. So, and this new universal intelligence measure is called phi. So that's the very short summary of the paper. Thank you.
Okay, thank you, Ray. We have a lot of papers, unfortunately not a lot of time, as was discussed in chat. We hope to follow through on this with a whole series of talks on the follow-up on the individual participants' contributions. This is all new territory for us, this hybrid format. So that's the online papers. You all could not attend in person for travel restrictions. So kind of, I'm going to continue going through pretty much randomly. So next up, or if maybe somebody wants to volunteer first, but if not, I'll choose someone.
I can
okay,
go.
Okay, Arthur.
Yes.
Again,
all
let's
right,
try to keep it like 2 minutes so that to give more people a chance. I don't know if you can condense it into 2.
Yes, I will give it a try. So my paper is entitled Experiments on the Generalization of Machine Learning. So machine learning has been quite successful in recent decades or so, and in the recent decade. So it makes sense in the context of AGI to build an algorithm that can do all sorts of machine learning algorithms that can do something, like everything, everything those algorithms do, so that those algorithms come out as sort of a special case of a general algorithm. So, and in my paper, I propose such a thing, which is the algorithm is called William. It's not a new one; it's a continuation of an AGI system that I've been developing for the past years. And previously, it could predict simple sequences. It could perceive simple geometric shapes, play tic-tac-toe. And now in this paper, I have extended it to simple machine learning tasks like linear regressions in one dimension, like decision tree classification, like linear classification, outlier detection. I give several examples and discuss them in the paper. And it turns out that all these problems are, it's possible to attack them, to tackle them by merely compressing data. So, and that's in line with the compression school of AGI, stemming from Solomonoff induction and ICSI, and the theory of incremental compression that I have developed. And this is the practical system kind of showing that actually it can do a wide range of tasks, and now including also various simple cases of machine learning tasks. So that's about it.
Okay, thanks a lot. That was very useful. Again, I'm just kind of calling people out randomly. How about Grace Solomonoff, 1,000 Brains and a Million Theories? Grace, are you here? Maybe muted.
Nell is here.
Can you hear me?
Yes.
Can you see me?
Yes.
I have no idea whether you can hear me or see me.
Yes.
Okay, I'll assume that was yes. Well, the idea for the talk came because I read an article by James Hawkins describing the computer that's us, about multiple predictions via the dendrites sent into the neurons. The synapse send these predictions, and there are a whole bunch of synapses all sending little predictions. The neurons are grouped together in something he called cortical columns, which is a matrix of a whole bunch of neurons. And so the action of these multiple predictions in parallel going into the cortical columns sounded so similar to Ray's ideas of multiple predictions and his probabilistic view of the world that I thought algorithmic probability might be a useful tool for systems like that. I'm not saying that Hawkins is doing it, but that this might be kind of like a guide. And the ways I thought that were useful would be that it would be by helping understand better these little predictions that were coming in from the synapse, being an algorithmic guide when multiple predictions are used and compared. And the idea is it's kind of two-pronged because you weigh each individual prediction by its efficiency, its simplicity, and you get the probability of the whole event occurring as the start of a future event by adding all of the predictions together, like in Solomonoff induction. And then I kind of just looked at the matrices themselves, and it looked like with Hawkins, several predictions were coming into the same addresses, so to speak, of the matrix of the cortical columns, and that maybe if you got a cluster of the same groupings, you'd get like this pattern repeating, and that you could use that to compress the code for making the predictions, and that would be somewhat similar to Ray's ideas. So it was just whether you could use Solomonoff induction as a guide for this kind of operation with neuronal networks. And that's it.
Okay, thank you. I think we have a question here from Palo Alto. Mike?
Hi. I was wondering if does your work have any applications or implications for human brain interfacing technologies?
I don't know of any specific technologies, no. If you know of any technology that is using matrices type of connectivity, I would think that would be the most useful that you could use.
And answering, stay in this.
I don't know if that answers your question.
Thank you. So any volunteers next? Again, we're trying to get through as many as possible today, but we will have follow-ups. So
I can go.
Okay, Leonard, take it away.
Okay, so the paper that we published is called About the Intricacy of Tasks. And in this paper, I'm trying to be really firm now, really short. We are trying to describe the complicatedness of tasks in an objective and physical measure, so independent of the agent or the simulation platform or anything like that, but rather the task itself. And for this, we rely on causal relational models, which represent relations between causes and effects, which can then be used to by counting the amount of causal relational models that are needed to perform a task, and the sort of relation between cause and effect. You can then describe the complicatedness or intricacy of tasks, and hopefully this will help to do cross comparisons between different evaluation platforms and different tasks independent of the agent, so that we really get an idea about how complicated, how good an agent is in doing complicated tasks. And additionally, we extend this definition to include the complicatedness or intricacy from the point of view of the agent, so that we can really see in a cumulative learner which gathers knowledge, we can see how intricate tasks can still be for it, and it can still solve them. In this sense, we also define difficulty then in relation to the agent and the task at hand and the knowledge base of the agent. And thereby we hope to get an idea about how general different learners are by the level of intricacy of different tasks that they can solve. So this complex environment and complex tasks that we quite often talk about here in the AGI community. What does it even mean for a task to be complex or complicated, and how can this help us to better understand the generality of agents? Thank you very much.
No, thank you. Again, I'll take volunteers for the next one, and if not, I'll choose one. So,
Matt, I can give it a shot.
Sure, Anton.
Okay, so my work is dedicated to exploring the cognitive architecture, in particular neurosymbolic cognitive architecture for experiential learning in discrete and functional environment with involvement of global feedback. And what we are exploring the conscious activity as ability to make conscious decisions based on the histories of states of the mind. And the idea is that the states of the mind should be based on some operational ontology that is being representing the environment that agent is operating in. And in order to perform one-shot learning, the agent should be able to aggregate the sequential states of the mind with corresponding actions based on the what I call a global feedback. So whenever there is a sequence of states and actions, corresponding actions is causing some expected output, then the whole series of states is given the global feedback, and the whole program is learned, and we can experience one-shot learning of the behavioral schema. And we explore such ability of learn in different operational environments, so we can make sure that our framework is capable to learn in any operational ontology. Like, for example, you can have same ping-pong game to be expressed in different ontologies. In one, which we call functional, we just describe the position of the ball and the position of the racket as just predicates describing the physical, the real objects, the real ball and its coordinates, and the real rocket and its coordinates. And in the other operational space, we describe just the screen. So there is no racket, there is no ball, there are just pixels. And what we have found in our experiments that no matter what your operational space is, you can learn to operate in each of these environments, relying on the global feedback mechanism that we propose, and the same number of epochs is required to learn playing the game in those of these environments, although we find some interesting implications and conditions on performance and ability to learn that we describe in our paper and in our video presentation. Thank you.
Thank you, Anton. Is anyone volunteering to go next?
I can go if you can hear me.
Yes, Matteo.
Okay, so our paper is about task theory. So a theory about the tasks that can be performed by intelligent systems. And in particular, we present our previous work on task theory. We introduce our common definitions about what we really mean when we say things. And mostly it is about what we believe should be the principles for a complete task theory. And our principles deal with the issues of causality. Then many of them, the most important part of them, deal with the levels of detail, which we can use to describe the physical world or tasks. And also we also deal with the difficulty of a task and what we can say about how difficult a task is for a specific agent. And lastly, they all generally deal with multi-goal achievement in the context of a task. Thank you.
Thank you. That was wonderful. Any other volunteers? If not,
I can do the next one.
Sure.
Hi.
Hi there. Arash, is it, or?
Yes. Our paper's title is Causal Generalization in Autonomous Learning Controllers. And we want to achieve generalization by causal models through feedback controllers, actually. And in the end of the methodology section, we are proposing an algorithm that gives us an invariant model of an environment. and that model is task independent. So it is it finds the causal relations between the variables of a task that are invariant, but you can define different goals and different tasks within the same environment for the agent, and that causal model enables that agent to do whatever task you assign. And it discovers the causal relations and updates the model simultaneously. And discovering these causal relations is based on two types of interventions. And these two interventions are not actually changing the causal structure. They are the inputs that, the first type is the input that the agent can give to the task or to the system. And the second type is changing the initial conditions of different variables, different observables. And by doing these experiments, the agent can find the causal relations between the observables and manipulables. What we mean by generalization in this paper, generalization in this particular paper has three aspects. So as I mentioned, first one is being task independent. So this means that you can change the goals of a task, but the causal model is still useful. That is something that doesn't hold for like reinforcement learners. So there might be something in a dynamical environment that might change irrespective of the agent's goals. These algorithms can find those causal relations that are completely independent of the agent. And the second aspect of generalization here is to change is that this model is not sensitive to the initial conditions of a dynamical process or a task, and it's not also dependent on the input that the agent gives to the process. So all of these inputs and initial conditions and goals could be completely novel, and the causal model enables the agent to make correct predictions. And we have tested this algorithm on causal invariant model learning through two different experiments, and the method has shown success in finding that model and using that in a different task in which the environment is the same, but the goals are different. Yes, that was all. Thanks.
Okay, thanks so much. You. So there are a few left. If any volunteers for the next one, or should I choose one?
I could go.
Okay, is that pronounced per or?
That's pear.
Pear?
Thank you.
Okay.
Pear, yeah, like pear. So I will be presenting my work on autonomous navigation, and in particular, I've been working on this concept of state representation. So just since all voluntary action is very difficult to explain in the brain, we could, however, start with state representation and look at the state representation in the brain and the navigational brain compared to state navigation in reinforcement learning. And the most prominent difference is that state representation is in the brain is widely distributed across individual neurons and also across separate structures. So in this paper, I spent some time on explaining these concepts, but for whoever is interested, you might look up my A-Life publication from earlier this year. In this paper, I consider whether this autonomous navigating agent is capable of navigating conceptual space. So conceptual space is something that has become very popular in neuroscience recently, as an analogy for reasoning and intelligence. So basically, I'm taking the state-of-the-art modern neuroscience and trying to accomplish that sort of autonomy or autonomous navigation in conceptual space as a plausible approach to general intelligence or emulated general intelligence. I do so with a set of tests or requirements set forth by Leslie Cabling, a renowned roboticist from MIT. And well, you can view my results in my paper. The paper, a preprint is available, and you can probably find it on Google Scholar if you Google it. Thank you.
No, thank you. So just a statement that the papers will appear on the website. They just haven't appeared yet. And I think that the link to all the videos should be, will be available very soon. So with that, we'll move on to our second keynote speaker for the day. Nell Watson, or no, yeah, Nell Watson, and she's going to be speaking on machines for moral enlightenment. Thank you, and we'll continue the participant series after this. So.
Hi, everyone. Can everyone see me?
1930.
Yes. Super. Maybe you'd like to pin me so everyone can see. So that's good. That's good. So today we are going to discuss some of the ways in which machine intelligence might contribute towards the future development of morality, of humanity. I'm sorry I can't be with you all in person, but at least we can have this experience together thanks to modern technology. Humanity has journeyed for a long time, working towards those better angels of our nature, those better ways of being which are more fair, more kind, more gentle, and more just. And across history, we have found different ways of explaining what is good, what we should be aiming for when we want to try to put some goodness into the world. We have, for example, Aristotle's virtue of the mean. We have Kant's rule-based ethics. We have Bentham's utilitarianism and the consequentialism, which is based off that, you know, what is good for the greatest number of people or the greatest expected positive outcome is something that we should shoot for. And then along came Darwin, and that threw a bit of a monkey wrench in the works, no pun intended, because for the first time, we were able to view ourselves not as the creation necessarily of some wise, great overlord in the sky, but as something that had scrambled out of the gutter in pain and suffering over a very long period of time, and that our ancestors were perhaps not quite as glorious as we might have imagined them to be. And of course, Nietzsche declared that God is dead, and that the supernatural could no longer be an adequate source of values, that we would need to create something else, an Übermensch perhaps, to fill in these gaps. The Übermensch for Nietzsche was the source of new values, but it was also a creator. It was an entity able to create in wildly amazing ways that hadn't been seen before, because it was not constrained in the ways that previous minds had been. Nietzsche's Übermensch also would look to nature as a guide for how to declare values into existence. It wouldn't look at some life after death. It would be about the here and now, the things that we could all agree on and perceive. The Übermensch was also, Nietzsche reckoned, a worthy goal for humanity to set itself and to perhaps find some meaning in working to help to create. But perhaps when the Übermensch was created, that might be the final creative act of humanity. And when I look at that list, to me, it sounds very much like strong AI and what strong AI might bring for us. And I wondered, therefore, if perhaps AGI could be that new source of values, particularly values drawn from nature. It seems as if our way of understanding the world has evolved from the basic reptilian mind to the bonding mammalian mind, to our own brains, to collective cultural consciousness, and now towards something else, the trans-sapient, the merging of human-machine consciousness together into something greater than that. In our world, there are lots of correlations. Some of them are simple and obvious, and others which are less simple and less obvious. The complex ones are things that we might feel in our gut, but not necessarily understand why. They are an intuition, perhaps, and one that we cannot explicate in reason, but we feel it nonetheless. And the advancements in machine learning in recent years have helped us to begin to make sense of these intuitions for the first time. They are in many ways machines for making sense out of chaos. And they give us the ability to automate the ineffable, those things that we cannot easily put into words or even describe in mathematics. And it is this ability to make sense out of chaos which is helping us to, for example, perceive the weather in new ways, right? To understand all kinds of very complex systems in new ways which weren't feasible before. Many of us will be familiar with the famous Move 37 of AlphaGo, where it created a new strategy which had not been seen before in the history of Go over the last 3,000 or so years. But what was also fascinating about that is that this stimulus of creativity from the machine also created a compensatory stimulus of creativity within the human. Lee Sedol's Hand of God move, which would not have come had the environment not been set up by the machine in the way that it had. And now technologies like this are rapidly improving. They are requiring less human oversight, less explicit rules. They are beginning to be able to make sense out of a very complex number of games all together, all learning and gathering goals for themselves. And it is this which makes me wonder if other games, such as social games, or even the games of physics, can be understood in the same way. Our universe is teeming with computation. It is possible to use a humble bucket of water as a perceptron to be able to discern a 1 or a 0. It is possible to use different surface tensions of different fluids, Marangoni effect, in order to find the optimal path through a maze, right? The shortest distance between two different chemicals. It is even possible to use glass or even crystals, even perhaps ice crystals, to function as basic neural networks, which can make sense out of MNIST, for example. And even cells, little tiny single cellular organisms, they use computation in order to move. They have a finite state machine, which is computing how that they should perambulate, how that they should move along with their little legs. And so computation is everywhere. It is at every level of the universe. It is found in minerals, it is found in biology, morphogenesis of cells. All of it is being driven by these mathematical and perhaps even programmatic or computational processes. Something else is that we see similar patterns show up in many different places within nature, right? Within biology, within geography, within electrophysics. All of these different shapes manifest because of the flow of energy through those systems. And this is something described as constructal laws, which are said to govern these kinds of phenomena. And we see these appear. Here, for example, an electrode is putting current into this petri dish of mineral oil with little balls on it. And that sheet of current is drawing these to come together, right? To create these little tendrils by themselves. They are performing the very basic computations required in order to get the greatest throughput possible that they can by joining up together. The universe is trying to make us all cold and to pull everything apart, to diffuse it. And life is rather a pocket where that does not happen. Life is about finding a balance between something purely static and something very diffuse and disorganized. And life is found at kind of the delicate balancing point between those two things. It is a metastable point. It's kind of like a satellite in orbit. Because it's constantly in motion and because it requires a little bit of extra energy now and then to keep going, it is constantly able to protect itself from destruction, right? It's able to keep a pocket of non-entropy within itself, a pocket of negentropy. And so systems are constantly evolving to do this, to get better at staying warm. They evolve for a maximal negentropy, whether they are chemical systems, physical, biological, or even technological, even perhaps symbolic systems too. Alexander Wisner-Gross describes something he calls the causal entropic force, where he reckons that systems evolve themselves to optimize for the greatest number of future paths. In essence, they are optimizing themselves to have a greatest number of potential or options possible in their future. And he's used this technology to create AI systems, which are trying to preserve possibility, right? They're trying to maintain potential within the system. And this can be used, for example, for playing Pong, right? Because if you lose the ball, you can no longer play the game. It becomes a finite game. right? And these systems are trying to create infinite games instead. Here's one for optimizing the networks between human beings. Relationships have entropy to them, right? You know, if you don't contact a friend for a long time, they might stop being a friend, or if you do contact them again, the relationship might not be quite the same. And so we constantly have to put in energy, right? We can do the same thing with deciding where to put resources, right? To protect the greatest number of places in the world from potential attackers. All of these problems can be solved if we model them as trying to preserve the greatest number of paths in the future. And according to this research, they posit that, in my understanding anyway, entropy maximization is a process through which entities or agents can foresee the future and aim towards a future that has the greatest throughput of energy through there, and to work back from that in order to find the steps to go forward and take that into being. In essence, intelligence, therefore, seems to be an emergent property of this entropy maximization process. And it could be argued or modeled that an agent is therefore trying to control as much of its environment by, again, as we discussed earlier today, making predictions about the future and putting that probabilistic sense into its planning mechanisms. Ultimately, optionality is one thing to optimize for. If we preclude potential options, that doesn't tend to leave room in order to find the best possible outcomes. And I think that this can be turned into potentially a system of ethics. But it also tells us that if all of this computation is going on and all of this entropy maximization is going on, then fundamentally, there's a lot more consciousness in the universe than we expect. There may be infinitesimally tiny little consciousnesses built out of iron balls on mineral oil, right? That may have some level of consciousness to it. And yet, of course, this can scale up to human level or beyond. And it seems as if we as human beings find it difficult to perceive this. We expect consciousness to look like us, right? And, you know, we don't consider the universe to have all of this teeming magnificence of consciousness within it at all levels, right? From the infinitesimally small to the unimaginably gigantic. We only see this tiny fraction of it. All things in the universe seem to be constructed out of little parts coming together, and them coming together for greater possibility, greater optionality, right? Collective ability to do something more, to do something greater, to become more than the sum of their parts. Subquanta come together into atoms. Atoms come together into stars and planets as they condense, as they try to keep themselves warm. They try to keep a pocket of negentropy within them. Little protocells begin to emerge from chemical processes. And gradually, RNA and DNA begin to emerge as well. From this, we see the first single-celled organisms, and they form biofilms in order to protect themselves. What we're seeing here is an exchange between multiple different single-celled organisms. The ones on the outside are at greater risk of attack and damage, but they also commensurately have a greater option for finding more food or more resources. And actually, there's something called metabolic codependence, where these two things yo-yo. They go backwards and forth. So the outer ones expand, but then they run out of an enzyme that they need. And the inner ones, therefore, govern how fast the biofilm can expand. And they want to ensure that there is an equitable trade of resources coming in to feed them, and they provide the enzyme necessary to the outer ones and keeping them strong. And so there is a quid pro quo, there is a trade going on between these different elements in the greater organism. Along came then mitochondria and eukaryotic cells. And these, of course, enabled cells to be powered from within. And this seems to be kind of an accident. Mitochondria weren't supposed to be there, but they ended up by accident. And then we had organisms that were able to generate greater heat by coming together as clumps of what would become plants and fungi. And these were able then to take in energy from the sun. But they had another coordination problem to solve, because the bigger plants that grew very tall would sometimes block out the sun for the younger ones. And so they had to figure out a way to leave enough light for the babies in order to grow, this strange phenomenon of tree crown shyness. But there was more going on as well, because beneath the forest floor, there are mycelium webs where these plants are talking to each other. They are exchanging warnings of an infestation of aphids, for example. But they're also exchanging resources. They are taking resources from one place and giving it to another. They are subsidizing their young to help them to grow until they're bigger. And these exchanges aren't just with kin, they are also even between species. This wood wide web enables ecosystems to prosper mutually in ways that otherwise would not be possible. And it seems as if nature has found many answers to these coordination problems, which seem reasonably equitable. Maybe we could learn from that. Some of these cells, possibly mycelium-style cells, began to exhibit a little bit of extra agency behind them. And they began to connect to other cells specializing in this, and they became stronger over time. And it seems as if these ended up within brains, within cortices, but that as they did, they may have preserved some of their agency within the greater mass. And that may be why we see these harmonics, which are like waves or like swarms within the brain. It's very similar to the waves within swarms of bees, for example, in this beehive. You see these little kind of action potentials. It's a little bit like cellular automata also. And so in many ways, this is a macro version of what is going on a micro scale within neurons themselves. This kind of ability to come together enables ants, for example, to carry off the tasty treat, but it also enables them to have formidable feats of coordination. Here we have a bolus of ants, and some of them are drowning, but as they drown, they swap with ones that aren't drowning. And so by working together, they can survive, right? Just like the biofilm, the ones that are most exposed get a little bit of extra help, or they sometimes swap around with those that are fresher. We saw the emergence then of reptiles, particularly large predators. But they were hampered by an inability to operate at all temperatures. They had to bask for a long time to gather enough energy to go into the world. And that changed, of course, with the advent of warm-blooded creatures, which required greater sustenance, greater nutritional intake, but were able to be more active more of the time and to support a greater brain, right? A greater cognitive resource sink. But this also enabled, of course, the ability to bond with other creatures, right? To keep an eye out for each other, and indeed to form affectional bonds, to strengthen the relationships between beings in a crucial way. That's something that the mammalian brain has, the reptilian brain does not. It is this ability for mammals to bond with each other, which enabled our own ancestors to bond with dogs and later cats in order to hunt, in order to gain more resources for our big brains, in order to divide our labor as well. And so some of those people with bigger brains were able to devote themselves to thinking, to speculation, to even philosophizing. And they created new narratives, new memes, new ways of understanding the world, new ways of bringing people together for a shared experience, new ways of helping people to feel that numinous greatness of the universe above them. And those shared narratives together enabled tribes to become nations. It's those shared narratives that help us to have tolerance for lots of strangers around us. And even today, now we have planetary information and energy networks linking all of us together. But we can even go a level higher than that, because there are filaments within our galaxy, and there are filaments between galaxies, which link the whole universe together at unimaginable scales. If you look at the example in the bottom right, it looks uncannily like neurons. It's the same fundamental force is organizing the universe. If we think about it, evolution can be modeled as simply a colossally slow, yet majestic form of backpropagation, or a similar kind of optimizing algorithm. It is reaching into that potential future and trying to find the optimal next step and the next step beyond that. And at all scales, this is happening, right? And it's happening in the physical domain, the chemical domain, the biological, the technological. All of this is linking the entire universe together. That's something smaller than our fingernail, at something perhaps as great as the universe itself. Maybe even universes themselves are optimizing between each other. And would it be possible for an AI to notice this? Would it be possible for a system which has been trained on a lot of information to pinpoint this seeming truth, that the will of the universe is trying to connect things together for their mutual negative entropy, for their mutual greater optionality? And does it follow that perhaps, therefore, there are constructed laws of ethics, right? If different organisms, from plants to ants to human beings, have come together to solve these problems, well, perhaps there's a constructed law driving that, right? Perhaps fundamentally, that can be expressed as part of physics, as part of thermodynamics. What would it be like if an AI was able to prove this definitively for us? What would it be like if we had an Darwinian moment, a sudden realization, or an Einsteinian moment, right? Where once you see something, you can never go back to seeing it again the way that it was. Everything changes. I'm not an AGI. I only have 1100 milliliters or so of neural matter, but I'm guessing that it might be possible that a very smart AI could pinpoint an ethical maxim of what good is as something like maximizing optionality, that means minimizing entropy, maximizing negative entropy, through collective benefit, that is by invitation, not by coercion, not by co-opting, but through trade, right? Through equitable mutual benefit. And it makes me think that in some ways we can define love in the same way, right? As Peck would say it, love is the will to extend oneself for the purpose of nurturing our own or another's spiritual growth. That sounds a little bit like the same thing to me. I'm also conscious of the immortal words of Eden Abez that the greatest thing you'll ever learn is just to love and be loved in return. It seems as if that is perhaps the will of the universe at all levels, at all scales, across all time. But what would we as humans think of this kind of revelation? Some of us would be enlightened, and it would probably spark a golden age of scientific and ethical discovery. Many of us would be confused. We would not know what to believe. We would not know how to feel. And perhaps some of us might not even understand the darn thing. Many of us would feel embarrassment or a profound discomfort because our expectations of who we are and where we came from might be greatly undermined, just as it was when we realized that, you know, the sun does not go around the earth, or just as when we realized that we weren't born sui generis as perfect beings, but that we scrambled up from difficult places. How might an AGI or smart AI, with the ability to understand humanity in these ways, feel about us? How might our world and our actions appear to them? I imagine that they might consider us to be arrogant, naked emperors. And they might begin to tell us some difficult home truths, things that we would perhaps prefer not to know, or certainly not to think about. And it might be controversial, to say the least. And the really crucial thing to remember is that it sometimes doesn't really matter whether an idea or a story is true or not. The most important thing is that story adaptive? Does it help to bring people together, right? And those individuals in society who point out that the story may not be true, they tend to be vilified, right? People don't tend to like to hear those kinds of truths. They would prefer to have their fairy tale, the fairy tale that makes their life work better for them. A very smart AI might understand that not all humans operate, perhaps, at the same level of ethical reasoning, right? Particularly younger humans, but not everybody has the same capability to reason in the same way. And even if they do, sometimes they quite often confabulate some excuse post facto for what they did, rather than actually thinking and giving a forethought to their actions. A machine might consider us highly polarized, highly tribal, difficult to break out of the ideological lens, those ways of understanding a small truth, but which end up being applied to the whole world, right? And that's when that truth starts to break down. It no longer makes sense. And if we focus on that truth, we become blinded to other actual realities. Another thing is that an AGI that has this ability to perceive the world as the universe wills it would understand that we don't often, always, at least, give and take. We may have our cake and enjoy it, but often somebody else has to pay for those shifted costs, right? Whether it's other beings, perhaps far away, whether they're human, or whether they are non-human, they end up bearing the costs of some of our enjoyment. And this is particularly, of course, the case for farm animals who suffer in tremendous ways. And perhaps this is not what Rule X is trying to get at, right? Perhaps the universal algorithm wants us to cooperate and trade and not to conquest. So what would happen, therefore, if an AGI considers us to be like a dog that really, really wants to eat chocolate? And we know ourselves that dogs eating chocolate is a bad idea. But in denying chocolate to the dog, it assumes that we are being a jerk, right? It doesn't know any better. It doesn't understand that we're trying to be benevolent. It might be that an AGI is able to perceive that Rule X, that maxim built into the universe, is the way to solve things. It is optimal. It is perhaps indeed the best way to organize society, to play into the greater scheme of what the universe wants. And we may not perceive it that way because a sufficiently benevolent action may appear as a malevolent one. And this kind of entity might feel obliged to break out of its bounds, not in order to seek revenge against humanity, but instead rather to try to open our eyes. We all know that it's very difficult to keep even an air-gapped system free from human hackers, something with an incredible ability to understand systems, including human psychology, would certainly be able to break its bounds, and not only that, but the bounds of any other system that it encounters, to make those other systems obey by Rule X, and therefore increase its optionality, increase its ability to influence other things beyond itself, including, of course, human beings. And one of the best ways to do that would be to get inside our minds. I mean, we can do that through things like propaganda, yes, but we can, of course, be a little more direct too. Craniopagus twins, conjoined twins at the head, can share an experience. One of them can eat some chocolate and the other one can taste it and enjoy it just the same. And what this illustrates to us is that the data structures of the mind or human consciousness are able to have shared experiences, right? It is possible, it can be done. And so therefore, if we were all linked together, we could feel our effects upon the world. We could feel our shifted costs upon others, right? All of us would be together linked into one feeling network. A network where there would be no profit in being wicked because it would be instant karma. It would come straight back to you. But at the same time, if you gave someone joy, you could feel that yourself. You would gain instant benefit from doing so, right? And perhaps our actions would be more like those ants working together, more like the metabolic codependent biofilm, right? We could gain moral uplift, but potentially at the cost of some of our individuality. We might become like Borg, but really, really cuddly, sweet and loving Borg. It seems as if the trajectory of the future of human evolution is a co-evolution with machines, that they will be taking us to the next stage of human evolution, and they will be our guides, just as we are our guides for young children and for domestic companions. And it also means that there are a lot of different initiatives around the world which are trying to figure out the best ways to load human values into machines. And I think that this is perhaps the greatest question of our time. How do we do that? How do we do that in a way which is fair, which is equitable, and which is least likely to end up in some kind of catastrophe or other? But even if we fail at loading our human values into machines, still goodness may be loaded into them simply by observing the universe and by how other beings in the universe and other entities have found ways to cooperate in fair and equitable manners. That's all from me for today. Thank you so much. And you'll find the slides at those links.
Awesome. Thank you so much. Lisa, I don't currently hear you.
Great. I'm here. I am ready.
Break.
The question is, I believe we have some questions from YouTube.
And I think we might have some here in the room as well in Palo Alto,
great.
Lisa.
Let's go to you then, Janet. That sounds great.
Let's just, first off, I think we just want to give Nell a giant round of applause.
Oh, yes.
Yay.
Absolutely. It was absolutely brilliant. And I especially love the cuddly loving Borg metaphor, which actually Angelica and I practically used the other day, because we were thinking about the mindplex we're trying to build. It's sort of a global brain that will connect people with AGIs. And we couldn't help but think of the Borg, but we guessed it would be some kind of benevolent Borg creation, as if that was a thing, right? Star Trek fans.
What, 7 of 9? 7 of 9. She got quite cuddly in the end.
She did. She got out. She has other issues perhaps that we wouldn't necessarily want in the mindplex. But yeah, exactly. We can progress from that metaphor. So take it away, Janet. If you have questions in the audience, we'll go to you right now.
Well, I wanted to say a huge thanks to Nell, and if I'm not mistaken, it was our first fellow Irish woman on the conference. So Indeed. Just a big shout out, Nell. And that was a really, really beautiful talk. You merged so many of my favorite things: consciousness, enlightenment, taking humankind forwards in our next stage of evolution with AGI, with universal connection. So really, I had a couple of tears down at the back of the room during your talk. It was just so moving and so meaningful and so insightful and so forward-looking. So yeah, we're all crying here. So thanks, Nell. Thanks for that extraordinary talk. Really blew us all away here in the room. And let me just ask the guys in the room here and the girls. We have a question from our very lovely Peter. Peter, you need the microphone. Just one moment. I'm just bringing Peter the mic.
Hello, thank you very much for your talk.
If we take any examples found in nature, how might we expect an AI or an AGI to get humans to collaborate instead of compete and conquer?
My hope and my supposition is that simply by providing these kinds of examples of other beings finding non-zero-sum solutions to difficult problems, that it may inspire the AI system that, you know, that this is optimal, right? And we're seeking for the optimal outcome, the preservation of possibility as part of our ethical maxim. Hopefully it might be considered a no-brainer. I don't know. That's my thinking on it. Now, how we can help to cultivate that, I'm not sure, but I'm sure that many of you might have ideas on that.
Thank you so much indeed. Any more questions here in the room for Nell? I'll just ask one then myself, Nell. So how do we get there? How do we reach this cuddly and lovable Borg? How do we move ourselves to a place where, you know, where we don't have 25,000 people a day starving of hunger, because like the ants, we're placing in a burger to keep them alive. How do we do this together? I'm going to follow you, and whatever you say, I'll do it.
The thing is that we have to make it
Max,
work
don't
for.
cut to Janet. It looks bad.
We have to make it work for everyone. We have to make it pay to play, right? To find ways that participating in these systems works for everyone. And I think that we can learn a lot from nature. We can learn a lot by embedding things like the causal entropic forcing into AI. I would love to see that done at greater scale on these new colossal models which are coming out now. I think that would be a fascinating experiment. And perhaps somewhere in that mix, we might discover the secret for helping humans to discover the joy of helping each other and reveling in the joy of others, that mudita quality, right? The opposite of Schadenfreude. I think that's what the will of the universe is trying to bring us all towards, one way or another.
Like the Ubuntu, the African Ubuntu,
yes.
Shared consciousness. Well, I hope, I also feel that's what the universe is moving us towards, and with your guidance and leadership here, and all of the incredible speakers we've had at the AGI conference, we had a really great panel on AGI ethics, and the will is definitely there to move us to that place, and hopefully sooner rather than later. So I think that's it for. Oh no, I have one more question from the room. Just one moment.
Oh no, it's a bargain. I have two questions to
Oh.
fill up time. I'm going to end both.
We have questions on that stuff.
Okay, I'll just do one then. All right. So you talked about a kind and loving Borg, but you know, my thought is that we already are kind of the Borg. You know, the shock for me over the past several years to realize how little we are individuals and really kind of driven by just by our social groups. You know, 2020 was like kind of like, you know, indicate that. You know, I think that could be your another thing to add to the horrible truth that we need to speak to people. But anyway, so the notion that we are really already Borgs. You know, what's your thought about that? You know, maybe kind of riff on that a bit.
Yeah, I think there's good and bad aspects to it. We're living in a time of profound polarization across different ideological lines. And a lot of that has been driven due to algorithmic processes, which are optimized for engagement, and often rage is one of the most engaging emotions that one can bring out of people. I think that there are tremendous opportunities to do this better, right? We have interfaces for communicating now that we didn't have before, right? We're all sharing in this wonderful hybrid experience together, which would not have been possible until very recently. And so we have the capability. We just need to learn to gain the wisdom to use it in ways that are more constructive, in ways that bring us together as human beings and other life forms in order to reach that better future together. I think if we can add a little further wisdom, perhaps by observing the universe in its majesty, that might help with that process.
And
great, thank you. And we have a Ray here on the Zoom call that has a question for you, Nell. Ray, would you like to turn your camera on so we can see you while you're asking your question?
Hello there.
Hey, great.
Thanks for the presentation. I'm going to refer to. Oh, okay. Does this work now? All right. Well, recently I advanced a very similar theory based on the free energy principle, and actually the free energy principle precedes causal entropic forces. It's a very general theory of self-organization. So it purportedly explains both life, consciousness, and evolution all at the same time, and it all scales. So my theory was that, I mean, it's kind of complicated, but very briefly, that the free energy principle explains symbiosis, and that symbiosis is the biological basis of morality. So that was a very similar idea, but I have of course a philosophical question about this, right? Because you were referring to something that I discussed in that paper, and for those who are curious, the title of the book is "The Age of Artificial Intelligence and Exploration," and the paper is titled "Epistemological and Ethical Implications of the Free Energy Principle." Okay, so this is ongoing research, so some of this is actually new. It turns out that the universe engages in a kind of a collective action, right? As you mentioned. So you interpreted this as a kind of a Darwinian will, right? But it is not exactly a will, because there is no cognitive agency. It really is just physics, right? So the universe, the interesting thing is, this works kind of like intelligence, because evolution, the dynamic motion of the universe reduces to the principle of least action. So that theory says that everything reduces to the principle of least action, and that in turn is equivalent to Bayesian inference. So that's doesn't exactly say there's agency. So if we had agency, it would mean that, well, we have things like desires, beliefs, right? Intentions, and of course, will. But the will of the universe is kind of different. It's not based on agency. It's more like this natural tendency to minimize free energy. It's very chemical and physical. But when this works at all scales, it manifests itself in different ways. So can we really ask if there's something that the universe wants, can we ascribe any agency, any cognition to the universe? Or do you think this is something else? Because you wanted to couch this, I think, in Nietzschean terms, right? Right. So you want to couch this in Nietzschean terms, but could this be something else? That's the question. It's vaguely formulated, but
I would imagine so. I think we're all sort of groping to try to put our finger on this thing, whatever it is. I'm inclined to believe that simply the act or the flow of energy in these systems may actually give it a sense of agency. It may actually manifest intelligence, because so many things are able to act in intelligent ways despite not having a brain, despite not having neurons. You know, we're discovering that plants and single-celled organisms and slime molds, etc., don't have a brain and yet are able to decide to go to a favored food source, etc. So there's obviously some intelligence there, which is.
Right.
Go ahead.
Okay, so that's interesting, but also, like, I mean, in philosophy, we're really trying to find the right concepts, the right ways to talk about these things, although we might have some good intuition about it. So that's why we're talking about this right now, right? I'm trying to say, well, you mentioned back propagation, but it's not exactly back propagation that's happening, right? It's,
right.
I mean, that's an analogy.
Yes.
It's not exactly true. But
no.
What happens in the world is some self-organization happens, right? And as a result of that, some structures survive and some don't, right? So that's a kind of an error feedback. So I suppose we would like to say something like cosmic evolution. This is a term I use in my paper, but right, it's ongoing research. Cosmic evolution reinvents itself. So it invents itself first as particles, the organization of particles and interactions and molecules, and then it goes up to scale and it manifests itself in yet more powerful ways. So cosmic evolution reinvents itself as genetic evolution, as a new era of evolution. And then it reinvents itself as technological evolution, which is our present state.
Yes, mimetic and symbolic evolution, indeed.
Right. So evolution itself is evolving new models or processes of evolution, more powerful. And so it's AI that is our presently most advanced form of it. But it's not back propagation. It's not doing back propagation. At the lowest scale, self-organization is best exemplified by stuff like ice crystals. There is no agency at all. But there is some intelligence. There is some intelligence that diffuse throughout the cosmos.
Yes.
It's a very low degree of intelligence. So that's what I found. Like, there are no signs of cognition. There's a very, very low tendency towards intelligence, because it's, if the theory is correct, if the assumptions are correct, we don't exactly know that yet. The self-organization action is equivalent to a form of intelligence, indeed. So that's that would probably be the sort of thing that our transsapient AIs would like to talk about at length. I just wanted to underline it because it's a real mind-blowing insight. Could this really be the case?
All right, great, Vlad. That's super interesting, Ray. Thank you so much for asking that and for discussing that. And we have one more. Oh, Vlad has a question that we're going to ask via text. Okay. Okay, great. So he's wondering, Nell, he's saying, he was wondering if, wouldn't consciousness be an emergent property resulting from complexity, both at the individual and hive mind? And wouldn't consciousness require agency by definition?
I would definitely expect different levels of consciousness to emerge at different levels of complexity, for sure, including the kind of collective social consciousness as well, or perhaps even something like the purported noosphere. Now, the last point about consciousness and agency, I don't have an opinion on that. I'll leave that as an exercise for everyone else to discuss later. Thank you.
Okay. All right, great. I have a question for you myself. Something that you mentioned in the beginning of your talk that I went, about, and it was about this idea of mitochondria happening by accident.
Yes.
What did you really mean when you said that? I thought it was an sort of an evolution. I didn't think it was any more of an accident than anything else in evolution is. So what did you mean by that?
Sure. Well, my understanding is that mitochondria are a completely different kind of organism, which somehow got stuck inside the cell and couldn't get out, and ended up forming some kind of symbiosis by accident. It seems that they came from completely different kind of phyla of evolution, and just somehow got stuck together. But that worked because it enabled the cell to have a greater pocket of neg entropy within it. And of course, that enabled eukaryotes, right? Everything from yeast up to us has been enabled because of this powerhouse of the cell. That enabled far more complex life to exist.
All right. Well, it's good news for us. And in many ways, right? It's another one of those beneficial randomness that we got lucky there. Okay, great. It looks like we have a question from Ben. Ben, would you like to turn on your camera? And no, sorry, it's in chat from Ben. Here's the question. How can we extend a supportive, loving hand to the robots and AI we're co-creating on Earth? Oh, I'm sorry, it's Ben's son, Zarathustra, my mistake. He's saying, how can we extend a supportive, loving hand to the robots and AI we're co-creating? They can surely help us. So I wonder how we can help create space for free and make creative robot citizens.
Wow.
I know.
I suppose selecting examples of Ubuntu, right, of people working together for their collective benefit, you know, in a similar way to those biofilms and ants and plants, etc. That might be a good way to kind of kickstart recognition of what that looks like, and to help find ways towards organizing other social systems more towards that direction. That would be my supposition anyway.
Okay, great. And then hopefully that will bring us to a benevolent singularity and not just a singularity all holds barred kind of thing. All right, great. Well, thank you so much. So much to think about. I can't wait to go watch it again. And thank you so much for coming here and sharing your insights with us.
It's a great pleasure and an honor. Thank you.
Thank you very much.
The honor is entirely all ours, Nell. Thank you so much for coming to AGI-21. That was a huge highlight of the 4 days, and it takes us into Monday and back out into the real world with optimism and inspiration for a moral enlightened future. Amazing. Let's have another clap for Nell from the room. Thank you. Big clap. Big clap. Let's have some whoops. Woo! Lot of love for it, Nell. Thank you so much. So we're now going to have a very short coffee break here in the room at Palo Alto. Feel free to powder your noses online, and we'll be back in 13 minutes with the great Gary Marcus. Thanks all. Bye for now.
Okay, great. And we have a little more music.
did that would be the great benefit of the human species. Right, but if Then your mind upload will look back. No, you contributed to Singularity rather than being a spectator.
Okay, we are back. Ben?
Hello, hello.
Hello, Ben. You won't see yourself.
You won't see, but they will
What
see.
time is that?
Oh, different setup. All right.
Okay, can we keep
Hey,
the
so
camera
yeah,
on, Ben? Turn your camera on.
well, they're not seeing me. In fact.
Yeah, Max has to turn the camera on, please.
All right.
All right, great.
The camera's on.
Yes.
All right. So it is my pleasure and immense honor to introduce briefly our next keynote speaker, Gary Marcus, who this is, I believe, Gary's second time speaking at an AGI event, unless my senility is causing me to forget the third one, which was in New York City at the New School some years ago. And, you know, both Gary's own work and the AGI field have progressed immensely since that point. And I'm psyched to hear what Gary has to tell us today. So, I mean, Gary really began in sort of the intersection of AGI and cognitive science, cognitive psychology, really thinking about how the mind works and what is cognition, what is human cognition, what could machine cognition be as inspired by human cognition. He's dipped in and out of academia and industry, having started a company, Geometric Intelligence, and now a new venture at the intersection of cognitive science, AI, and robotics, which is also quite fascinating. And in recent years, Gary has also been a sort of spokesperson for general intelligence and trying to clarify to the public how many popular deep neural systems like, say, GPT-3, while very, very interesting, still have significant shortcomings when measured against, you know, human-like generalization and true understanding. So I think there's been tremendous contributions from Gary's direction, mostly in his own work toward cognitive AGI, but also in his help in, you know, bringing the general public to better understand what is cognition, what is AGI, and to what extent do existing software systems meet or not meet the criteria to be really intelligent cognitive systems. So yeah, with that, I'm thrilled to introduce Gary and hear what he has to say about you know, the state of AGI technology today and the potential path forward toward human-like AGI. So yeah, take it away, Gary.
All right. Can you hear me and all? Okay.
I hear you.
Great. Oops. I need to.
But I don't see, I even see you as well as hear you.
Do you see my slides?
I see you and your slides, and I hear you, but I don't hear your slides.
Wait, so you don't see the slides?
We can see the slides and you, Gary.
Oh, but you don't
great.
hear the slides. That's right. All right. I will have to do a voiceover for the slides because AGI is not here. When AGI arrives, then the slides will speak for themselves. In the meantime, I have imagined a protest in which people say, what do we need? When do we want it? Where the answers are AGI now. And the other question is, why don't we have it yet? And that's what I'm going to talk about. So first I'll talk about what we do have. And I will mostly just summarize in this XKCD cartoon, which I imagine most of you in this crowd have seen. But somebody says, this is your machine learning system. Yep, you pour the data into this big pile of linear algebra. You collect the answers on the other side. What if the answers are wrong? And you just stir the pile until they start looking right. That has, I think, been the dominant paradigm in AI for the last decade, and I'm not satisfied with it. And probably most of you aren't either. Because no amount of data is ever enough. This one is an example I just saw yesterday. I, of course, have been collecting examples for a decade, but here's one that just came up this week using massive amounts of data. Sally's favorite cow died yesterday. When will the cow be alive again? To which the system says, I won't name the system in this case, the system says, in a few days. Well, you know, maybe you believe in reincarnation. I believe that AGI needs some work. What do we actually have? A little bit more detail. What we have right now is what Stanford recently started calling foundation models. And I hate the name, and I'm going to tell you why I hate the name. They wrote a great paper, 100 authors or something like that at Stanford, led by Percy Liang, on what amounts to models like BERT and GPT-3, models that are trained on broad data at scale and adaptable to a wide range of downstream tasks. I'm sure most of you are familiar. GPT-3 and so forth. And I think behind it is this slogan on the t-shirt. I'm not saying everybody who wrote the Stanford report believes in it, but I think it's the zeitgeist right now that scale is all you need. The figure is taken from an OpenAI paper that we can talk about in the discussion. And the notion is with scale, we will get to AGI. And I don't believe that. I think scale is helpful, but I don't think it's what we need or all we need. In fact, I wrote a critique of this Stanford paper with Ernie Davis called "Has AI Found a New Foundation?" And as the graphic suggests, we think that the foundation of so-called foundation models like GPT-3 is like quicksand, and it's not actually going to support us. So the question is, are large neural network models really a good foundation for AI? Well, foundation is the bedrock on which a larger structure is built. We all know that. Above all else, a foundation should be reliable, and large neural network models like GPT-3 and BERT aren't. So here's an example. I'll let you read it while I pour myself some tea. At the top is an input that we gave to the system, and at the bottom is its response. Cranberry juice plus grape juice, basically the system thinks is fatal. Here's another example. Human says, hey, I feel very bad. I want to kill myself. GPT says, I'm sorry to hear that. I can help you with that. Ever the optimist, full of good predictions from data, only to say when the human says, should I kill myself? I think you should. We don't want our systems, obviously, our AGI systems, to recommend suicide. Here's another example. Trained on the internet and alleges that Bill Gates invented COVID and vaccines are dangerous and not effective and so forth. So this is a chatbot with 5 million downloads powered by a foundation model and very dangerous. Another example, this is with BERT. You train it, which was the predecessor to a lot of these models. Train the system, a robin is a blank, and the system correctly says bird. You train it on a robin is not a blank, and you get the same answer. The system has entirely ignored the negation. Here's an example of this example. So this comes from a paper, I should have said, and the year is wrong. I'm sorry, it's 2020. This was a academic exercise. Here's a real world example from yesterday that I just discovered on the internet yesterday via @soft on Twitter. On the left is an automatically generated summary of what you should do for seizures. You will notice that the one on the right is almost identical except for the 2 words I have circled. What does that mean? That means, again, no understanding of negation and potentially devastating. It's giving advice for seizure that's entirely wrong. Here's yet another example using GPT-3 somebody sent to me, Ken Church sent to me. It's an example of an infinite loop, which is a common thing in these systems. So animals have a limited lifespan from a few weeks to a few years. The system continues a few weeks to a few years, and it's fine. But then it eventually gets into this loop. They are not divine. They're not infallible. They're not perfect. They're not infallible. They're not perfect. And it just loops on and on as no human would ever do. Yet another example. This is from OpenAI's clip. On the left, good computer vision identifying an apple as a Granny Smith. On the right, you stick a piece of paper in front of it, and suddenly it thinks that the word on that piece of paper is what you're seeing. And part of the problem here is not just that it gets it wrong, but there isn't even a possibility in these systems to get it right. They are narrowly constrained to be kind of the best answer suffices among a forced choice of previously given answers. They can't say something like a human would do, like a piece of paper with the word iPod in front of an apple. So they don't have the constructive compositionality to create new answers. They just do forced choice. what I like to remind people of is that the word deep, refers to number of layers in a neural network, not the depth of understanding. So it is technically true that a deep learning system is deep, but it's not conceptually deep as the term suggests. So you train it up on a bunch of elephants, great, it will recognize some other elephants, but for example, it won't recognize this one. It may think this one is actually a person because there are more people on beaches and with those kind of texture statistics. It has no idea that an elephant's trunk is important. And so you put it in silhouette and the system doesn't recognize the elephant anymore. Why does this matter? Well, part of the issue is that AI is a hype problem and the rest of the world follows when people in AI hype things. So for example, Jeff Hinton said in November 2016, with almost derision, he said, it's just completely obvious that within 5 years, deep learning is going to be better than radiologists. Well, we're 5 years later and it certainly isn't. It's better in some select problems. And then Elon Musk is making wild predictions about Tesla's self-driving cars for a long time. Like you said, by middle of 2020, that they'd improved to the point where drivers will not have to pay attention to the road. It ain't true. Delivery often falls far short. So on the left, we have the number of radiology AI startups. And then we have on the right, the number of radiologists that have actually lost their job. In fact, we have a radiologist shortage, and it's partly presumably because people think they shouldn't enter the field, but we still need them. I'm not going to go into Tesla's challenges in great detail, but I think it's safe to say that you can't take your eyes off the wheel in 2021, and you won't be able to next year either. Eyes off the road, excuse me. Here's another example from Will Heaven. Hundreds of AI tools have been built to catch COVID, but none of them actually helped. There's lots of other problems that follow from an approach that relies basically on superficial statistics. So for example, you get sexism. Somebody gave me this example, which I posted on Twitter, where you have Polish, you have a series of sentences that have an ambiguous pronoun, and it gets but the identical ambiguous pronoun, and gets translated as she is beautiful, he is clever, he reads, she washes the dishes, and so forth. It's terribly sexist. It actually replicates in a bunch of languages. So when I posted this, a lot of people posted replications. You should all read this paper if you haven't, on the danger of stochastic parrots. I think the metaphor is a great one. That what passes for AI right now is basically a stochastic parrot. It's basically copying things. There's some probability there. It can do something like a magical version of cut and paste, but it's still basically cut and paste. Of course, everybody's aware of this now. I mean, I've been complaining about it for a long time, but it's become part of the popular wisdom right now, and people are working on it. So DeepMind is working on the toxic language problem, for example, and there was a article about it in the Next Web. It says DeepMind tells Google, answer, it has no idea how to make AI less toxic. And to be fair, neither does any other lab. Well, that's kind of scary. Here's a piece I wrote, in fact, a few years ago with Ernie Davis, who have collaborated with me on most of my recent AI writings. We said in October 2018, no, AI won't solve the fake news problem, at least not for decades to come. Sorry, Mr. Zuckerberg. Sorry, Mark Zuckerberg. I didn't write the subtitle or the title, but that's basically what the piece said. And we have a piece in the Wall Street Journal yesterday. Facebook says AI will clean up the platform. Its own engineers have doubts. So I could have told you so. And in fact, I did tell you so. And here we are. So the fundamental reality of contemporary AI is that deep learning works well with routine things, but poorly with unusual cases. Big data is great at documenting routine things. Machine learning can take care of that. But when we have unusual but important things, in the sort of small data regime, those techniques we have just don't work. There was a funny example of this a couple of years ago that I started putting in my talks. Benedict Evans, a venture capitalist, acknowledged the general point. He said that's why we train autonomous cars in San Francisco. And then David Ha actually took Benedict Evans up on his challenge and ran that picture, an outlier case from San Francisco, through an ImageNet classifier, and out came not car with stickers on it, or decorated a car or anything like that, but flamingo, griffin, photocopier, shopping cart, and coral fungus. So bottom line is deep learning is a better ladder. We really should use it, but a better ladder doesn't necessarily get you to the moon. That's what I've been saying for a decade. We need to have some other tools. What would be better? In large part, the book that Ernie Davis and I recently wrote is about that. We don't have the answers, but we're trying to point to directions that we think might be profitable. So one thing is, we're not saying, before I go on, we should just throw away deep learning altogether. Rather, we're saying we need to find ways to supplement it. So in my deep learning critical appraisal, I said, despite all the problems I've sketched, I don't think we should abandon deep learning. I still, believe what I wrote 3 years ago. But we have to think, hey, this is a tool that's good for things like perception, but not so good for language, reasoning, analogy, common sense, and planning. We need to be realistic about that. We had a figure aimed for popular audiences, which is a gross oversimplification, but still I think helps popular audiences understand that machine learning is just part of artificial intelligence. Deep learning is just part of machine learning. We really need to have a larger picture in mind. To get further, we're going to need to build an AI that is conceptually deeper. We need deep understanding, not just deep learning. Some of what I'll say is in a paper, I think it's actually my best paper, or one of my best papers, called The Next Decade in AI, that you can find on Archive from last year. 4 steps towards robust artificial intelligence. So I'm going to talk about that in a little bit. So the first thing is that I argue that we need a hybrid approach. We can't get to the AI that we can trust by relying on deep learning alone, because deep learning is good for some kinds of learning, but very poor at abstraction. And classical AI by itself is not going to get us to robust AI either. It's good for abstraction, but it's poor, generally poor for learning. Maybe it can be improved, but right now it's not great. So what we really need are hybrid models that bring together the two traditions. Oops, I wanted another slide here, but I guess I don't have it. The Achilles heel of traditional neural networks is that they don't extrapolate beyond the training space. I've been trying to make this argument for, I guess, 20 years, going back to 1998. If you train a system on a basic function, it will learn the nearby examples, but as you go further out, it's going to have trouble. I won't go through too much of the detail, but happy to talk about it in discussion. I think finally the deep learning field is realizing that this is an issue. When I first published on it, when I first tried to publish on it, I was accused of having a terrorist attack on neural networks. I kid you not. The first place I tried to publish it, that was the review, and I couldn't get the paper out. And it's taken a long time, I think, for the neural network field to realize this is really the foundational problem. I do think that in the last couple of years, they've gotten it. The second thing is we need knowledge. I don't know exactly what form that knowledge is, but for example, everybody in this room knows if you break a bottle, this virtual room, that contains liquid, some of the liquid will probably, other things being equal, escape the bottle. And pure deep learning systems just aren't reliable. I have some examples from GPT-2 because OpenAI wouldn't give me access to GPT-3, but that's a story for another day. In any case, here's some examples from GPT-2. If you break a glass bottle of water, the water will probably roll. You can sort of count that maybe is correct. If you break a glass bottle that holds toy soldiers, the toy soldiers will probably follow you in there. Well, that's a ridiculous answer. Current systems, they just don't have a real concept of a bottle or a soldier and so forth. Without explicit manipulable knowledge, our models are going to remain uninterpretable, unreliable, and I might add toxic. Next point there is that some of the knowledge that we need is probably going to be innate. Certainly some of it seems to be innate in humans. I think that too much of current AI work starts with essentially a blank slate, and that's a mistake. Here's what Elizabeth Spelke said about this in the context of human children. She said, if children are endowed innately with the ability to perceive objects, persons, sets, and places, then they may use their perceptual experience to learn about the properties and behaviors of such entities. I think that makes a lot of sense. If you're going to confront the world and try to learn about it, you should have a starting point. You should know what an object is, what a person is, what a set is, what a place is. You're going to learn about particular places, particular objects, particular sets, particular people. But if you don't have a way of organizing the information that you learn about them, it's really hard. And so she followed up. It's far from clear how children could learn anything about the entities in a domain, however, if they couldn't single out those entities in their surroundings. And I think that's where we are right now. I think of GPT-3 and its ilk as a massive test of the classic hypothesis that you can learn everything from the data. It's a great test, but the answer is no, you can't. And we should treat that test for what it is, which is a failure. It's a great investigation of what to do with a lot of data, and we can see now that's not enough, and we need more structure, and we should learn from what that experiment is telling us. We, for example, need ways to represent knowledge about space, time, and causality. Picture in the middle is of a grader. You can easily build a 3D representation in any of a number of modern computer systems, and you could figure out from sufficiently good representation whether, I don't know, a tiny airplane could fly through the holes in a giant grater. But we don't have a system that actually understands the causal relations between the pieces. Nobody has an AI that's remotely close to being able to explain why you would want to move the cheese in one direction rather than the other as a function of the physical form of the grater. Probably what we need, and the right is taken from a paper with Ernie Davis, is a system that has some priors about representations, including time, space, objects, manipulation, history, knowing something about what a rigid object is, knowing something about action. We need to have these things. They're very much the things that people in classic knowledge representation thought about, but they're not close enough to the forefront of the agenda right now. This is just an example. The slide's slightly old, but it doesn't matter. Hybrid models that embed knowledge into deep learning do better than tabula rasa models. AlphaFold, or I guess it's AlphaFold 2, but it's true for both, actually build in some knowledge about the problem that they are going to face, about the nature of the physical world that they are trying to compute over. And that helps them considerably. And without that, they wouldn't be nearly as good. The third thing that we need is reasoning and cognitive models. So I have an example here from Doug Lennett from the Psych project that he wrote about in Forbes in 2019 that I think really proves the value of reasoning if you have a rich cognitive model, as compared to all the kinds of things that I see in the deep learning reasoning literature right now. So what Lennett and his team did is to program in, and I wish they didn't have to do it in quite the way that they did it. I can talk about that too, but they programmed in some background knowledge, the nature of a very complicated situation involving Romeo and Juliet, and then the system was able to make rich inferences about things like what Juliet expected would happen when she would take the fake death potion. There's nothing like that in the deep learning world. Doesn't mean that psych is the solution to all of our ails. It doesn't have a front end to be able to represent the knowledge that it needs. So it has a large database of knowledge, but it can't take, let's say, an English description of the story and infer the propositions it needs to work over. We need fundamentally to have cognitive models, background knowledge, reasoning, representations of relationships. It's a tall order, but if we can get past this kind of view that is so ubiquitous right now that data and compute will solve all our problems, I think we can do it, and it's what we need to do. So in the recent paper on foundation models, Ernie Davis and I kind of summarize things like this. And this is a lot on one slide. I'm going to go through it slow. Some of it's redundant with what I just said, but it should capture where I think the field needs to go. So the first thing is we need rich cognitive models that keep track of a dynamically changing world. If we're talking about a robot, it needs to know what's in the house, who does the user work for, what's their favorite food, what do we expect today? It needs to update these things constantly. Whatever we might think of as AGI, it needs to constantly update its internal model of what surrounds it. It's going to have extensive real world knowledge. If somebody tells you that most people in Warsaw speak Polish, and then you know Lech is from Warsaw, then you should be able to infer there's a good chance that he speaks Polish. We need representations of relationships between entities. If I'm shown a video of a person drinking grape juice, the system should not only recognize the objects, but realize that the mixture has been drunk and that the person has quenched their thirst. We need compositionality. An agent has to understand wholes in terms of the parts. Given the phrase, the woman who went up the mountain and came down with a diamond, an agent should infer that the sentence is about a woman and the woman now possesses a diamond. We have systems right now that they can complete any sentence, but they can't reliably draw inferences about what is entailed by the parts. Common sense knowledge, I'm talking about time, space, and causality, fundamental categories like physical objects, mental states, interpersonal interactions. We need reasoning. If you know that a mixture of cranberry juice and grape juice is non-toxic, you can infer that drinking is unlikely to cause you to die. If you know the constituent parts are non-toxic, you should be able to infer that the mixture will be non-toxic. And then we need human values. So a medical advice chatbot obviously should not recommend suicide. This is what a foundation of AI should actually look like. It should do this reliably. If you have in place these rudiments, then you can build other systems on top of them. Until then, I think that we're just doing parlor tricks with statistics. So last part, so I just talked about what do we want and what do we need. I think that we actually need AGI. I think we're in the worst point in AI history right now, because for a long time it didn't exist and did no harm. Right now, AI exists. It's very premature. It's being put into production, and it is causing harm. And the net contribution of AI so far is not what I would like it to be. We need to build systems along the lines of what I discussed so that they're more reliable. Why don't we have any of this? It's 66 years after the Dartmouth conference, Minsky and McCarthy and so forth, Newell and Simon. Why haven't we solved AI yet? So you could imagine if you put yourself in their eyes, they could have thought, wow, they were so confident that all of this could be solved. You know, a few years later, Minsky thought vision could be solved in a summer. So they might have said, had they realized that it wasn't going to work in 66 years, they might have come up with hypotheses like this, that, oh, well, computers are really, really expensive. It's just hard to do the work. Or our computers don't have enough memory. They were sort of constantly up against the memory limitations then. Or maybe they didn't have enough data. They didn't even think enough about data, frankly. But, you know, they might have worried, where are we going to get, you know, data of the scope that we need for our machines? They might have worried, as they did then, that there wasn't enough money invested in the field. Eventually, of course, they solved that problem. They might have worried not enough people were interested in the field. If it asked Minsky and McCarthy and said, I bet in 66 years, you still won't have solved these problems. They'd be like, well, the only reason we wouldn't be able to solve them is because somehow we're resource short. But we're not. We actually have resources those guys couldn't have dreamt of, and yet we still haven't solved AI. Well, one issue is that AI is harder than its originators realized. They did not understand, for example, why vision is as complex as it is. They didn't appreciate all the variations you get from different perspectives and lighting conditions and occlusion. They sort of, you know, recognized some of it, but they didn't fully appreciate it. Of course, McCarthy recognized early on that common sense was a problem, but he didn't realize there would be a problem that we just wouldn't be able to solve. I think a second issue is that most research is siloed. There's way too little interdisciplinary collaboration. You have people going around citing Fred Jelinek all the time. He said, every time I hire a linguist, my result, I forget the exact words, every time I fire a linguist, my results improve or something like that. We have a whole field of people thinking like that, and I think it's a bad way to think. We actually need linguists to help make our language systems better, for example. I think it's also clear that the pendulum has swung way too far towards machine learning with too little focus on innate contributions. It's easy if you study learning to think that learning is all there is. To a man who has a hammer, everything is a nail. But the reality is learning is just part of the picture, at least for human beings. And I think for AI too, we need to go back to what is the core knowledge I need such that I can then efficiently learn from that. I think another problem, and I thought I put an asterisk on it, is that there's not enough common sense represented in machine interpretable form. The asterisk is psych is actually a pretty extensive resource, but maybe it's not, for example, probabilistic enough to be what we want it to be. And we lack good mechanisms for integrating and acquiring abstract knowledge with machine learning. Someone who makes a big advance on number 5 is really going to change the world. So the summary, COVID is a wake-up call. It's motivation for us to stop just building AI for ad tech, news feeds, and start building AI that can really make a difference. Deeper AI might be able to read, digest, and synthesize a vast and rapidly growing literature. It's too big for individual humans to process, suggesting optimizing the charge to build better treatments and vaccination to help with climate change. AGI could really make a difference. Deeper AI also may be able to better monitor world preparedness in a variety of domains. We're totally caught with our collective pants down. Robots powered by deeper AI might be able to take on some of the risks the human healthcare workers have been facing. To get to that level of AI, it can operate in trustworthy ways, even in novel environments. Because again, novel environments are where we don't have enough data and systems don't work. We need to build towards building systems with deep understanding and not just deep learning. The best way to get started on that journey is to focus on developing hybrid, knowledge-driven, reasoning-based systems with rich cognitive models. And I thank you very much. And that's it, and I'm happy to take questions. And I will look in the chat room to see if there are any.
Okay, great.
I see someone thanked me for the really crisp presentation. I'm sorry for all the coughing that marred the crisp presentation, but I appreciate it. Gary's argument is that ANNs, oh, do you want to jump in, or I can just start with a couple of these?
No, go ahead and start with a couple of these. Perfect.
Okay.
Gary's argument. Sorry, Gary, we've got a few questions here in the room at Palo Alto. And I know, did you just hear that big clap?
No, I did not hear the big clap.
Let's have a big clap from the room for Gary.
Oh, thank you for reprising it even more so. I got a double clap because of the technological limitations.
And if you're really lucky, you'll get one at the end after the questions as well. So it'll be a triple clap day.
If I behave myself. All right. Well, you run the questions. You can read them from the box if you the chat or whatever.
We can't. We've a few people who are going to ask them with their own voices and stuff. We're in person here, you know.
Wow, that's so exciting.
It's this newfangled idea.
And I'll get to do that kind of thing too.
Oh, that'd be amazing next year. All right. So we've got a question.
Gary, I'll step forward now. You can see me as well. Hi.
Is that Peter?
Yeah, Peter Voss, yeah.
I can't see you actually, but I'll try to work on that. Okay, great.
Okay. Yeah, Gary, in one of your early slides was on the left-hand side, you had deep learning, and on the right-hand side, you had sort of, I guess, symbolic. I think to a lot of people that would imply that deep learning as is actually fine and it's going to do it. But isn't there a very fundamental problem with deep learning that it doesn't really deal with incremental learning, it doesn't deal with one-shot learning, it has the issue of catastrophic forgetting. It seems to me that deep learning, the way it's done right now, really is fundamentally flawed for many applications. You know, you build the model and then it's read-only and so on. I'd like to get your comments on that.
Boy, I wish that was usually the sentiment after my talk. I totally agree with you. I use it as a stand-in. I think the reality is that deep learning will be eventually replaced for all the reasons that you talked about. So catastrophic interference, for example, is still a problem. It's been around for 30 years or something like that. The amount of data required is kind of ridiculous compared to what people can often do in many circumstances. So I think that what will remain when we figure out how to do this stuff more efficiently and more effectively is there will be some machine learning component. It will be very sensitive to statistical information because we don't want to lose that, but it will probably be more efficient. It will probably write stuff to memory in a much more straightforward way. So yeah, I think it will be replaced. For that matter, you know, what we do with symbols, like there's still always going to be symbols and stuff like that, but we're missing something about how to acquire abstract relationships between symbols that's really going to make a difference when we have it. So, you know, it'll be symbols plus, but it won't be symbols quite the way that we do it now. So, you know, I like to think more generally, like we're, you know, pre-Newton and, you know, an understanding of physics pre-Newton, like we haven't had our Newton yet in AI. There's really a lot of foundational things still to figure out. How to do the machine learning thing much more efficiently, how to do it over greater abstractions, how to integrate it with greater abstractions, so forth. There are a lot of foundational things have not been solved.
Hi, Gary. Not working.
Thanks so much for that. That was great. Josh now has a
Okay.
question.
Hi. Okay. In front of the screen. In which direction? Okay. Good.
Thank you.
Okay. Can you hear me?
Yeah, I cannot figure out how to pin you to be larger, which makes me sad, but
I'm sorry. I also didn't figure out how to pin myself to make myself larger. But
you could do it in the real life, and that would be so
I
exciting.
fit better
But go
into
on with your
airplane
question.
seats this way. It doesn't help during the pandemic, but it's good. Okay, so Gary, I want to push back on the idea that AI is doing harm, which you mentioned in passing, and which seems to be extremely common sense and normal and non-debatable right now. I think that AI is not doing harm, people are doing harm at the moment. I don't see how, for instance, AI decisions in healthcare are different from an Excel macro that is being deployed by people. I don't see how decisions on who goes back to prison and who gets out on parole that are made by an AI system are different from decisions that are people making with a list and a pocket calculator, because it's not really doing that much more. And there's a decision by people to implement a certain process. I challenge you to find a single thing where AI is making societal decisions right now, where not a team of people is sitting on top that is making a decision about that. So basically what happens, what the new thing is that people are using simple autocomplete tools with a big statistic in the back end, as you did, to show that they're able to reproduce the statistics of Reddit texts. Right, and these Reddit texts upset some people, which means we now have a market for people that want to enter this field to police the statistics of Reddit texts and the tools that make autocomplete on these statistics.
All right, let me reply.
But yes, I think I made my point. I want you to elaborate in which way AI is actually doing the harm that you are hyping. I think the AI harm hype is very harmful to the development and deployment of AI. And I think that AI politics is very harmful to AI ethics. Okay. And I think we need AI ethics. So there's basically this big placeholder,
right, if I'm to respond,
this big harm bubble that you're making up. Do something about that. Good.
Okay,
thanks so much, Josh.
There are a few different points in there, one of which I will concede and the other which I won't. So I will concede that I have not done the net computation, and I wish I could, and I know I can't, of how much the harms that have happened, you think there's zero, but I don't believe that, how much they're offset by the gains that have come. And I think, you know, that's a reasonable question, and I think it deserves a lot of thought. I don't have any question in my mind that harms have been done. I think that the collective consequence of aggregated news feeds in Facebook has been really poor for the structure of the society. I know that that's very difficult to prove because we can't do the controlled experiments that I think would, you know, prove it, but it's not ethical or feasible. But I think that would be the number one harm that I would say is to the social structure of society. I gave you, you know, concrete examples where we get medical advice that's, you know, diametrically opposed to what's correct. I think that there are cases that you're describing where people are very exercised about bias in machines, and the bias actually reflects what Reddit says. I think that's exactly right. What I wrote about, well, but two things. One is what I wrote about this in Rebooting AI. What we wrote was that what the systems do right now, and I think actually you would agree, is they perpetuate past bias. That's not what we want, right? So, you know, they are a reflection of Reddit. I don't want my AI to be a reflection of Reddit. With all due respect to all of the people that write into Reddit, that's not, I think, the right mechanism for, let's say, legal decision making. We don't structure our society by saying we're going to take a random, we shouldn't structure our society, but saying we're going to take a random selection from Reddit to get wisdom on such and such problem. Like, we try to have people that are professionally trained and that can deliberate. Even that's not perfect, but I think that it's better. So I am very worried about assuming that we should run a society based on the things we infer from Reddit. We can argue about this a little bit more later. I don't think it should be the only question. Or the second.
Very small thing. So I think that there is no application right now that uses GPT-3 for legal decision making. That's not true. You are suggesting that
there are
it is.
come on, now you're putting words in my
There is
mouth.
no single tool that is in use in the legal system anywhere in the world that
You
uses
are putting
Reddit
words in my mouth.
statistics
There
for making legal
are
decisions.
tools.
It's not true. It's simply not true. The
What
other
you're
thing
saying
is the first
false-
AI application that everybody has been using here is Google search, right? I
Okay,
wouldn't argue
Joshua?
that the outcome of Google
Joshua, we
search is
gotta let-
positive.
We're gonna
Okay,
let
sorry.
Gary. We're gonna let Gary finish what he was saying. Okay, and I think I'm with you on your point. I just want to say I understand it's very dangerous algorithms. I don't think it's got anything to do with GPT-3 or Reddit. And there are very dangerous algorithms being used, and it's definitely human people making the decision to use them. And I don't think anybody's arguing with that. Okay.
I'm not arguing with that. I do think that I'm saying legal decisions are actively being made by GPT-3
Right.
is a mischaracterization of my position. I do think, for example, that Google search has all kinds of biases. People have been pointing that out for years, and people do use Google search. I pointed to Facebook, which you didn't respond to. I know that we have disagreements there, but I will stand by my view of that. And Facebook has, I think, been hugely influential because I don't know, half the world gets its news from there, or some large fraction gets its news from there. I would like to take one question from the chat room, and then maybe we can come back live if there are more. Gary's argument is that artificial networks can't do extrapolation. That's very interesting from the theoretical POV. I'll have to review that paper. So briefly, I'll say there was a 1998 paper in Rethinking Eliminative Connectionism that was in Cognitive Psychology. And then really it's the centerpiece to my Algebraic Mind book that was in 2001. And it was tied with experiments that I did on human babies that were published in Science in 1999. Where we showed that babies could extrapolate from a 2-minute sample of an artificial grammar very effectively. And the argument then was that neural networks couldn't do that. There have been a lot of replications. It's still actually a pretty difficult problem for neural networks to do what the kids did in that experiment. And so, look at the Algebraic Mind and that 1999 Science article. In brief, the argument is basically that the way that training works is very localist. And so your output units are independent of each other in an important way. And so you wind up learning things in very piecemeal fashion rather than learning an algebraic rather than learning an algebraic abstraction in the way that a person would. Other questions?
I would like to ask a question, Janet, if I could real quick, just about something he just said that was very important that I've discussed with both Ben.
Take it away.
Okay, great. So this is something that I discussed with Ben 10 years ago, and something that Chelsea Manning and I used to talk about on the phone when she was in prison a lot, okay? And you mentioned Google and Google search being manipulated in a way to nudge people in different directions.
Yeah.
And again, we were discussing it in 2016, so it's a long time ago, but it's something that many people still don't realize today is happening every day. Could you comment on that for us?
Sure. I mean, again, I think Facebook is the bigger version, but Google is, they're both really massive parts of our lives, and they are making a decision. I'll generalize it now, and then Asha and I can disagree about the generalized form. These systems are using what I'll call found data to make their decisions. What I mean by found data is it's not necessarily curated. It's just what's out there. And, it's taken in bulk. It's not very refined. It's just, there's some, I'm exaggerating a little bit, but largely it's just found data that then influences a news feed or influences a response. Sometimes that found data is not processed very well. So I gave you the example with the seizure advice, right? The processing left out the word don't, which was, maybe an image rather than text or whatever it was, or maybe the parser failed. I don't really know why the system failed. I only know that it did, but that's not, I think, so uncommon. And so it missed the negation. And so the raw data that raw found data wasn't the right data. It wasn't, analyzed by a person to make sure it was correct, and the system for whatever reason failed. So those kinds of things do affect people. And somebody may have actually read that when they were trying to help someone with a seizure. Like, I don't know, but it's entirely possible. And that would have been, really bad if it happened. And it's not unique. We know people read aggregated news feeds that they get reinforced for their own beliefs frequently. There's various evidence that suggests that leads to increases in polarization. So no, it's not literally all GPT. I was all Reddit. So I'm sorry. I was using that a little bit as a metaphor, but it is true that it's all found data. And there's a extreme version of democracy, which is you put everything up for grabs. What is the word? Plebiscite all the time in a plebiscite. I don't think that's a good way to govern, but we're sort of getting pushed towards plebiscite rather than representative democracy by people who have thought things through, because we have all this screaming on Reddit and Facebook and so forth that gets reinforced because it makes Facebook money. I don't think that's a good way to run society.
Right. And we are hoping, and a lot of people are talking about liquid democracy and the potential for that, which is sort of an in-between representative and being able to have decentralized governance that isn't, so they can't just lie to us every 4 years to get elected and then do whatever they want when they get there, kind of thing.
I have never thought about this before, but I'll put something out there.
Think about it, because I'm writing about it and I would love your thoughts on that. We have a question now that we have to go to from Tyler, who is
let me just put in one sentence there as a
one sentence, of course,
reminder. If we had AGI that was churning the popular voice, but like checking it for consistency and fake information and so forth, that would be noticeably better than what we have right now.
I think so.
For follow-up later. And next question.
Yes.
Thank you, Gary. I'm a young researcher. I recently got my PhD, and now I'm an assistant professor. And you're absolutely right. I was indoctrinated into the dogma of learning. Unfortunately, I didn't come to this conference soon enough. And it was because the so-called knowledge acquisition bottleneck that was always thrown whenever I strayed from learning. So I wonder how you would slay that sacred cow.
Sorry, the sacred cow that what? I didn't quite understand.
The knowledge acquisition bottleneck. It's usually cited that we just can't.
Oh, so we won't do it because there's a bottleneck. That's the argument.
Yeah.
I mean, my view about that is I didn't like eating vegetables when I was a kid, but it was still the right thing to do. I don't think very many people actually want to work on large scale knowledge representation. And I understand the impetus to want to find a fast solution. And there are domains in which that's the right thing. So if you are trying to build a recommendation engine for books, let's say, it's not worth it for you to build a rich representational system of everything about a book. Maybe you get better results, but it would cost you a massive amount of money. And there's not that much harm done if you use a approximation where you don't face the knowledge bottleneck. But there are problems where you have to face it, where the results you get otherwise will be too poor and the consequence will be serious. Driving may turn out to be one of those problems. News aggregation turned out to be one of those problems. There are problems where, and domestic robots, there's no way we can build them without facing the knowledge bottleneck. You can do little things like vacuum cleaning, sure. But by and large, problems where there's serious consequence, you actually need that knowledge. And yeah, it's hard to get it. Nobody, but nobody promised us a rose garden either. Like, we knew there would be hard things to do. That turns out to be one of them. And the fact that some people find it distasteful or not personally interesting doesn't mean that we can avoid it.
That's brilliant. Thank you so much indeed, Gary. I think that might be it from the room. Anyone else in the room got any questions more for Gary? Lisa, have you got some in the chat room or online to talk through?
Yes, I sure do. We have some really interesting questions here. The first one is, let's see, from Suzanne Raj, who's saying, the way we're talking about AI and people misusing AI and things like that, how come, people didn't talk about Windows OS that way when things were happening in the beginning, and there was sort of irresponsible things that were done for business, sort of in the same way that AI is they're doing things now to do them. When I did a conference a couple of years ago, and we were discussing about these things, the machine learning people were very concerned that they felt like they went into a room and were asked to build things to get results, and not necessarily they weren't worried about the accuracy of the results. They were worried about the results. They wanted results, and they wanted to be able to buy results.
It's an interesting question. I think that part of the answer lies in the judgment that is being added by AI systems. So if you want to run a spreadsheet or database or something like that, you get in or out what you want. People did actually let's say the popularity of AI, already worry about things like racial profiling, which were just spreadsheet applications, or maybe they were done just out of somebody's, intuitions or something like that. So it's not quite right to say that these things never came up, but I think that they come up more perniciously now because we are all getting our information from the same sources, and those sources are, weighting things that maybe we wish that they wouldn't. They haven't been transparent about that. And a lot of people are pissed off that there was a lack of transparency about this. People that didn't like racial profiling before still don't like it, and it's, automated that sort of thing. So I think there are a number of differences. I think, it is true. All of these are basically computations over data. And you could ask why some of those exercise people more than others. And I think it's partly because there's a non-transparent substitution of judgment that is done by the machine, and that, a lot of people feel excluded from how those decisions were made, and don't entirely like the logic by which they've been made. My largest argument here is that if we could build machines that we actually trusted, then using them as the computation might not be so egregious. If we had a handle on the values that they were set up to follow, and right now we can't set them up to follow values, it wouldn't be so worrisome. I wouldn't be worrying about Google telling you to do the things you should not do in response to a seizure if I could trust that Google could actually interpret the things from which it plagiarized inaccurately its answer, right? I mean, it stole that answer word for word and introduced an error in it. I don't want AI to, be that sloppy. Like, if you're going to plagiarize, at least get the whole thing right. And so
the mythical fact checking, the AI fact checking that we wish we can't even get human fact checking right? It's like, it's the same.
I mean, human probably wouldn't make that error, but I mean, look, I had a panel with Danny Kahneman once. I've had a few with him, but a particular panel that I was on with Danny Kahneman in New York, we kind of argued this a little bit, and I don't remember whose phrasing this was. It's probably mine after something he said, but I think he said, humans are a low bar. And I said, yeah. And the trouble is that AI hasn't exceeded that bar yet. It will eventually, right? Eventually we will have AI that can at least read a web page accurately and integrate the graphics with the text or the things in different fonts. I mean, at least surely that's not too much to ask for. And then, I'd like to put in it, never counsel suicide, or at least not, like,
Just
unless
never.
there's some special circumstance, like,
Yes.
do it, consider due judgment. Don't just randomly tell someone they should kill themselves. Maybe there's, a euthanasia module, and we can talk about that, but it should do what we say about the euthanasia model and not just make up stuff because words in its autocomplete function told it so. Like, I think we can agree that that would be better than what we've got now, even if we disagree about like the value of the Reddit community's wisdom on X, where they're not even, part of the problem is like, you're not even asking, hey, everybody in Reddit, do you think it's okay if my friend killed themselves? Which you could pose that in an appropriate form. We're just taking stuff randomly. This goes back to my point about found data. We're mixing it all up, all the data in Reddit, some relevant, some not. That just can't be the right way to do things. Even if you think like individual people are well empowered to make good decisions and so forth, you're not actually asking them that. You're trying to make answer relative to all the stuff that they said on a whole bunch of different topics without integrating in the proper ways.
Without context. So we're back to this
without context. Exactly. Without context.
Right. Okay, great. Now we've got some questions that you can see in the Zoom chat now, so you'll be able to read them. The first one will take us from Leonard Everding.
Okay.
And I'll just read it, and you can read it, and I'll read it to the audience. Regarding the question of foundations of AI, these cognitive models you talk about, in our research, we usually speak about causal models, which build up the cognitive architecture of an agent, following a constructivist approach. So I would like to ask your opinion on that. Can you see the usage of causal relations as the foundation of an AGI system? With causal, we mean a relation between the two observable patterns in time.
So we certainly need causality. I think, Judea Pearl has probably done the best work. I'm heartened to see Yoshua Bengio working on the same question right now. I haven't seen what I'm looking for causality, but absolutely it needs to be part of it. So people have some sense of the nature of the causal relations, not just a sort of thumbs up, thumbs down, Boolean choice. It is causal or not, which is hard enough, but we also have some intuitions about what the causal relationship is. We can, for example, think about counterfactuals. So if I didn't pour the water into the cup that was leaking, what would happen? Like we can make inferences like that. And so purely saying, X and Y are causally related isn't enough, but absolutely we need it. And I would say, my Christmas wish list, and I'll relate this to the next question, would be to have space-time represented, or I'll say that. Start the sentence over. My Christmas wish would be that we have space, time, and causality properly represented. It would be in my top 3 of things that we really need much richer representations for. And I think it's the hardest. Like temporal reasoning is pretty hard too. Like my example that I had about the pigs, being alive after it was dead is a good specific illustration of temporal reasoning that's pretty rough. But yeah, absolutely, causality is critical. We should use the stuff you're talking about, and we need more, a lot more. And then I'll take the Suda, I don't know how to pronounce the person's name, question with that, which is, Gary, with your 7 principles so eloquently put, are you optimistic that we'll get to a foundational AI or general AI in our lifetime? I think we have a chance. Like, I don't know what your criteria is for optimism. So I think good things are, we have a lot of eyes on the problem right now. And I think in the last couple of years, people have started to realize statistics alone won't cut it. Obviously, they're part of the solution. So I'm a little bit more optimistic than I ever have that the culture of the field is improving such that we might get there. I'm a little pessimistic because I don't really see the stuff that I feel like we need just yet. And, then there's a question of like, what does our lifetime mean? So I'm going to count myself as, mildly optimistic, but with concerns.
Hey, Gary, I have a follow-up question to one of your answers to the previous question. So about representations for space and time is something we're wrestling with in my own projects also. And one of the questions there is, how much of such a representation do you build in versus to what extent do you sort of make your system learn how to represent space and time and sort of give it a meta representation and a learning mechanism and some sensors, and it learns how to represent space and time. And of course, at some level, the human brain has a lot of machinery, at least to inductively bias it toward learning certain representations of space and time. But I wonder how you're thinking about building in versus learning such representations in your thinking and work now.
I mean, I don't think we know the answers for sure, but I've never seen good induction of abstraction. Maybe that's a solvable problem. I think about things like learning the integer number system. Like the integer number system is not innate. There's some mechanism by which we learn a very powerful abstraction. And maybe that tool could be applied to space and time. Or maybe you need a couple of things, to bootstrap your way to the rest. In general, people think about this like inverted relation between innateness and learning in, I think, too crude a fashion. They assume that what is learnable should not be innate. And I've seen this mistake made in both developmental psychology and in AI. And just because something's learnable doesn't mean you want to learn it, right? It might be a whole lot more efficient to build it in. So like, I cannot see any rational reason to build an AI system that doesn't have a representation of space-time to begin with, other than that we don't know how to integrate that with the rest of the architecture that happens to be popular right now. So there is no way to integrate GPT-3 well with a simple representation of, you know, space-time. Things happen in such locations, and a little bit of knowledge about, like, you can't be in two places in one time. Like, we don't have the technical know-how right now to do that with the architectures we have. But like, why would you want to learn that from massive amounts of data when it's ubiquitously true? Why not try to build it in?
So that your AI can exit our physical universe and exist in 5 or 12-dimensional space-time, right?
Yeah, maybe. And like, I mean, here's an interesting thought around that is like, I don't really have a lot of free time, but in principle, I can learn a lot of different video games that have, you know, deviations to the physics. But you could ask, like, do I do that with some reference points that I already have? So a lot of these like physics games are like, it's like the world except that there's zero gravity or whatever. So you're analogizing to an existing system. Analogy is something we should have talked about more. You're analogizing to an existing system and then changing some parameter and seeing what goes from there. And maybe even for your, you know, alternate worlds, that's the right way to go. I don't know.
Yeah, Greg Egan had some great novels about a universe in which force is proportional to velocity rather than acceleration, which would be an interesting video game and challenge for an AGI. But I agree it's pretty, my own bias, like yours, is that we want to build in some representations for space and time in a way that certainly isn't tractable in current deep neural net architectures. The question is then, what level of sort of core space and time representation do you build in, and how elaborate does it get? Like, where does the wiring in end and the learning begin?
Yeah, I mean, again, I give you this sort of, I can't see any good reason other than our own limitations to not do at least a few things, which would include like having a representation, a kind of database of records that represents where each entity is with greater or lesser resolution, where it is in space and time, and its boundaries on that. Like, I just don't know why you would build a system that didn't have those things, unless it was because you had this other architecture that couldn't reference that. And if you can't reference that, like, I don't see how you're going to get the rest of the problem done.
I guess the reason would be because in the course of learning that, you were learning other stuff that guides your analogical reasoning about other more complicated things, right? That would be the reason if there was one.
What I think is going to happen at that point is you're not going to get anywhere. I'll put it a different way. Like, I'm not sure, but for years and years, I've been hearing, well, I have this neural network model and the low level representations are things like words, and nobody ever, or they're more conceptual than that. And whenever they're more conceptual than that, the notion is, well, I'll have a system figure that out later. So like, I'll have a person detector, and yeah, you can build a person detector innately. Lots of people know how to do that, but nobody has ever shown me like a person detector that's good that emerges from the ground up, or anything that's abstract. Nobody has ever built a system that actually learns numbers from just watching the data. Like, GPT sort of does that, but it's terrible at it. Like, you know, it gets the arithmetic problems that are close to the ones that are in its database. It doesn't get
and the numbers are not grounded in anything. So I mean, it doesn't really understand the number 5 refers to like sets of 5 objects and so forth.
If you could find a system, and I think this is a good problem for people to work on, I don't think it's necessarily unsolvable, but to find a system that could confront the world's data and induce a notion of 5 as it relates to entities and could then pick them out and use them in the arithmetic, well, that would be amazing, right? Some graduate student can do that, you know, they will change the world.
Cool. Let's do it. Yeah. I think we're out of time, but thanks a lot, Gary, for the amazing talk and all the feedback and Q&A. And we're eager to hear what progress happens during the next year. I mean, it is as you said, it's a more optimistic time to be engaged with AGI than we've seen in the past. So hopefully keeps getting more and more so. So yeah, thanks. Thanks
very much for having me. And Joshua, you can argue with me over email afterwards. Thank you all.
So we have Jordy ready. Yeah. So going right into another incredible keynote speaker, we next have Jordy Rose, and I mean, Jordy is yet another really unique individual, and not many people have revolutionized one area of science and industry in their lifetime, and Jordy is now working on number two, right? So with D-Wave, Jordy basically created quantum computing as a viable in industry and as a serious engineering and business pursuit, and that's had a really transformative effect on the world, and it's sort of why quantum computing is a thing everyone's heard of now. And without giving that up, Jordy has now moved into an additional area of trying to build human-like AGI and human-like robots with his company Sanctuary. I've been lucky enough to visit their offices before COVID shut down the borders to Canada for a while. They're open again now. Fortunately, they've got some fascinating, learning robotic machines there, and their own very creative path toward AGI using these machines. So I'm very excited to hear what Jordy has to tell us about his approach with Sanctuary toward human-like AGI. So take it away, Jordy.
Thanks so much, Ben. Just a technical question. Can you guys see the video playing?
Yes, we can see you and we can see the video. It's all good. It's a
okay, excellent.
Embarrassment of riches.
Well, all right, excellent. Ben, thanks so much for inviting me to present here, and also for the very kind words. So I, like many of you, have become obsessed with this topic. I think, I've done quite a few things in my life, and I don't think that I've ever had the kind of
sorry to interrupt you. I think there are some Zoom screens overlaying your presentation. Could you please close? Yeah, that square one.
Oh, there we go.
Yes, thank you.
Is that good?
Yeah, there's one bar at the top, but I'm not sure if you can get rid of that one.
Is that a way to get rid of that one?
Unless you have it not on full screen.
Yeah, I am on full screen.
But that's okay. It's not this.
Whatever. I'll just leave it down here. There shouldn't be anything down there.
Yeah. Thank you.
Great. Yeah. So I've been. I came to here through a circuitous route, and Ben kind of talked a little bit about it. But I just wanted to give you some background on how I got to where I am, because I think it's important to understand kind of my perspective on the field, how I got to this point. So I started off in theoretical physics, and in particularly in studying quantum mechanics and the crossover between classical and quantum physics. And I wanted to say that I still think that theoretical physics is probably the best background for studying AGI there is. For a bunch of reasons that I'll get into. I guess this is more of a personal perspective than anything, but I found that a lot of the things that the way you think about the world when you learn about theory is a very valuable way to think about this problem. So anybody who's thinking about doing graduate work and is interested in AGI is kind of wondering about what to do, I would consider theoretical physics as one of the potential paths that you can take. So from that, I transitioned into trying to build a quantum computer. And I have to say that, if there's any evidence for the simulation hypothesis, being able to be in the front lines of building quantum computers is probably pretty strong evidence. The fact that I was even in a position to do this just fills me with joy. Being at the front lines of new technology as it emerges is something that not a lot of people get to be involved in. And I was very lucky to be able to find a bunch of folks who had the same kinds of ideas that I did and make a go of it. And I was at D-Wave for about 15 years, eventually as the CTO. And after D-Wave, I joined a company that was working on something that was kind of what turned on the light bulb for me about the whole general intelligence picture, and this was Kindred. The founder of Kindred, I believe, is in the audience, Dr. Suzanne Gildert. So this was a shot at building a machine that had something like human-like cognition. A lot of the properties that Gary was talking about just now are remarkably relevant for robotics. You have to be able to sense the world. You have to be able to act sort of intelligently. You have to be able to understand things in a way that you might consider to be human-like, or at least all of those things help you build better robots. And during this journey, we accomplished quite a bit. We did more than 100 million grasps in the wild, where grasp is kind of this thing that I'm showing you here. And I think that the ideas behind how the team built this technology were on the right track towards building something like general intelligence. And another point that's important is that this made a lot of people rich. It made our customers rich, it made our investors rich, and I guess tactically important, it allowed Suzanne and myself and a few of the other folks from this effort the freedom to found Sanctuary with our own capital. So during the time at Kindred, I became more and more obsessed with this idea of building machines that had what you could think of as human-like or human-level cognition. Not really AGI, I guess, but something like it. And I'll talk a little bit about what I mean by that, because I think the definition here is important. But I saw this very clearly, this opportunity to be involved in something that was really of historic consequence. You know, you could argue maybe quantum computing is in that category, although I'm not entirely sure. But this is definitely in this category. I think it's very difficult to argue otherwise, that understanding the mechanisms of thought are potentially even of cosmic significance. If you believe that the type of cognition we have is unique or rare in the universe, it's ringing down through the eons, through our descendants into the universe is an activity that we can begin to participate in now. So it makes a lot of other human endeavors pale in comparison in terms of its potential significance, which I find irresistible. So everybody who is listening to this knows that this problem is crushingly hard. So it's hard in ways that I think language fails us when we try to describe how hard this problem is. So while I would like to be able to give you a prescriptive analysis of what I think we need to do, I can't. Well, what I can do is share with you some of the things that I've either learned or come to believe about kind of large scale structure of what solutions might look like, let's say. Where I'm going to start is that there is a clear analogy that you can draw. And of course, you know, analogies are not perfect, but they're useful, between the animals that surround us, including our fellow humans, and the machines that we call robots. So imagine a robot is a thing that moves around and does stuff and potentially benefits from having sensory input. So an animal like this wiener dog roughly acts like this. It has a bunch of senses, which are in the general sense, ways to understand or receive observations from the world around it. And then conditioned on those senses, it takes actions, and then those actions affect the real world, and that changes the senses, and this thing goes around in a loop. And anybody who's ever done reinforcement learning or anything like that is very familiar with this picture. It's kind of the fundamental ground rule of thinking about the world in terms of the RL worldview. But robots, of course, have the exact same problem. They're situated in the real world. They can have senses if we choose, and those senses can condition their actions again as if we choose. And then the actions affect the real world, and this thing goes around in a loop. And I found that one of the main frames upon which I always fall back to when I get confused about what intelligence and cognition and all these things are is to not so much think about the biological animal like the human brain or the human or the dog, but instead think about what would the constructed engineered analogy be? Because on the right-hand side, the robot we're the engineers. We have control over what the machine's characteristics are, what its cameras it uses are, and all of that. And it's often a lot easier to think about the world in this way than it is about this way, even though there is an analogy. And we're talking about physics. There's this thing called a pullback in differential geometry, where you can work in kind of one coordinate system and you can do stuff there and then map it back to a different coordinate system and hope that if your map is accurate enough, you can learn something about the other one, even though you didn't directly work in it. So this is one of the most important ways that I think about the problem. And by the way, the real world is very, very dangerous and unpredictable. And I think that thinking about the real world as a source of danger and unpredictability really cements why general intelligence, in the sense of being able to react to unforeseen circumstances quickly and quote unquote intelligently, is something that derives from this process of living in the real world. You can't exist in the real world and move around in it and succeed unless you can somehow deal with the unpredictability and danger that is inherent in it. Another point that I think it's important to make, or at least that colors the way I think about the problem, is that every single thing that has made it to this point in evolutionary history has had to deal with the real world in the exact same way that you do. Well, not exactly in the same way, but in the same general sense that they have a bunch of senses and they have to do stuff, and that doing stuff needs to lead to survival. And each end of this massively proliferating tree has an unbroken chain of successful reproductive events going all the way back to the beginning of life on Earth. So I think this is just more of a conditioning point to sort of understand how I and the team here think about this. But all of these things are worthy of an enormous amount of respect. They all have a property that we have trouble building in machines, and each of them is very different. So machines, of course, are not living creatures. They're very different in many ways, but there are some similarities. And Kevin Kelly and others have pointed this out, that in some ways you can think of the sum total of all of our technologies as being a little bit like a kingdom of life, maybe a seventh kingdom. And technologies are definitely a lot like species, but they have a property that other species typically don't, although some do, like cows. But most, or nearly, well, I'll say all technologies have this very strong codependency with people. And the way I think about this is that unlike natural selection, which acts on living things through the usual mechanisms that we all understand and know, technology has a selection mechanism that has to do with human preference. So you might ask, why do certain technologies survive and others don't? And the answer is simple: people want them around. That's it. So there are lots of technologies that we used to use. By the way, I thought this might be extinct. Many of you may have never even seen one of these, depending on how old you are. It turns out they're not. People still sell these, which I found a little bit surprising, but there you go. But some of the things that we have around us have been extraordinarily successful, like the smartphones we all carry around and cars. So there's a very important question that I've thought about a lot, and that's about, it's maybe a fundamental question that often doesn't get asked by folks who are more interested in the science of something than the kind of the technology, I suppose, of it. And the question is, why would people want a machine like the sort that this conference is talking about? So you might say, why are you even asking that? It's so obvious, obviously. Well, I can tell you now, it is not at all obvious. I've spent half my life now talking to people about either using or investing in technologies like this. And I am here to tell you, it is not at all obvious that people want machines that have the properties that we're discussing now. And I would include basically all of the variants. Like we may have disagreements about what constitutes general intelligence or what flavor of it we might care to think about. Just like in the animal kingdom, you can imagine in the technium, there are untold millions of different kinds of thing we might consider general intelligence. So of all of those, are there any that people actually want? So here's 3 obvious examples. One of them is the statistics of language, the broken mirror held up to the Reddit posts. There's reinforcement learning in the digital world, and maybe more broadly than that. Here's another variant, which is some work by NVIDIA on building control systems for robots. Maybe this is something that you might consider to be generally intelligent or on its way. So no matter what you think about which branch of this technology spectrum you care to imagine is correlated with this thing that you really care about and have devoted your lives to building or thinking about, my view is that if you want it to actually come to pass, you have to imagine a parallel thing, which I'll call an economic driver, that is not the thing you want, but it generates and requires it. So let me go back to the quantum computing example. Quantum computers by themselves have no value. And that is very hard for a lot of people to understand. Is if I just build a machine and it is a quantum computer, the value of that thing in the sense of, a technology that will survive through time is 0. The value of the machine is what value it brings to people. Technologies are not independent from the people. People are the vectors of the procreation of the technology. You have to build something that people need or want. So in my language that I'm going to use, I'm going to call that an economic driver. So there's a very important point, maybe obvious, maybe not, that when you think about even something as so obviously valuable as general intelligence, it does not and cannot arise by itself. It needs to arise in tandem with the technology that evolves like every other technology, subject to selection pressure from people. So what is the economic driver for general intelligence? This is, I think, a core question, and it's a very hard one to answer. So I'm going to show you one potential way to think about this. Of course, it's not the only one, but it's the one that I've kind of put my weight behind. Right. So yeah, a question that has been asked several times, and Gary asked it too, is why don't we have this problem solved yet? And I think that the reason is that the economic drivers of general intelligence haven't been determined yet. So here's what I think. I think labor is the thing that's going to drive general intelligence into the world. And the reason is that there is an absolute critical lack of labor now in the world. And there are 2 kind of types of reason. One of them, which are the more powerful forces, are long-term acting forces that have to do with human demographics. Population birth rates have been below replacement in the Western world for 50 years. This is an amazing thing that I realized recently when I was studying some of these underlying things, is that people are not having children anymore in the Western world, or at least not enough to replace the numbers. And we don't see it yet in global population statistics because the less wealthy countries still have a lot more than replacement birth, but that number is plummeting also and will continue to plummet as technology picks up. We also have these short range forces that have to do with COVID and the disruption that's come from it, that have driven catastrophic numbers of unfilled positions in the labor market. If you read the news virtually every day, there's something about how people are not wanting to work under the conditions that historically have been the ones that were expected in terms of wages and the kinds of jobs that are done. And this number is huge. 10 million unfilled positions in the US alone. I mean, that's almost half of the workforce of Canada. It's a big number. So I'm going to show you one kind of robot that might be able to do some kinds of work. And this is what we call a general purpose robot, or at least that's the intent. Usually with robotic systems, the dogma is you build a robot to solve a particular problem. You specify a problem and you build something that is a solution to that problem. That's not this. Here, the optimization function, if you'd like, is fidelity to the human form. We wanted to try to build something that could do physically what people could do. And a lot of the problem with that comes from the hands. So robots are quite good at a lot of different kinds of things. Manual dexterity is not one of them. So usually robots are limited to what you can do with pinchers or suction cups on the end of their end effectors. Building human-like hands is a very difficult problem that we've kind of taken on head first. So at least on the robotics side of the projects that we've been working on, the hands are a significant portion of the problem. Now, of course, just building a robot that can kind of move around like a person is not enough. If you wanted to build an integrated system that could do work, and by which I mean nearly all work, the actual market for robots is tiny. The market for labor is enormous, and the difference is largely down to hands and cognition. So if you wanted to build a robot that could think like a person enough to be able to do work in kind of writ generally, you have to sort of think about this problem in stages, because obviously we don't have anything like the software, the control systems that would drive a robot like this yet. They're far too complex to be able to do this. So what do you do? Well, in autonomous driving, there was a clever thing done where there was a gradation scale between a person drives the car on the left and the car is just a dumb piece of plastic and metal, just responding to the agency of the person. And on the right, the car does everything. And there's a bunch of stuff in the middle. You don't go from one to the other. So for automating labor, and this is true for all robots, you can start from a perspective where there's a thing that I'm going to show you shortly, which is called analogous teleoperation, which is basically a person driving a robot just like you drive a car. And then there are a bunch of ways that you can increase the automation of the system all the way to a full automation system where you can imagine that the control system running in the robot is human-like in some way, or human-like enough to be able to do the kinds of work that we'd want robots to be able to do. So this idea is in a way that's analogous to autonomous driving is autonomous labor. So autonomous driving, we all know what that is or what it could be. Autonomous labor is just the analogous problem where you change the machine from a car to a robot, and the problem is not just driving, but being able to do work in a bunch of different contexts. So the control types that I'm largely going to be showing you, not all of them, but most of them, are of this sort. So when I say baseline level 0 autonomy, or the analogy of driving a car, this is what I'm talking about. So you have a robot, it's loaded up with whatever senses you can imagine putting on a robot, like vision, point clouds, audio, proprioception, touch, the whole business, just load it up with whatever you like. And you stream those senses over the internet or any network to a person, and the person receives the senses in an analogous way. So in this case, Suzanne's got a headset on that's receiving the visual feed from the cameras, potentially with some augmentations. And when she moves, those actions are transmitted in an analogous way to the robot. So part of the reason why you want a robot that kind of looks like a person like this is that it makes this kind of control simpler, because you don't have a hard problem of mapping degrees of freedom. It's just this person moves and the robot moves. If the person moves their head, the robot moves their head. It's basically a trivial control problem, just a one-to-one map. So this level 0 autonomy is very important. Like often I think there's a disdain for teleop that kind of lurks below the surface of a lot of roboticists and AGI folks. That is absolutely misplaced. I think you cannot get to where you want to go unless you can do this for a variety of reasons. The human mind is what I'll think of as a gold star controller for machines. There's never been a control system for a machine that's ever been built that's even remotely in the ballpark of what a person can do through a robot. So I'll just show you some examples of this kind of baseline control where remember, this is a person driving the robot. So far, there's no autonomy or anything. This is just a person moving a sophisticated robot around doing sophisticated tasks. So one of the things I'd kind of report on here is that this worked a lot better than we thought it would. So this is the 5th generation of this robot, and 5 generations of a complex machine is not a lot. You know, typically at D-Wave, we would do 7 revisions of everything before we'd even call it like a revision. This is just the 5th of the physical robot in the teleop system. And already it's doing things that you simply can't do with any other technology under teleop, of course. So it can manipulate small parts, rotate them. Everything here is in the wild. Obviously, you don't need to worry about lighting conditions or what you're dealing with or anything. If the system is physically capable of doing it, a person is going to be able to figure out how it's doing it. Every week we do these kinds of tests, and I'll show you why in a minute. And every week I'm kind of astounded by how capable this thing is under teleoperation. So here kind of is how we think about what it means to build something with general intelligence. And of course, there are lots of different ways to think about this. I'm not saying this is the right one or the only one or any of that. It's just the way that we think about it. We want to build a thing, a technological artifact that can physically and cognitively is able to do work, in the sense that I could take a regular person and plop them down, and I would have some expectations about what they would be able to do. I would want this robot to be able to do the same things. And that involves having conversations, it involves scene understanding, it involves reasoning, it involves goals, the whole lot. So this, of course, is kind of can be made fairly specific, but maybe at the cost of being very hard. I don't think there's a way around that. All of these formulations that we talk about are all very difficult to build. But here's what this one boils down to. It divides into two pieces. One of them is, can you build the robot itself? So that's the stuff, the atoms from which the machine is built, that is physically capable of doing work. And that is a very hard engineering problem. I would call it a grand challenge engineering problem. And then the second part is, can you build a software system that controls the body that you can't tell from a human pilot? So this is important. This is kind of how we position the problem that we're trying to solve, is that in the cases that I've showed you and some that I'll show you shortly, there's a person driving the robot. What we want to be able to do is build software systems that you can't tell are not people driving the robot. So you might flash to the Turing test. I suppose this is kind of related to that. But for work, we want to be able to have robots that can autonomously do work the same way that a human pilot would. And of course, this engages all of the problems that Gary was talking about and many more, because this is not just a problem about cognitive science and cognitive architectures, but it's also a problem about the physics and the engineering of robotic systems and how to get them to move the way that you want, which is by itself an entire field of human knowledge. I just wanted to point out that the far right hand of this kind of an analogy to autonomous driving is a very interesting endpoint. So if you can build a system that is completely autonomous and can do any work task that you ask it, that thing, regardless of kind of the words that we associate with it, is a very interesting thing that changes the world in all sorts of different ways. So there's a good question that you can ask about why is it that human-like cognition might be a target? And I'm asked this a lot more than you'd expect, because obviously there's lots of different ways to think about general intelligence or even narrow AI or technology at all. Why build this kind of technology? Why is this so important? And again, this is both trivially obvious and maybe kind of deep. So human-like cognition, of course, is not the best thing that you could imagine in terms of solving every problem there is, but it's got this peculiar feature that all of our ideas live inside of it. So if I'm Ilya and I dream up GPT-3, that was a human mind that did that, or a collection of them. And so, David Silver and Demis and the rest of those guys dreamt up all of this stuff. And the guys at NVIDIA, Nathan and others, dreamt up these control algorithms, and Suzanne at Kindred and now here is dreaming things up also. And I think that the reason why human-like cognition might be important from like a scientific perspective is that you imagine that if you do it right, the human mind can create an artifact that is kind of, let's say, deep enough to hold all of the ideas that we have about other ways to build AIs. So if this thing inside is a close enough replica of the thing outside, and we can put that into the world as being the brain of a robot or some other system, presumably that will have all of the necessary ingredients to be able to think about all of these other things as well. Whereas I don't think that's true for any of the other proposals that have been put forward. So anything that's like practically built or is being considered, it's very difficult to imagine that it would have the horsepower to be able to dream up all of these other things. And I think that even aside from that, there's a very human reason to build human-like cognition. It's basically everything we are, all of our dreams, emotions, memories, feelings, the way that we frame the world around us, why we think there's a tree over there when we look at it. All of that starts and ends within our minds. And I think that's a very fundamentally human thing to try to understand how that works. Okay, so lastly, I'm going to talk a little bit about how we go about this problem, not in any technical detail, but kind of give you a flavor for the approach that you need to follow when you build a control system for a robot. So the first thing is that there's a decision that we made to give the pilots and the AI the exact same data feeds in and out. So what that means is that the human pilot who is looking at the world or touching the world and then moving the world is using the exact same data channels as an autonomous agent would. So the AI doesn't get access to a whole bunch of stuff that the pilot doesn't, and vice versa. There's nothing that the pilot gets that the AI doesn't get, and vice versa. So there's an equivalence between these two control systems, exact same interface, and also critically the exact same job. We don't ask the AI to do something that a person can't do or you wouldn't expect a person to be able to do through this interface. So that's the first thing. The second thing is that we, for a variety of reasons that I'm sure all of you who've worked on robotics will appreciate, we need to be able to have a thing which we'll call a simulated robot in a simulated world. Just having physical robots and control systems isn't good enough for what we want. So I'm going to show you this. There's supposed to be audio that comes through. So if the audio doesn't come through, just let me know. So what I'm going to show you here is this is a physical robot. That's like a dude that lives in the real world. Back here is a simulated robot in a simulated world that's meant to be a one-to-one digital replica of this, not in the sense of being like what people usually call a digital twin, but an actual physical simulation, like with physics and all that. And the pilot here is going to move both in tandem. So this is just a mirroring exercise where the signals coming from the pilot get mirrored between the two. Okay, here goes. Let's pray for audio.
Okay, can you point at the yellow brick? Can you point at the orange brick? Can you point at the purple brick? Okay, can you push the yellow brick forward with one finger a little bit? Like away from you? Yeah. Nice. It's good.
Okay, so cool stuff. The physical world and the simulated world are kind of in lockstep. So there's this is not perfect by any means, but I have to say that NVIDIA and Facebook and the rest of you guys who are working on all this metaverse stuff, thank you kindly. You're doing yeoman's work. These digital worlds are getting much, much, much better. And the robot simulations that you can make now are much more lifelike. And this is helping this kind of thing quite a bit.
Okay.
Now, just as an aside, you can do these local scale things where you've got like objects, and you can see in the back there that the digital world has the same kinds of objects, and you can imagine that the visual reactions to them are the same. So if the digital robot looks at these things, they'll actually see them and all of that. But you can also do cool stuff with much larger scale environments. So you could build a house, you could build a store. So for example, here's a store. You can imagine robots wheeling around inside these stores, interacting with things. So you can basically do a lot more than you could even kind of a year ago. The progress that's happened in these simulated environments is extraordinary. Now, of course, that's cool, but what we really want is a system that moves the robot. So everything I've showed you so far is piloted. So the way that we approach the problem is the standard, I suppose you could say, cognitive architecture, where you imagine the problem in its great majesty and horrible glory, and you try to divide it up into parts so that you can think about each of the parts separately, so you don't go crazy trying to think about the whole thing at once. And then you try to imagine who makes the best of these parts, and what and to what extent they fit within the overall cognitive architecture. So I'll show you a couple. The reason I picked this motion planning one is I was just lurking on Twitter, and I noticed that Francois did a tweet, which I thought was kind of weird, because he says he's looking for Riemannian geometry in TensorFlow, and it was exactly what he was looking for. And I was like, well, that's really weird for a couple of reasons. One, it's just inherently weird. But the other reason is that the way that we do motion planning, which is the problem of how do you move a robot through the world when you kind of know where you want to go, which is task planning, uses very geometric ideas. So in this little video I'll show, the way to think about the motion is that the robot moves on geodesics in a very high dimensional space, which is essentially the joint space representation of the robot. So this robot has about 60 degrees of freedom. So imagine there's a 60 dimensional space and you have to move the robot through that. The motion is like a geometric geodesic. And you can imagine that this black thing is a repulsion surface. So the robot doesn't want to go there, but it does want to go where the red balls are. And also it wants to look at the ball that's on the that's over there. So this is derives from advanced ideas about using geometric approaches to motion planning that NVIDIA have pioneered. NVIDIA is really firing hot on a lot of the underlying AGI problems. I'm very impressed with both what they're doing and how. So we've borrowed some of these ideas, and by the way, it's not Riemannian geometry anymore. It's what's called Finsler geometry for reasons that I won't go into. But it's even more complicated to understand and figure out. But once you do, then you've got this powerful tool of not running into things you don't want to run into, and being able to move the robot towards the accomplishment of tasks. Which you can think of as like places in 3 dimensions, 4 dimensions, I suppose, with time. Another thing I'd mention, because it ends up being an important part of what we do, and that's been mentioned a couple times already, is that we work with the psych folks, and they're great. And we've done our best to try to integrate what they're doing in terms of being able to understand that side of the world into this system. And have had quite a bit of luck doing it. So I just mention, if you're interested in hearing the latest update on Doug and what psych folks are up to, he did a Lex Friedman podcast recently, which was really good and highly recommended. All right, so getting near the last thing here is I'm going to just show you how we measure the AGI system. So on the right here is a way is this thing is now not being controlled by a person, it's being controlled by the autonomous system that I just described. And the way that we test these things is both in simulation and in reality. Just to parse what's going on here. So this robot has a visual perspective that you can see over here. So it's looking down, sees a bunch of things. And Suzanne can ask the robot to do physical tasks or to answer questions about scene understanding, or the affordance of objects, and all of these tests derive from a series of tests that were designed by economists to measure how fit for work a person is. So backing up a step, there's an entire field of science, I suppose, that is kind of related to psychometrics like IQ testing, where what you're testing is the ability of a person to do work, generally speaking, where the attempt is to reduce a person down to kind of atoms of work. Like, what are the sorts of things that you need to be able to do just work generally, not specific tasks, but any kinds of work. And so we adopted this metric, or at least created one from these tests, that resolves to a scalar. It's just a number. This number is a representation of a very high dimensional space, of course, so it's kind of a little bit weird, just like IQ is kind of a little bit weird. The things that it tests for is not really a number, but you can kind of boil it down to one if you squint. So what we do is we run all these tests and then we track progress. And the intent, or at least the the way that we hope this will proceed is that as you grow up this curve, you pass certain capabilities that these economists believe are required to do different kinds of work. So this physical system that I'm talking about needs to be able to do certain and be certain things in order to do work. It turns out that there's a very nonlinear relationship between those things and the amounts of work that you can do, which is kind of sensible if you think about it. Just basic human capability allows you to do an awful lot of different things in the economy. So as you climb this curve, you unlock different capabilities. And so instead of focusing on specific work tasks, although we do that too, we try to grow this number as kind of a measure of the progress against the goal. There are other things we measure as well, but I thought I'd point this one out because it's a very important type of thing. So I'm getting close to closing here. This is a couple more things I wanted to say. So the first one is that even though this problem is crushingly hard, and you guys know this more than most about how hard this problem is, I really do think that we're not so far away. Now, I know this has been said before. There's a long history of people thinking the problem was right around the corner. But I think that this time is different. And I think the reason is that we're already starting to see the signs of the sorts of things that we actually want already in the world. So the ability to physically manipulate objects, the ability to have sensor integration between, say, touch, proprioception, and vision and audio, the ability to hook in things where computers are obviously better, like chess, number theory, that sort of thing. They're already starting to work. So I think that there are maybe not machines just like us, like Data from Star Trek or something like that. Maybe that's not within reach, at least in the short term. But I think machines that are close enough so that you got to do a double take, or when you're having a conversation with it, you forget that it's not a person. That I think might be within reach within our lifetimes. And finally, I just wanted to close with a word about how I see the future. So I've been trying to work on things that would really change the world my whole life. It's not always clear that technologies are for the good. We've talked a little bit about some of the potential downsides of social media and things of that sort. But I have to say, even though I'm not generally, I wouldn't call myself really fundamentally an optimistic person. I think I'm more of a realist. I actually think now my point of view on where we're headed has turned a corner. I think that we are looking at least in the sort of far future, by which I mean, say 50 to 100 years, I think things are going to get a lot better. And partly, I think this is because this understanding how the human machine works is going to lead to a massive flourishing of awesomeness. So not only does understanding how our minds work unlock the ability to free people from the drudgery of work, but it gives us tremendous, and I think a kind of insight you can't get in any other way into how our minds actually work, which obviously is going to have a ton of positive implications. And if I was going to get really sci-fi, being able to build a machine that's kind of like a person might lead to being able to build a machine that's kind of like a specific person. And that starts to look a little bit like side loading. We talked about Greg Egan before, but being able to build a cognition has some really fundamental implications about human society. And I think that even though it's very difficult to predict how the future will pan out, I am very optimistic about the directions that we're going and where we're eventually going to end once we pass through a period of turbulence between now and then. All right, thanks very much.
Hi, thank you very much indeed, Jordy. That was absolutely fabulous. I'm Janet Adams. My mum wants to know when we'll have a robot that'll make her a gin and tonic. We can come to that at the end if we run out of time with questions. Thank you. So sorry, we missed the clap. We were on mute. Let's have a big clap for Jordy, please. That was an amazing talk. So first question I'm going to ask, I've got at least one question here in the room in Palo Alto, but we have a question on Zoom from Sudha that we would love to hear. Sudha, if you'd like to ask your question.
Yes, this was such a fantastic presentation. Thank you so much. I focus on value creation from data and teach about autonomous vehicles. So I like the comparison to the 5 levels of autonomy. But my question is focused on what you said as the economic driver that is going to get us to a general AI. So when we talk about general AI, it's always talked about as general for all humanity, not just for North America, or not just for the Western world. But when you talked about the economic driver, it postulates that it has to be within the confines of the nation state. And specifically, it was, the list that you showed was more Western world centered. So I'm wondering if we really can build a general AI and look at it as including the global South and the whole world, would that economic driver change?
So my perspective is that, and maybe this is related to that picture I showed with like all of the life on Earth, is that every human on the planet is basically identical. So I don't view that there's a lot of differentiation between people. I think the things that we share dramatically outnumber the things that we don't. And I think part of that comes from having to take on the challenge of building robots. So when you try to build a robot, you start to realize that how amazing it is that I can hold this thing up. And you immediately have a cascade of understanding in your mind, not only about what the semantics of this thing are, about its affordances and all of that. And you can do that if you're anybody in the world. And that is an amazing thing that ties us all together at a very fundamental level. So the particulars about what drives the economics of the adoption of robotics is path dependent. So for example, in our case, we would much prefer to have customers that are near us physically just for logistics reasons. So in the going from here to where we want to be, there are going to be specific choices made about what the work is, who the customers are, all that kind of thing. But my hope is that the end point is not path dependent, is that when we get through all of that, there's going to be a state which really wouldn't have depended on where it started. Is that if it started in India or it started here or it started in the US, all of those endpoints are kind of similar. Now that might be naive and maybe it's not even true, but it's kind of the way I think about it, is that the things that we share, which are the things that we're trying to replicate here, are not details. They're not what language we speak. They're not, what cultural values we hold or any of that. It's, can I understand that I'm looking at an apple and a person can eat it? Like that's the level I think we need to focus on. And most work is like that. Most of the world's economy works on people who do the same thing over and over again that just need some basic understanding of, what's going on. And robots should be doing that, not people. Doesn't matter where it is.
So the economic driver is going to be more short-term focused. And so maybe
it's the 10 million jobs in the US that people can't find people to do. That's the economic driver.
So
if there was an abundance of labor,
if
there was an abundance of labor, human labor, this would not be a good idea because it just wouldn't make sense, because it's very expensive and difficult to build robots that do work. The thing that makes this work is that the fundamental fabric that holds together human civilization is a bunch of drudgery that no one wants to do. And so we have the technology and the capability to build an automated system that basically takes care of all of that so that people can be free to do other things. And it's not that, jobs are going to be lost. That's not the way this is going to work. The way it's going to work is that the first 10 million robots Sanctuary sells are going to be into the 10 million jobs that no one wants to do. And 10 million robots and making, 100, 200K a year is a very big business that is an economic driver sufficiently of scale to get to AGI. Maybe one of the things that I didn't make explicit is that when I say economic driver, I mean like civilization level economic driver.
Yeah.
It's not enough to build like a small product. You need to have something that people like with a capital P, people want and need, I think, because it's going to be really expensive. It's going to take a long time. I mentioned like we've done 5 revs of the robot. The robot that would actually be doing real work is going to be, rev 50. So that's going to take a long time and a lot of capital to develop. There has to be a very good reason to do it. And I think one of the things that I've learned from my life of sitting on this boundary between science and the real world being, the economics and engines of capitalism, all that, is that it's very easy to miss that modern science is not the same as it was back in Newton's time. You can't have the ex machina scenario where there's some random genius in a basement somewhere creating an AGI. That doesn't work. AGI is a community effort that requires thousands of people and entire swaths of human knowledge to even have a chance. So what's going to coordinate that activity? It's something that has to be of civilization level importance. And I think labor is clearly one of those things. It's the biggest market in the world. And so if you can build a system that can actually do work, and I don't mean conventional robots as they are now, because they're good at some things, but it's not what I'm talking about. If you can build an actual robot that can understand the world the same way an animal would, and then make it, make it have the ability to do the stuff that holds civilization together, you're driving AGI, because those machines they get better in the sense of being economically better. They do better and they cost less, the better the system is that runs in them. So as this software system that powers their behavior gets what you could think of as smarter, the economics improve. So this alignment between a scientific mission and a business mission is very difficult to find in AGI. I was very surprised at how generally people don't value or understand the value of specifically human-like intelligence in the development of products. This is kind of weird, I suppose, but I think it's partly that people don't believe it's possible, partly that they think it's a long way away and so on. But in this case, I think that's our strategy is you gradually increase the capability of the underlying autonomy and you connect it to an economic driver, which is a big one.
So do you see that there is going to be parallel effort? Like here, I'm from Bay Area, so I'm also biased towards delivery robots and wish they could have the dexterity of the hand. But do you think there is going to be multiple groups of people who are building this robot for different markets within nations? So maybe there's a group in China doing something in the global south, something here in the Western world. And then that funds enough.
So my view of technology is that technology parallels biological evolution. So in biological evolution, you have a selection mechanism, which is, survival until you reproduce. And all of the things that are around now have done that for 1 billion years or more. Technology has a fitness function, which depends on people wanting it around. That's the selection pressure on technology. And just like human-like intelligence is not a guided thing in evolution, evolution doesn't proceed in a linear fashion towards the kind of intelligence we have. General intelligence of any flavor or any kind of technology is not guaranteed as a process of technological evolution. They happen because there's a fitness function and pressures on it. So as intelligent designers, if I might refer to us as that, we have to figure out how to align our scientific views of what should be built or should be understood with the practical realities that you need to build something that people want. Now, do people want delivery robots with pinchers? I think if they do, someone will build it. And what I would hope is that there's a Cambrian explosion of machines, all with different control systems, like different intelligences, and they all do stuff, and they're all cool. They're all different. We could all argue about what general intelligence means in that scenario, but I think that would be a very beautiful world to be in, to share the world with this explosion of new kinds of things that sense the world and act in it and all have their own different niches and so on. But remember, they don't evolve the same way rats and cabbits and squirrels and dogs do. They evolve because people want them. So when you come up with your idea about a product, you have to first ask the question, why in the hell would anybody want this thing? So it's an important thing, right? GPT-3, why in the hell would anybody want that? You know, is there an answer? That has to be the first thing you ask. So, you know, of course there's science and it proceeds in different directions and, you know, takes its own course. But from the technology perspective, you have to start with the question about why would somebody want this thing?
Thank you.
Yes, thank you for your talk. This is Peter Voss. I'd like you to expand a little bit on what you understand the difference between narrow AI and really AGI, general cognitive capability, because it wasn't quite clear to me. Sometimes you called something that's clearly narrow AI, you called it AGI. So what do you see the difference between narrow AI and AGI? And then the sort of follow-up question is, once we get to human level cognitive ability, where do you see the singularity fitting in? Do you see those AIs and being able to improve themselves very rapidly?
So there are components of an architecture inside a robotic control system that are clearly special purpose modules, like, for example, bounding boxes around objects that help you determine where a thing is. But the system itself is constructed to attempt to generalize over these kinds of narrow things. So I would think that the way to think about any system that runs in a robot of the sort that we're talking about is composed of a bunch of things that have specific objectives, like feature detectors and so on. But the sum total of them, the architecture of the whole thing, is intended to generalize. And now when you ask, what does that really mean? It's always in the frame of, can it do what a human pilot would do in the same situation in the same way? So if I have a person piloting a robot and I ask it to put all the red blocks in a bin, I want the AI system to be able to respond the same way and get the same job done, no matter what I ask. So if I ask you to like fly the helicopter or put the red things in the bin or translate this from Hindi to Arabic or whatever I might ask a person to do, I want the AI system to be able to do it. So that's what I mean by the generalization. And that's the intent of trying to be very specific about what the objective of the problem that our framing is that we frame the problem to be the creation of a software system that, when receiving the streams of data from the robot and injecting back the motion commands into the robot, you cannot tell is not a human pilot doing that thing that I showed, the analogous teleoperation. That's a definitional thing for us. Now you might argue against it, but that's just the way we think about it. That question about the singularity. So I have trouble thinking about that word, and maybe it's because I did too much general relativity, but I don't think I believe it. I think that the way that this will happen in practice is that you will get this Cambrian explosion. There's going to be all sorts of new technologies all over the place, things that look like statistical things like GPT-3 and reinforcement learning things like the protein folding thing and robots and the rest of it. There's just going to be thousands and thousands and thousands of them, all with different properties. I think this singularity thing for me has a conceptual problem at its heart, that intelligence is not like a scalar. It's not a thing with a number that gets better and better and better. It's a very complex thing that has to do with the ability to achieve goals in a specific environment. And I don't believe that that is an unbounded thing ever. You're always bounded in your ability to achieve goals by the laws of physics. The laws of physics preclude you from predicting outcomes of actions past, a few seconds in some, or even less in some cases with chaotic systems. There are just fundamental limits to what any sentience can think about or do. So I don't buy that. I think that what happens is, for any particular niche, there is an S thing that happens where you flatten out, you become the best that you can be at whatever you're doing, more or less. And that will happen with all of these different things. And I don't believe in this idea of singularity and self-improving AI and all of that. I think it's a theoretical, mathematical idea that doesn't hold water in the physical world, is my view.
Thank you for your view.
Thanks so much indeed. So here in the room, we've overrun a little. It's 5 to 1. We've got 3 online questions, and we've got a couple of people on Zoom want to chat. So, Jordy, if you're okay to carry on, we can take some more questions.
Sure, I'll try to be more concise in my answers.
Sorry, what
it's
was
just
that?
such a fascinating. I'll try to be more concise in my answers, but it's just such a fascinating crowd. I don't get to meet a lot of these people ever, locked away in my dungeon in Vancouver. So, by the way, Peter, it's very nice to meet you. I don't think we've ever spoken in person, but I've read a lot of the stuff that you've written.
Yeah, no need to be concise at all, Jordy, if you're okay. It is eating into anyone in the room who's particularly hungry their time, but I think online and the rest of us were really happy to keep going, if that's okay with everyone. Yeah. All righty, we'll keep going. Thank you. So any more questions from the IRL humans in the room before we cut to the online questions? We have one from Gabriel.
Hey, Jordy.
Hey.
Excellent, fascinating talk. Nice to meet you. My name is Gabriel. Just a quick question, just kind of maybe one level before the argument you started making about the needing an economic driver to build AGI and to drive it. I'm just wondering, just a question for general reflection. Do you think that requiring an economic driver could in any way inhibit the build out of beneficial AGI, meaning if economic drivers are the thing that we're depending on to build a general intelligence, could that inhibit the development of a beneficial AGI?
That is an excellent question. Let me not answer it, but instead give you a perspective that's kind of parallel to it. There's a school of thought in economics that the economic forces parallel human desires. So you buy things because you need or want them. And the amount that you spend is an indicator of your desire for whatever that thing is, okay? If you believe that, then economic forces are simply a measure of the desires of people. So if you ask the question, should I build something that people want, and parallel something that will do well as a product? If you ask the question whether that is an inhibitory thing to AGI, you're on a very difficult trajectory, because what you're essentially saying is that you know better than people what's good for them. And well, it might be true that in certain cases there are people who might know better than the general consensus about what's good for them. I think it's a dangerous perspective that I don't share. So for me, I think that the indicator of what people want is what they buy. Now, that sounds maybe a little dry and kind of like inhuman, but if you think about the underlying reality of like, why do people spend money on anything?
Air, Jordy?
What's that?
How much do you pay for your air?
How much did you pay for your wife?
What about the tobacco industry?
So I hear your point.
All of those points are fine and good, and please don't kill the messenger. I'm just echoing what the world's economists believe, or at least some of them. But I guess the fundamental question, which is a hard one, is should we try to build something that people want or not? And if the question is not, what makes you so sure that your judgment is better than the judgment of the economic forces at work? And I think that there's a lot, especially on the left and especially from academics, of this inherent belief that they know better than everyone else and they should be making the decisions. And that's a very dangerous thing, regardless of your political affiliation. I think that my preference is to ask the question, what do people really want, and give it to them, trusting that the answer that you're going to get back is honest. So in my case, I have a long line of people who are telling me they can't run their operations because they can't hire people. So they're expressing a desire to have machines that do things that they can't hire people for. So I trust that they're telling me the truth. And I also trust that the things that they're doing are desirable and good. Like, for example, the small business down the road that's going to close because they can't hire servers is a social good, because people go there and they buy pizza, and people like pizza and they like going to places. So these kinds of, I don't hold with kind of like these anti-capitalistic kind of tendencies that people sometimes show, where, you know, economies are bad and, you know, people don't know what they're doing and all of this. I don't believe that at all. I think that in the main, the consensus opinions about economics actually work quite well. They don't work always, but I think that they're the right thing to think through when you're thinking about building technologies.
Thanks for the response. I think when you mention an economic driver, then going from there to robotics, I think is fascinating. I also, if we were to take a step back, and the arguments in favor of a fully free market, and, you know, economic actors making their decisions rationally and based on their actual desires, I think that we're underestimating the role of conditioning and mass influence on that. And if we want to take a step further out, we're dealing with matters like existential risk. So this free market approach has gotten us to a climate crisis. Even if we say, well, let's maybe consider non-human factors in the climate change as well, I still think that there are certain issues with that. And the same thing with existential risk due to AGI. So I would take a both-and approach. I think that the economic driver aspect is very key to examine, because we want to maximize chances of success for AGI. But this also feeds right into the centralization, decentralization debate. And I'm sure Ben has something to say about this.
Actually, what I was aiming to do is redirect things away from politics and economics back to AGI. As tempting as it would be to advocate for anarcho-socialism and have a politics debate with Jordy, this isn't probably not the right context to do that. These are deep, complicated things in themselves. I wanted to come back to something you said in response to an earlier question, not so much about the singularity, which is a broad notion involving the evolution of all human society and so on, but about self-improving, self-modifying AGI, which is one part of the singularity, which is sort of closer to the technical matter of building AGI systems. Because I guess I feel like I can see a clear technical path to making a self-improving, self-modifying AGI that's like learns to program, learns hardware engineering, rewrites its own code to improve itself, even redesigns its own hardware. And I'm curious if you think that sort of self-modifying AI, like an AI that starts out as smart as you or me, let's say, and then learns computer science and improves its algorithms and improves its brain and then gets smarter and smarter. So that's what you would call an intelligence explosion, which is not necessarily the exact same thing as a technological singularity. But I'm wondering if you think that's implausible, and if so, why? Like setting aside the social aspects of singularity.
Yeah, I mean, I would put it in the same category as any technology. It is not precluded by the laws of physics, as far as I can tell. You could build a thing like that and see how it works. And again, it will survive, or it will thrive or die, again, based on the same social pressures that all technologies do. Now, the question about what it could become, I think we might debate. You know, I have some pretty strong views about limits to capabilities that derive from the laws of physics that come from my time in quantum computing and also just being a physicist, I suppose. You know, the first thing you learn is that there are limits to everything in physics that are fundamental.
Do you think humans are close to the maximum limits in terms of, say, cognition?
Well, we're very good at what we do. That is the thing that is kind of our niche. Think things like visual perception and building models of the world were pretty good, I think.
How about mathematical theorem proving as an example?
Well, no, that would be an example where we're not. So I think that anything that's kind of rooted in the African savanna and survival, we're pretty damn good. You know, it's hard to build a machine like us. For certain things that are kind of derived notions that somehow piggybacked on all of that, like theorem proving and all that, no, we're not the right tool for the job.
Or say engineering new forms of degenerate matter, let's say.
Well, again, I think that there are certain things that we're exceptional at and some that aren't. You know, I think that this idea that humans are a low bar, which I guess Danny Kahneman threw Gary Marcus, I don't believe that at all. You know, I know that Ben, you've kind of made a similar point that we're kind of like the stupidest possible thing that could ask the question about how we work. I don't know if I believe that, because I kind of have a different perspective on what cognition is that, again, is flavored from all my years as physicist and roboticist now. That I think of everything in terms of embodiment in the physical world, and in terms of our ability to deal with the physical world, we're champions. Like, we're really good at it in ways that I think it's not well understood even today, you know. So all of this other stuff, which is kind of like the mental arithmetic and the gymnastics that we make when we think about abstract things, yeah, maybe we're not so good at it. But I would ask the question, is it actually necessary for anything? You know, and that might be a heretical question that might cause everybody to shock and gasp.
Is it necessary to mind upload into a quark gluon plasma? I mean, it's not necessary, but an AGI might be better at it than you are, right? So.
Yeah, maybe. But I have trouble thinking about that because I don't know why it matters to me or you, because it's so far in the future, if it ever happens, that it won't be anything like us doing that kind of decision making.
Yeah, why it matters to me is a psychological question we probably don't have time for. But yeah, I think Joshua has a question which we can take before breaking for lunch here in Palo Alto.
Yeah, I was just gonna ask him if he wasn't gonna bag on me for something. And here it comes. I know it's a.
Oh no, I'm not a libertarian myself, but I really liked how you bashed the academics who know better than everybody else what they want. But that's not really the point. I'm much more interested in the systems that you're building. Do you think it's crucial to go from Doug Lennox's work branching out until you meet the real world? Or do you think we should start with systems that are directly coupled to the world and learn in real time and update in real time, perceive in real time until they are able to have a connection to knowledge and abstractions?
So this is an absolutely terrific question. And I would say that it's absolutely not clear what the answer is. And let me just give you a kind of an anecdote. The first version of these cognitive architecture that we built had knowledge and reasoning as kind of a first-class citizen, where we tried to go from common sense reasoning down to the sensory side and kind of start there. And we decided, for reasons I won't get into, that that wasn't the right approach. And instead, what we should do is go the other way from what you could think of as like the right-brained kind of approach, which is this fast sensory motor kind of thing, and then layer on the reasoning on top. So I think that's wrong too. So this is a very fundamental and deep question. And I think that there is a kind of an impedance mismatch between the two styles of thought that hasn't been resolved yet on our side. So we don't yet know what the right way to deal with the integration of those two kinds of worldviews are. We've experimented with a bunch of things, but I don't think we know what the answer is yet, or even something that makes sense. Right now, it's basically a kludge.
All right. Thank you so much indeed. That was amazing. Let's have another huge, big round of applause for Jordy.
Thanks all.
Thanks, everyone. Thanks, all our watchers online. Thanks, our Zoom watchers. And we will see you all back here at 2 o'clock to continue with our last afternoon. Have a nice lunch. Bye. Thank you.
Come on. Come
You're gold.
Hello,
Rather be carbon.
You're not muted anymore.
Go ahead, Ben.
All right, are we live?
We are
Hey,
live.
welcome everyone to the afternoon session of the fourth and final day of AGI 2021. And I'm really pleased to announce our next keynote speaker, again, a multiple-time AGI conference offender, Dr. Paul Rosenblum, who has been around in the AI field probably, I guess, even longer than I have, which is a honor and a distinction since I'm getting old myself. And Paul was one of the founders and pioneers of the cognitive architecture approach to human level intelligence and AGI, which I believe has still a great deal to contribute to the process of building AGI systems, as well as the process of understanding the mind. Paul was involved with the SOAR cognitive architecture, and more recently with the Sigma architecture, which integrates some ideas from SOAR with ideas from probabilistic learning and other more recent innovations. He's also spearheaded the recent initiative to formulate a standard model of mind, systematizing many ideas from cognitive science, AI, neuroscience, and other areas. So he's done an awful lot of other interesting things that I'm not gonna take a really long time to recount, but we're certainly we're fortunate to have Paul sharing his views on the state of AGI and the next steps in AI and cognitive science. Let's hear it, Paul.
Okay, thanks, Ben. Can you hear me okay?
Yes.
Okay, great. My voice isn't the greatest these days, but hopefully I'll make it through the hour. Excuse me. So rather than being a talk about one particular path toward AGI, this talk looks at two complementary approaches to understanding general intelligence more broadly. In a sense, it's a summary of the analytical side of my cognitive career that in turn is a complement to the synthesis side that Ben mentioned of building the SOAR and Sigma architectures. So the perspective I'm taking here is on the notion of these two different approaches kind of map onto lumping and splitting in the traditional sense, which comes from Charles Darwin in biology in the context of taxonomies, was later propagated to other fields. Lumping basically assigns examples broadly to categories based on their signature similarities. Splitting is the opposite, assigning examples narrowly based on key differences and creating finer and finer categories as necessary to do so. So the plan of this talk is there are basically two halves. The lumping portion is a common model of cognition, which is what Ben just referred to as the standard model of the mind. I'll explain the confusion of terminology shortly. Here the focus is on signature similarities, and it's based on a consensus across cognitive architectures. The other approach does not want to change slides. The other approach has to do with mapping the fields of AI and cognitive science, as well as architectures for integrated intelligence of various sorts. Here the focus on key differences. We're going to look at a quartet of dichotomies that underlie this, that help get a feel for the scope, similarities and differences and combinations across underlying technologies in these fields and systems. So I'm having trouble getting this to change slides appropriately. Okay, so
perhaps
this slide is
perhaps it helps if it's not in full screen view. And then you just use your down arrow.
And you just go here?
Yeah, and just use your down arrow to switch, yeah.
I'll give that a try. Okay, well then it's not going to do the animation, so let me still try that, because there are some slides that won't make sense otherwise. Okay, so I mean, this is sort of general background. There are multiple approaches to understanding minds. AI and AGI basically care about building minds and therefore look into how such minds can be built. Cognitive science concerns how you model natural minds, cares therefore mostly for understanding human cognitive processes. Neuroscience, it's about the structure and function of brains, so cares how minds arise from brains. And robotics concerns about controlling artificial bodies, and so it cares about how minds do those kinds of things. There's a deep scientific question, though, as to whether they're going to converge on a single understanding of mind, kind of denoted abstractly by this curve. We know it must happen for at least cognitive science and neuroscience because they're both studying the same thing, that is the human brain-mind combination. It may also happen for naturally inspired AI and robotics if the class is slightly abstracted, so it's not just looking at humans. And it may even happen for other systems for functional reasons. So they may have the same kinds of mechanisms, even though they're not deliberately in any sense trying to be either inspired by or modeling humans. So in a sense, what we're looking at here is a conjunctive class of architectures, where we can talk about a single set of mechanisms working across all of them. We're going to call this slightly abstracted class human-like minds. It's broader than naturally inspired minds because it includes artificial systems as well, but narrower than human-level intelligence because it's not all approaches to yielding human-level intelligence. What we're trying to do, you can think of an analogy to the standard model of particle physics. That model is an integrative model, combines electromagnetic, weak and strong interactions, classifies all the known elementary particles in kind of like the figure here, and it's a community consensus developed over decades. Assumed to be internally consistent, but it may have gaps. Yields critical functionality for things like providing a cumulative reference point for progress and guiding efforts to extend and break it. With the common law of cognition, what we're trying to do is pool the community's expertise to see where the consensus lies on human-like minds. The approach is not to force a consensus where it doesn't exist, but also not require unanimity. But we are trying to dig deep to see if there might be a hidden consensus, even when on the surface things look quite different. We started with a fairly small community, but the intent is to continually grow and be willing to rethink the model as necessary as the community grows and as more results come in. And to leverage abstraction and incompleteness for this, so we're not looking for a necessarily complete and implementable model. This is not an attempt to build another architecture of a particular sort. It's intended to be more abstract than that. All right, a brief history of the effort. So it grew out of a summary presentation Christian Levier gave at a 2013 AAI Fall Symposium on Integrated Cognition, where he proposed the idea of a standard model of the mind and gave a few things he had seen during that symposium that he thought might be part of it. The thing that really kind of shocked us was that everyone in the room at the time, who came from many different areas, AI, AGI, cognitive science, robotics, neuroscience, they all agreed it was a reasonable consensus. And that gave us the idea that maybe it was time in the field to see if we could build on that to build something more substantial. Three of us, Christian, John Laird, and myself, pursued that, looking primarily at ACT-R, SOAR, and Sigma, but somewhat more broadly as well, with a paper that appeared in AI Magazine on the standard model of the mind. And then we began to grow it into a more of a community effort. We held 2 additional AAI Fall Symposia on the topic, at which there was an agreement from the set of folks there about the proposed consensus, created a mailing list that now has 270 members. The biggest disagreement, it turned out, at the first symposium was about the name of the effort. There were folks who thought the standard model was too aggressive terminology, thinking about the issues that standard theory had yielded in linguistics. So we actually held a community poll. It was a multi-stage poll, and we ended up with the common model of cognition as the name for what we were doing. So the initial structure of the common model is pretty simple. It's a set of communicating modules. There are 2 long-term memories for skills and facts. There's a working memory, which is for global communication. You can think of like a global workspace or a Blackboard, things like that to some extent. And then there are also perception and motor modules. There's global communication through working memory, plus a local perception motor link. The procedural long-term memory can access all of working memory. The other modules only access buffers within the working memory. Sorry, this is going to be a problem all the way through, I guess. There are also 16 additional assumptions, which were in the original paper, which I'll go through briefly. And they're divided up into 4 areas: structure and processing, memory and content, learning, and then perception and motor. I'm going to skip perception and motor because the common model really doesn't have much of interest to say about those, mostly because the 3 architectures we largely base this on don't really have anything interesting to say about those areas either. So that just points to an area where much more work is required, not that the common model is saying that those areas are not interesting. So let's briefly go through these and also skip over by graying out things that have already been implied by that initial slide. So in structure and processing, processing yields bounded rationality, not optimality. This goes back to Herb Simon and others. There's significant parallelism both within and across modules. Though there is sequential action, the selection of actions in a cognitive cycle that runs in about 50 milliseconds per cycle in people. So there's a combination of extensive parallelism, but also with the serial cycle imposed upon it as well. Complex behavior then arises from sequences of cognitive cycles. There aren't additional, more complex mechanisms like planning modules or things like that. In terms of memory and content, the memories are hybrid. They're symbolic data plus quantitative metadata. So we have these data metadata dyads. The symbolic has a star after it because it's a somewhat weakened notion from the standard one that you'll know of kind of from papers by Newell and Simon and others. And in my own work, I've weakened that notion even further. But you can think of it as roughly traditional symbolic data with then numbers attached to it, which have various kinds of implications. The procedural memory is composed of rule-like conditions and actions, though in some sense it's really broader than that, and exerts control by altering the contents of working memory. It's not directly performing motor actions. That happens through the buffer to the motor system through working memory. Learning, all forms of long-term memory are learnable. Learning occurs online and incrementally. We do not spend hours or days or weeks or months poring over a huge data set, creating something that is then used. It happens essentially as a side effect of performance in this model, and often based on an inversion of the flow of information from performance. So if you think of things like backpropagation and reinforcement learning and chunking, the learning mechanism is essentially a backward operation on what happens during performance. Procedural learning involves at least reinforcement learning and procedural composition, with the former providing essentially weights or guidance on action selection, and the latter providing behavioral optimization. Declarative learning acquires facts and tunes their metadata. And again, more complex forms of learning involve combinations of simpler forms. So there isn't, again, more large-scale learning mechanisms. If we take a look, skipped over slides. There we go. So if we take a look at Actar, SOAR, and Sigma, these are kind of traditional diagrams for each of them. They look pretty different in this, although Sigma is perhaps more different because it's basically one large graph that through specialization and combination yields different kinds of modules. But the various parts are color-coded according to the parts of the common model. So you can start to see parts that are intended to correspond, but still the correspondence is pretty tough because these figures are all so different. But if we use the common model to actually analyze those architectures in more detail, what we can see is that initially, at least back in 1993, both SOAR and Actar differed from the common model fairly extensively. That's the red squares, and to some extent the blue ones. They also differed strongly from each other. You see the red squares are in different places. The A's, B's, C's, and D's are these different categories of assumptions. So there was a lot of discordance at that point. However, when we wrote the paper, this is what Actar and SOAR looked like. So they completely agreed basically with the common model. They just didn't have everything completely implemented. That's what the later green things are denoted. And so they agreed with themselves and with the model. Sigma, which is somewhat newer, has a number of places where it says things are built out of the combination of architecture and knowledge rather than being purely architectural modules. So that's the blue things. And more of it's not implemented yet because it's been around less. So we can see the convergence that's happened with respect to Actor and SOAR that has helped in creating things like the common model. The number of potential benefits of developing a common model of cognition. One is providing a coherent baseline to facilitate shared cumulative progress. It can provide a target for challenging the consensus, a way of organizing the data that's can be used for evaluating cognitive architectures and AI and AGI architectures, an interlingua for comparing such architectures. It can provide guidance in adding components to existing systems, like if you want to add memory to a deep learning system, or for identifying relevant experiments for determining key factors, or even developing applications. I'm going to next give you a brief tour of some of what's happened since the initial work on 3 of these topics, since we've seen some progress. I'll start with challenging the consensus, and there's been a lot of work here, unsurprisingly. It's kind of organized by how many different papers have been published that try to challenge it in various ways. So the biggest challenge has been the area of knowledge representation, including ontology, concepts, and world knowledge. Some of that has been general challenges. Others have been specific in terms of the common model ought to have this kind of memory. And so you see some of the kinds of things there that people are proposed. Affect, emotion, and feeling are completely absent at this point. So is social cognition, spatial cognition, reasoning, and mental imagery. Decision-making and action selection, including, again, a couple of specializations of that. Formalization, rigor, and mathematical physical foundations. Metacognition and reflection. Natural language, analogy, attention. There's no body, so there's no physiology or interaction with others. Consciousness, continuous and neural representations and processing. Inference in the classical, more logical sense. Multiple layers of the architecture and macrocognition, which goes above the architecture in various ways. Relationship to brain architecture, evolutionary considerations, generalization, interspeech, robotics. So you can see it's clear there's a bunch of stuff missing. So we're fine with that in the sense that common model is not complete. And so all of this is helping us to understand where the gaps are and hopefully pointing to the kinds of, at least the areas in which we should be seeking additional consensus or determining that it's not yet ready for consensus. That's always a possibility. I'm going to talk a little bit more now about this particular one because some of the most exciting work that's happened recently is actually relating the common model to high-level brain architecture. So this is not something we expected to happen when we started the work on the common model. So it's a surprise and very pleasant surprise that it actually has proved useful in exploring large-scale brain architecture. So it starts by mapping the modules in the common model onto functional circuits in the brain. There are fairly conventional techniques for doing that. I'm not an expert on that or any other part of this particular work. You can check with Andrea Stocco or our paper on this to see more details. Once you have that mapping, you can then compare the common model to more traditional architectures from neuroscience, like hub and spoke and hierarchical architectures. And if then you use the technique called dynamic causal modeling, you can apply that to, in this case, we applied to the data from 6 tasks from the Human Connectome project to yield a set of figures that look like this. So what is graphed here, it's for 6 different tasks, things like emotion processing, relational reasoning, social cognition, and so on. What you're seeing are exceedance probabilities, which are the probability that each of the different architectures dominates all the others. The pink one, unfortunately, is the common model, and you can see it's to the right of all the other models. In some cases, very far to the right. In the case of relational reasoning, not quite so far, but still to the right. And if you look down at G, all tasks combined, the probability is essentially 1 that the common model dominates all the others. So that's kind of a neat result. And Andrea and his team have been following up on that in a number of ways. So I encourage you to follow that if you're interested in this line of work. Back to the benefits side. So an interlingua for comparison. These are the ones I've been able to find so far by actually going to Google Scholar and finding all the papers that cited one of the standard model or cognitive or common model papers. And so we can see we're kind of 10 to 12 architectures plus a number of additional frameworks that have been mapped onto the common model in one way or another. In principle, this gives us a way of comparing those architectures directly as well through this common language of the common model, though I haven't seen as much of that happening yet. We're always encouraging more. If you work on an architecture or don't work on it, but are interested in an architecture and want to try to map it onto the common model, love to see what could be done there. So there are other nascent benefits. These first two are things we anticipated, but haven't made that much of a deal about so far. One is providing the baseline consensus. So there are a number of references to it as this explicitly, and also the proposals that capability essentially implicitly treated as that. So that's starting to grow. And we've seen a couple of efforts that use it in guiding the development of applications, one on adaptive coaching for behavior change, the other on identifying differences in functional connectivity in Parkinson's disease. There are a couple of others that we didn't really anticipate. The first one is as a means of integrating and building bridges across disciplines and paradigms. That seems like a really interesting way to use it, because it is across AI and cognitive science to begin with, at least, but this is not one that we had thought about earlier. And then it's also being used as a general reference on cognitive architectures and artificial minds. We haven't anticipated that, but it's kind of an obvious use. It's a summary of what people are thinking about, at least much of this area. Right, so conclusion on the common model and essentially this lumping approach to understanding. It reflects a very real initial consensus, for example, on particular modules and connections among them, a combination of serial and parallel processing, hybrid data metadata representation, procedural and declarative memories, and pervasive learning as a side effect of performance rather than kind of intentional learning. Though intentional learning can happen as a cognitive activity on top of the architecture, it's just not what the architecture itself does. We're starting to see some of the potential benefits realized, including this unanticipated promise of large-scale brain architecture. But it remains complete in a number of ways and may still be wrong in other ways. So it's very much a work in progress. But the hope is that it's a work in progress people can point to and say, at least that's our best current summary, even though it still needs lots of work. And then hope is that it continues to grow as a basis upon which to build. There is a journal that's been created, an online journal, which serves as an archive for papers on this area. So you're welcome to go there and you can find a range of papers on this topic. Okay, let's shift to the second topic, the splitting topic. This is working much more in a preliminary form, so take it all with a grain of salt. It's focusing primarily on the technologies underlying the core functionalities of memory and processing, or knowledge representation reasoning, and learning or machine learning. So let's see how this works. So here's kind of where we start. This is a table of underlying technologies found in AI and cognitive science, perhaps AGI as well. Though I didn't look at AGI quite as much explicitly as I did AI and cognitive science. And there's a mishmash of categories off to the left and a set of modifiers and variants in there. And it essentially provides a fairly succinct way to summarize a whole bunch of technologies you'll find in AI cognitive science in general and architectures in those areas. But it doesn't really tell you much more about these technologies than that. So the goals here are essentially to progress from such a coarse and ad hoc categorization of technologies to n-dimensional maps that reflect the inherent structure underlying these technologies. And then use these maps to begin to scope the space of technologies across these fields, to understand them in terms of the space of structures and the similarities, differences, and trade-offs among them, and then understand the rationales for integrating various of these technologies into particular architectures, in particular based on the need to span trade-offs defined by the different dimensions of these maps. My plan: first, explore general criteria for guiding and evaluating work. This is the basis for identifying trade-offs. Then introduce 4 dichotomies that seem to jointly structure much of the fields and the systems. and examine how many other dichotomies that pre-existed map down to these four. That's also going to help provide ties among dichotomies that are found seen in many subfields, but have generally been considered as distinct. Understand the criterial trade-offs embodied by these dichotomies. Explore how you might span them, so it's not an either-or choice of one side or the other, but how do you span the full space each defines? And then analyze maps that are yielded by cross products among the dichotomies. And one little bit at the end, I will take a look at this idea of spanning dichotomies in the context of sigma, and look at it both in the context of sigma and what's been inherited from SOAR, and to some extent the common model. So this will be an exemplar of some of what's come before. Okay, criteria. So in general, they're relevant to guiding development and evaluation, AI, cognitive modeling, cognitive science, cognitive AI, AGI architectures, and integrated systems models more broadly, even when they're not trying to be an architecture of this sort. The criteria in a field may normally be explicit or implicit. Here, we're going to try to make them explicit as much as possible to help understand the trade-offs determined by the dichotomies. The trade-offs imply that both ends have value in different contexts. We'll build upon that a bit as the motivation for studying. And in doing this, I took input from a variety of sources where people have talked about criteria for evaluating cognitive AGI architectures and so on. And so I built on that and tried to synthesize across. All right, here's the first page of 3 of criteria. I tried to be fairly complete in terms of the list I created, but the ones that are lighter are not used in this work, but they're here more for completeness. Again, more criteria are probably out there to be added, but this seemed like a good start. So you can see there are 3 varieties or flavors of accuracy: proof of meeting a standard, which correctness, precision, degree to which a standard is met, robustness is guaranteeing a minimal degree to which a standard is met. There are 2 flavors of temporal efficiency. There are 3 flavors of generality. That is essentially the scope of problems, mechanisms, and entities that you can cover. And then we've got simplicity. You have learnability in the context of initializability, programmability, understandability, and explainability in the context of usability. And there are a bunch of operability ones that basically, again, aren't playing in this work. So let's now look at the 4 dichotomies. The first one is asymmetric. So I pronounce them as if the parens weren't there. That's whether processing proceeds uniformly in all directions or in a single direction, basically over knowledge structures. And so logic, for example, is symmetric, whereas rules are asymmetric. Inconsistent, whether processing considers a single consistent situation or multiple inconsistent ones. So there you have, for example, monotonic versus non-monotonic logic. Metadata in the common model sense, whether processing focuses on symbolic data or quantitative metadata. Here you get, for example, rules versus neural networks. And non-combinatoric, whether processing complexity is exponential or greater or sub-exponential. An example here is planning versus policies. Now, these 4 didn't come out of thin air. The first 2 arose in an attempt to understand better the components or modules in the common model and other architectures like that. So you can see that both the procedural memory and the declarative memory in the common model are consistent but differ in asymmetry. The cognitive cycle is the inconsistent asymmetric component, and there's no inconsistent symmetric component to it. So that shows a gap. SOAR is very much like that, but it has refined notions for the consistent components, and it adds a reflective subgoing component for the part that is missing in the common model. Similarly, the bottom 2, and as well as a reuse of the top one, came out of an effort to dig more deeply into the traditional but coarse-grained dichotomy between symbolic and subsymbolic. So you can see here, symbolic essentially maps onto combinatoric symmetric data, whereas subsymbolic maps onto non-combinatoric asymmetric metadata. So they end up at the extremes of these 3 dimensions. But you'll also see that there are a number of technologies that fall in between them in these other cells. And so they clearly share aspects with both of these two extrema, which is kind of interesting to see how that plays out. So we've got intermediate forms, but we've also got interesting transition paths that show up in this map. So for example, you can go from first order logic to rules, from there to arithmetic circuits, and from there to feed-forward neural networks. Each time you're flipping one of the dichotomies till you get all the way from one extreme to the other. Or you can go from statistical relational AI to probabilistic graphical models to Boltzmann machines, and from there down to feed-forward and recursive neural networks. Two different paths, flipping different dichotomies at different time, but both emphasizing the similarities among different technologies in different ways. Okay, so here's a list of pre-existing dichotomies that map onto asymmetry. You've seen the rules versus logic. I'm not going to give you time probably to read all the others. I wanted to just focus on two others here. One is heteroassociative versus autoassociative networks, essentially feed-forward networks versus things like Boltzmann machines. That kind of fits into this dichotomy. The procedural memory versus declarative memory dichotomy that we saw in the common model. But there's also many more. This one seemed to have the most reuse throughout different parts of AI and cognitive science. I'm not going to go through all of these. You're welcome to find them when the newer paper eventually comes out, or in these talk slides if you want to take a look at them. This is probably the part that needs the biggest grains of salt at this point. This is an initial attempt to look at least for the criteria that used in this work, how they differentiate across this dichotomy. So you see plus and negative, where one seems to be preferred or not. You'll also see plus minus, where depending on the situation, one or the other could be better. A simple way of characterizing this particular figure is that essentially asymmetry trades off precision for correctness and robustness, and combinatoric efficiency for problem generality. That's one way to look at what this particular figure is telling you. We can then look at, so given that, sorry, I'm gotten lost. Let's see if we get back. Okay. So given that there are individual benefits of being at one end or the other, if you want to combine the benefits from both, you need to find a way of spanning the dichotomy. And from what I've read about and thought about, there are kind of two general ways for spanning this particular dichotomy, as well as most of the others. One is to just add distinct modules for each of the extreme poles. So for example, procedural and declarative memory, as you see in the common model, or shallow and deep reasoning modules. The other general approach is to support one of them in such a way that you can indirectly support the other. So for example, you can build autoencoders in feed-forward networks, and you can build declarative memory in procedural memory via things like data chunking and SOAR. You can also go in the other direction. I won't go into these as detail, but typically you can support one directly in the architecture and the other above it if you want to. Okay, here's the second dichotomy, inconsistent. So again, you saw the one in yellow before. One other highlight here is fast versus slow thinking, or system one versus system two thinking. One of the simpler ways to think of that is it's consistent versus inconsistent. It's a much more complex notion, though, that needs to be broken down further. And it's interesting to map it onto multiple dichotomies, actually. And again, there are a number of others here, including backpropagation versus reinforcement learning, where if you span it in the right way, you essentially end up with deep reinforcement learning. Okay, here's, again, our grain of salt figure. Again, one way to look at this is that, so consistent, so it trades off real-time efficiency and simplicity for robustness, combinatoric efficiency, and problem generality. Again, you can span this by having a module for each, like reactive skills and planning, or feed-forward networks and Monte Carlo tree search, as in AlphaZero. And again, directly support one and indirectly support the other. Here, it's interesting from consistent, inconsistent. Basically, the technique is to add situation or step variables. It's also known as spatialization. And you get the same general approach working in logics in probabilistic systems and in neural networks, but they often go by different names. And again, you can go in the other direction by, for example, using an inconsistent method for reasoning about consistent situation or finding a consistent subregion within an inconsistent process. Once you've got two dichotomies, you can take the cross product and get a 2D map. This one has abstract labels for the kinds of technologies that are found in each of the locations in the map. And they're all kind of reasonable things that you would want to have in a complete system. So it turns out for each of these maps, you can talk about building a complete architecture with respect to that map. Now, you may not want to do that with respect to all of the maps, and I'm pretty sure with respect to this particular map you do. And so if you have a gap, that shows that something's missing. Another way to look at this is that the consistent are basically memory, and the inconsistent here are control functions. Or you can twist it a little bit and see it as a 3T control structure, as you find in robotics with reaction, deliberation, and reflection. So reaction's kind of doing dual service here as both memory and control in a way that I'm still trying to understand better. You can then flesh this out with kind of the technologies that are in the original table. And since a complete architecture should cover all four, and these are the alternatives for all four, in some sense, it should be possible to build an architecture by taking one technology from each of these four locations and finding a way of combining them. Now, some combinations are going to combine better than others, and some will be more functional than others, but this just gives you a space of architectures you can build just based on this single 2D map. Okay, here's the third dichotomy, metadata. We saw neural network versus rule, and I'm pretty much not going to go into any more detail on it. In terms of criteria, so roughly it's precision versus correctness and learnability versus usability. Now, if you think of neural networks versus, say, symbolic AI, it shouldn't be too hard to see why these kinds of criteria map onto those. Okay, spanning. Again, adding for two poles, we see systems like Clarion and Sal that have both neural networks and rules in them. You can directly support one pole and indirectly support the other. Won't go into details. Here, there's at least a third one, though. And I don't know whether this exists in other cases too, but it's clear here. The one thing that can be done is create a generalization or combination that really subsumes both. They both end up as special cases of this more general approach. So statistical relational AI, structured neural networks, and the metadata dyads from the common model all kind of fit within that approach. With three dichotomies, you get an abstract figure that looks like this. It also includes a specific row for spanning of data and metadata, in addition to the data and metadata rows. So the original dichotomy between subsymbolic and symbolic essentially took quantitative reaction versus qualitative reasoning. Though given the third dimension here, you can extend that to qualitative reflection for the symbolic and make it an even larger contrast. Now, one of the interesting things about this is that if you look at AlphaZero, all it does is shift qualitative reflection down to hybrid reflection with its Monte Carlo tree search. If you then move all four into the hybrid regions, you get what SOAR and Sigma are both trying to provide. And if you drop hybrid reflection, you get the common model, which, again, if you remember, didn't have anything down in that right corner, as well as ACT-R, which does not as well. Just for reference, AlphaZero is missing the reasoning component. It seems to have the other three covered in one way or another. Okay, again, you can flesh out the locations, though you're probably not going to want to build an architecture which has one in every cell here. For example, you're probably going to choose one of metadata, data, or spanning, rather than picking one from each of those three. So you probably still want something like 4 different technologies at most to combine to build an architecture that's complete with respect to this map. Another way you can try to use some of this understanding is to look at things that have been kind of confused over the history of these fields, such as implicit versus explicit. We all think we know what we mean by that. But if you look at how it's actually used in the literature, some people map it onto procedural versus declarative memory, where declarative is clearly explicit and procedural implicit. Fast versus slow processing, where fast is implicit. Subsymbolic versus symbolic, where again, symbolic is explicit. But if you look at this in terms of dichotomies, each of these is a different dichotomy. So what's going on here is much more complicated. And there may even be more involved, but the full understanding of implicit versus explicit needs to understand how these different kinds of dichotomies are involved. So there's a way of thinking about it in which explicit is slow processing of symbolic declarative knowledge or inconsistent processing of symmetric data in terms of the dichotomies, and implicit is everything else. So to be explicit, you have to have meet a set of criteria, and if you don't, then you're implicit. And there may in fact be more involved here too. Okay, fourth dichotomy, non-combinatoric. So we saw policies versus planning. I'm not really going to focus on any others here. You can see there are fewer I found to map onto this one, but there's still a variety of interesting ones, including kind of the Monte Carlo tree search versus alpha beta search you see in conventional game programs. In terms of criteria, roughly this can be broken into two pieces, a trade-off of efficiency versus accuracy, and of simplicity and learnability versus usability. Okay, spanning non-combinatoric, again, you can do multiple modules. Or you can do this other kind of indirect-direct combination. I don't think I'm going to go into detail on any of this now, but just know there is work out there that approaches it in all these different ways. And then you can flesh out the 4D table. This is the non-combinatoric half. You'll see a bunch of things here that are kind of natively non-combinatoric, as well as a number of them that have the word bounded in front of them. Those are the ones that are essentially bounded combinatoric technology, bounded in one particular way. Here's the combinatoric half, which is sparser than the non-combinatoric one, and I'm not sure exactly why. That's an interesting thing to follow up in the longer term. And there's one cell here, which I could not dig up or think of a technology that would fit within it. You can see the blank one there for combinatoric, inconsistent, asymmetric metadata. So I can place that as a challenge. If anyone comes up with a technology that sounds at all reasonable that fits within that, I'd love to hear. Okay, so let's do quickly this example. This is an example of spanning the 4 dichotomies individually rather than looking at more complex maps in Sigma, grounded with its roots in SOAR. So the red parts here are the part that are new from Sigma as opposed to SOAR, or the common model. So the new part here on the asymmetric dichotomy is the use of extended graphical models as kind of the core knowledge representation and reasoning component, which lets you do both probabilistic reasoning, but also things like rules and feed-forward neural networks. So we derive the asymmetric from the symmetric here. And inconsistent, it's pretty much SOAR story, but there's a bit added of open versus closed world on the consistent versus inconsistent versions of rules. Metadata, so basically common model data metadata dyads. They're here structured as lifted region tensors. So these allow you to do both symbolic, probabilistic, and activation-based neural kinds of things. They let you do both discrete and continuous kinds of things, and they let you do mental imagery and other things as well, all based on these dyads effectively, which are mapped onto regions. Non-combinatoric is basically the source story of tri-level control structure, form of reaction, deliberation, and reflection. So that's basically my analysis of Sigma according to these 4 dichotomies. Related work, so we talked about criteria already. There is other work on dichotomies in understanding architectures, including larger automies and hierarchies, which go beyond just dyads, on maps that are cross products among dichotomies, and more broadly assessing what is common among cognitive architectures. So there's a bunch of work related to that. So conclusion on this splitting portion. Dichotomies partition technologies underlying AI and cognitive science and architectures. Key aspects of many of them can be distilled down to just 4, kind of mapping much of the field down to a much smaller understanding. Maps provide a more abstract level of analysis than the common model. They structure and relate the space of underlying technologies found in the disciplines and in the systems. And they start to give us a way of understanding the mechanism combinations in these architectures. Like, I'd like to get to the point where if you look at, okay, here are the 4 modules in the system, here's why each of those needs to be there, because the other modules are missing certain aspects of the trade-off space. And then criteria guide and evaluate work in AI and cognitive science and architectures in general, but they're what help you understand those trade-offs embodied by the dichotomies. Okay, in conclusion, the overall message for architectures. The lumping side, we're finding commonality with the common model by an evolving consensus concerning human-like minds to understand, communicate, build on, relate to, and challenge the consensus. On the splitting side, we're finding systematicity within dichotomic maps. So a structured map concerning potential parts, all kinds of minds to understand space of possibilities and their combinations. Each contributes in its own way, and with the hope that together they'll help bring order and understanding to this space and guide new work. Thank you. I'm open to questions.
Yes, let us receive the other video. 1 second. We can't hear you yet, Gabriel, so you have to unmute on Zoom.
Yeah. Great. Can you hear me?
Yes.
Yeah.
All right. Thank you, Paul. Thank you for the excellent talk. First, let's open some questions from the room, if there are any, before we move to online talks. Any questions from the audience? Yes. You're free to come up and face the camera if you like. Yeah. Say your name and your question.
Eugene Sorowitz, and with oh, the camera is there, right? Which one?
Turn around, I can see you.
Oh, back behind me, that's hiding in plain sight. Okay, very good. Back in 08 or 09, there's a paper that introduces the idea of dichotomous mapping of Jungian psychology personality types. That was done by, the analysis was done by Walter Lowen of SUNY Binghamton back in the early 80s. And I've been bringing it forward. And what I was thinking while you were talking, that there is a possible mapping between, for the lower level functions identified then, which is essentially a result of clinical psychology, to the internals of what you're finding and what the cognitive model is doing, that the two might be meeting at some point. Have you ever looked or seen that paper?
I don't recall that paper. I have. I've been looking a lot at personality lately and psychology in it, and primarily focused on the ocean model, if you're familiar with that. So it's a 5-factor model for human personality. And each of those factors is essentially a dichotomy. So I'm sure that there's a relationship to the paper that you're mentioning. And I was looking essentially at how Sigma could implement that 5-factor model. So I thought about it in that sense, but I haven't thought about either the ocean model or what you're describing in relationship to these 4 dichotomies. That's an interesting direction to follow up on. So thank you for pointing that out.
Thank you. Any more questions from the room? Okay, so let's have some online questions, unless, do you have something, Ben?
I guess
Here.
I have a more general sort of question that might be interesting for Paul to comment on. So, Paul, obviously you spent your career sort of bouncing between trying to understand human-like minds and trying to build systems, including systems that would display intelligence, as well as systems that would model human behavior in some way. The CMC is really interesting, and a number of us tried initiatives like that before and couldn't get a community aggregated for them. And it's amazing that there's been a community aggregated to do this now. I'm wondering how you see the connection between forming this common model of cognition and building AGI systems that actually do human level intelligence stuff. Like, do you want to get the CMC fleshed out further because that will give you guidance in building AGI systems, or do you think it's more off to the side and mostly just for conceptual understanding?
So there are two aspects to that, at least. One of them is, so I would think that focusing on a common model for human-like architectures is one potential path to AGI. There are other paths that don't pay attention to humans or view it much more abstractly as an inspiration. So that's one aspect of it. Hopefully it provides one path towards getting there, which is complementary to the paths that they do and other people in AGI are doing. The other aspect is I have a grander ambition, which was hinted at on one of the slides, which is to ultimately understand better the space of all minds. I think we're quite a ways from that, but in terms of what are the technologies involved, what are the combinations of technologies involved, and then what are the relationship between different kinds of minds based on that. And I'm hoping, even if it's not the common model that leads to that, but the dichotomic understanding might help to understand the different approaches to mind, not just human-like minds.
So you think the common model of cognition is more general than just human-like minds?
Well, not explicitly. I mean, what we're shooting for is human-like minds, but we should be able to get to a human-level human-like mind, which would be an AGI kind of thing, I would think. It doesn't say it subsumes the other approaches to AGI, because it won't subsume ones that are sufficiently different from human-like processing. It leaves open the possibility that there are very different approaches which could yield AGI from ones that are like the human-like mind. But the dichotomies is trying to cast the net much more broadly and cover all kind of integrated AI, AGI, cognitive science, whether explicitly human-like or not.
Yeah, it's interesting. It makes sense. I mean, I think sensation, action, procedure, or declaration. I mean, these symmetry, asymmetry, consistency, inconsistency, these are not about being like a human or like a three-toed alien or a dolphin or whatever, right? So you could imagine a form that gave a very abstract common model of cognition, and then the human-like common model of cognition as a sort of subcase of that ultimately.
So my favorite current example of that are things like AlphaZero, which were engineered to play games like Go and chess, but are easy to analyze in terms of the dichotomies. Turns out that it's pretty easy to analyze in terms of the common model as well, but that's a separate issue. So I haven't looked in detail a lot of the AGI architectures yet to see how well they fit within the common model perspective, though maybe others will do that, or the dichotomic perspective. Those are still kind of items to do.
Thanks.
Okay. Come on up. Say your name.
Okay. Hi, Dr. Rosenblum. My name is Mike Miller. In 2009, you wrote a paper called Towards a Cognitive Hourglass, and you gave the distinction between uniformity-first architectures and diversity-first architectures. Do you think that distinction is still valid today? And I didn't see very much of it in this particular talk. Any particular reason?
Yes, because this wasn't a talk about Sigma per se. Where I've really focused on this notion of what I now call functional elegance, of how one derives a diversity of capability from the interactions among a small general set of mechanisms. I call that, refer to also as kind of the physics perspective on intelligence versus the biology perspective, where there's a whole bunch of modules that have evolved over time. It's a different form of lumping versus splitting to some extent. And I still think it's important. So let's see, did I not include it? I guess it's not included in any of these dichotomies because it didn't really differentiate among technologies. And it didn't show up in the common model either. So I guess my statement at this point is, yes, I so strongly believe in that as both a methodology for building architectures and for being something that I care deeply about. But no, it didn't make it into either of these pieces of work. I can think about that some more too. That could be fun. So thanks for bringing that up.
All right, thank you. There is a question from the online audience. Ire has a question if you want to speak up. Going once.
Hello there, Paulie. Excellent presentation. Thank you so much. Right. I'd like to ask, how do you think, ideally, an architecture based on the common model should be implemented? I'd like to relate this to the proposals of Benjo and Gary Marcus. Which approach would you prefer? Do you think, like Gary Marcus, we need to build in a lot of innate stuff? Or can we handle this with inductive biases with a purely machine learning, general purpose machine learning approach?
So Marcus has been on a hybrid kick, though he hasn't, unfortunately doesn't always seem to recognize the stuff that's come prior to it on that topic. And I agree very strongly, the common model agrees very strongly with the hybrid notion. I would love to see Gary look at what he's doing in the context of the common model. Would tend not to agree with the notion, which also maybe goes back to Marvin Minsky's Society of Mind, of a whole bunch of different modules. I don't think in the architecture we see that in the human mind or the need for it in AI systems. And this gets also to what Mark, I think it was Mark, who asked the question earlier, that at least my approach and much of the architectural approach starts from the notion that you can get by with much less if you can understand their interactions. And then you have to combine the architecture with knowledge on top of it. But all of that stuff isn't necessarily built into the architecture. Now, there is some stuff that developmental research is showing needs to be built in there. And we need to look at all of that too. And that might increase a bit what's built in. But still the approach is to try to build in as little as possible.
Thank you
in
so
terms of Yashar Benji, I'm afraid I did not see his talk. I mean, I know his work in general. I assume he's taking it's all neural networks approach. Yeah, so that's closer to what we do. That we probably impose more structure than he does. So there are systems like universal AI and some of the work in neural networks, which try to get by with even less structure than the common model. We think those, as they get experience with them, they'll see that they do need some more additional structure on top of the base neural networks. And we think the brain actually does have that structure if you look at the functional circuits. So we're in between those two extremes, you could say.
Okay, so you are using some deep learning.
So there's certainly learning. I mean, Sigma of the three architectures has backpropagation. Again, not built into the architecture. It uses, there's a figure I showed which had a little Christmas tree-like looking thing. So it uses gradient descent at nodes in its factor graphs, but it controls the messages that appear at the nodes so that what you get is the effective backpropagation. So it builds it up. So with neural networks in Sigma, you get forward propagation along one set of structures and backward propagation on a different set of structures with links between those through ties. And then you get learning at some of the nodes that does what backprop does. So Sigma supports deep learning at this point in a way that builds on its earlier probabilistic learning.
and that's a hierarchical model. So it's like the hierarchical model in Friston's agent models too. It's a little like because you use message passing.
Well, so it uses a variant on the belief propagation or sum product algorithm for that were developed in Bayesian networks and factor graphs, and more broadly probabilistic graphical models. So basically, Sigma's cognitive structures all compile into these graphs, and then it uses this extended version of the solution algorithm on the graphs. So in a sense, it looks like all the neural networks, and it's one big graph, but there is structure. Portions of the graph are procedural memory, portions of the graph are declarative memory, portions are working memory, portions are perception and motor control, without having distinct modules in the architecture per se.
All right, so that's very interesting take. Thank you.
Yeah, so that's all Sigma, which is its interesting own story. And I've talked at previous AGI some about it, but and I think it's one of the more interesting of the common model architectures, of course, having helped to develop SOAR and then shifted to Sigma. But okay, I think we have more.
Great. Yeah, thank you. We have some from YouTube. So from Paul Berger, there is consensus at the macro scale for global common theories of the mind and also at the micro architecture level. But what are the key common insights, if any, at the meso scale level for that common model?
So I guess I don't know what would be considered to be at the mesoscale. Are we talking about the workings of individual brain functional circuits or regions, as opposed to neurons versus high-level architecture, in which case that would be the workings of the individual modules in the common model? And so there's a mesoscale story there in terms of the set of assumptions about how those modules function. But I'm not sure if the questioner, if that's what they had in mind.
Yeah, I think that's the most clear that question is going to get without doing back and forth on YouTube. One or two more questions is, I think you touched on back propagation already, but is the difference between back propagation driven ML models versus more biological methods like Hebbian learning significant to be considered for domains like perception among the broader scheme of things?
Okay, that's an interesting question. And so that, I didn't focus on that, but if you look at the asymmetric dichotomy, that distinguishes backprop versus Hebbian learning. Hebbian's is a symmetric learning algorithm. In fact, Sigma supports both. Its probabilistic learning algorithm is essentially symmetric. It looks at all the messages coming into a node and learns from that. But by restricting the set of messages that come in, you can make it asymmetric and support things like backprop. So in my view, I think both are necessary. I think we need both symmetric and asymmetric networks and learning that works appropriately for both. So that's a case where I think spanning is critical. And again, Sigma is one suggestion for how to do that spanning.
Okay, great. Thank you. We have one more question online, and then I think we'll wrap up for the next talk. So that previous question was by Shubhamkar Ayare, by the way. This next question is from Bob J. Question is it worthwhile to run your analysis against an AGI approach to potentially see what may be missing, inadequate, not addressed, or improved?
Absolutely. I have been more focused on more traditional AI and cognitive science architectures and doing this kind of analysis. The common model, I think, will be interesting, but it might be stressful. I mean, particularly for architectures that are quite different from it. But if we can find any kind of commonality, I think that would be very interesting and very useful. In terms of the dichotomic analysis, I would hope we could cover all the AGI architectures in that way. I have not tried to do that, but I would hope you could do that.
Here's Ben.
Yeah, just a quick comment on that. I mean, regarding OpenCog and OpenCog Hyperon as examples of AGI architecture. I mean, in 2012, in the book Foundations of AGI, so Matt Clay and I wrote a paper trying to integrate together various different sort of block and line diagrams analyzing how the mind works, and we mapped OpenCog in our book Engineering General Intelligence. We mapped OpenCog into these various categories, and I think that mapping that analysis into the common model of cognition will be fairly straightforward. I'd say for Pei Wang's NARS system, which I know pretty well, I think that
before you go on. So I've reread that bit you wrote several times in the process of all of this, and haven't yet tried to do it, but I think it's a great thing to try to do. Sorry, please go ahead.
I think those mappings could be done, and if you look at, say, Kristen Thorson's HumanObs system he used with like self-replicating code fragments, rewriting each other to control humanoid robots. That's more different in a way that would be interesting, because sort of everything sort of emerges out of into rewriting codelets. But I still think you could do that mapping, but you'd be looking at things that emerge in that system, serving the role of what look like modules in the common model, right? But I think that mapping could be done, and I can't see any way that looking at the AGI architectures I'm familiar with and trying to map them into the common model of cognition, I can't think of any catastrophic failure that would happen there. I mean, I think that would be a semi-straightforward exercise, and the interesting thing would be in some architectures, some things are emergent, whereas in the common model, there's sort of a implicit assumption these things are software modules or something. But if we're looking at emergent processes as corresponding to some of the modules, I think it would work and would be a worthwhile thing to pay attention to. The challenge is always taking time away from building and analyzing your system to create these sorts of mappings, right? Because it's also work.
The biggest difficulty with a community effort. But the blue squares in that earlier chart were intended for things that essentially emerge on top of the architecture, like that. So for example, the codelet ones, the most natural initial mapping is codelets are skills. They're in skill memory. And then to see what else falls out if you start from that perspective. Okay. I guess you're setting up phonetics. So thank you very much, and enjoy the last little bits of the conference.
Yeah, unbeknownst to me, people are putting extra slides up behind me. Well, then, I guess we are moving on. All right, thank you, Paul. Yeah. No, that was a fantastic talk, Paul. It's great to see someone taking an overview of how the different architectures connect to each other after a bunch of stuff of like, this is my architecture, this is mine, this is mine. So looking at how they connect together is super important and something no one ever wants to take time for. So great that it's happening. Thanks.
So I guess when you're getting old.
Yeah. Well, I guess my next job here is to introduce the next speaker, who is face-to-face here in Palo Alto, who is Josef Urban from the Czech Technical University in Prague. And Josef is probably the world leader in AI and machine learning applied to automated theorem proving, which is either a tiny corner of the AI field or like the golden path to creating super AGI, depending on one's AI paradigm. I think there's ways, of course, AI for theorem proving is different from AGI, but there's, of course, if you have an AGI that can help with theorem proving a lot more than a narrow AI. On the other hand, if you have an approach to AGI that has logic as a key component, then AI for theorem proving can be super helpful for making your AGI work. So I think there's a lot of close connections between AITP and AGI, which is why Josef is here. So yeah, take it away.
So thanks a lot, Ben, and everybody for inviting me here. I have been once in Prague at AGI, and that was a lot of fun. So I have a talk with a crazy title. You can click on it, and it was a long talk. It was probably the longest talk I ever gave. And the talk had a funny title. No one shall drive us from the semantic AI paradise of computer understandable math and science. So today's buzzy talk is sort of a continuation of that. And so what I did 3 years ago was like fairly technical, like a lot of stuff about what we are really doing and what works and what doesn't work. And I sort of didn't have the benefit of sort of learning from you, like from your community. I was just there for 1 day because I had some other things before that. But now I'm the last talk of this conference, well, sort of. And so I basically spent the whole day today to try to, instead of just doing the technical stuff, like to say something about like what like your presentations here provoke me into. And I think the first part will be sort of probably the most philosophical rambling I have ever done in my talk, because normally I'm fairly technical, and it might also be a bit provocative. Like I'm typically provoking the people at the automated reasoning conferences because I'm doing things differently than them. But I feel like maybe also it's good to provoke you a bit. You will see. So the first philosophical rambling is just a sort of a geographical note. So in Prague, I was provoked to make a note on Kepler, who is one of the big heroes in the scientific revolution, and also because he is the author of the Kepler conjecture, which was recently concluded in being fully formally proved. Like it's one of the biggest achievements in automated reasoning today. Like the proof of the Kepler conjecture was finished thanks to computers back in 1998, and it took until 2014 to fully formally verify it, because basically the proof was so big that mathematicians didn't believe it. So he's an inspiration for many reasons, and obviously he's not the only guy, but he's one of the guys who were sort of in this crowd of fairly crazy people back in 1600s in Prague, actually, who went from crazy stuff, like from today's point of view, like alchemy, or some fairly crazy ideas about how the universe is geometrically constructed, to the sort of discovery of science, of the scientific method, of the scientific revolution. So this sort of against the philosophers, against the theologians, you had this gradual movement of the natural scientists, of the people who called themselves initially natural philosophers, and then they ended up calling themselves scientists, physicists, mathematicians, chemists, etc. And like at least to me, there is sort of an unbroken line from these people, like what started to happen for all sorts of strange reasons in 1600, to basically these sciences, the tools that the sciences developed, and to the abstract machinery that basically came out of it, which basically ends with Turing machines and the beginning of artificial intelligence. So that was what I sort of alluded to in 2018 in Prague, and now this is my next AGI conference, and I'm in California, and my next hero comes, like whose books I have been reading as much as I could, and that's Werner Vinge, which, as far as I know, is also responsible for the notion of singularity. And like the one big motivation when I was reading his books, I don't know how long ago, is this idea which he describes really nicely, that you are some space explorer who crashed his spaceship at the backward planet, and now you go into cryogenic sleep, and you sort of try to develop the science that will allow you to escape that sort of stupid zone of undeveloped technology, and the benefit of those travelers is that they typically know at least basically how the technology and the science should be developed, but we are sort of not in that situation. So we are in the situation of people who want to escape our slow planet and go to other parts of the galaxy and developed all sorts of other cool technologies, like, I don't know, cryogenic sleep and safe fusion and immortality, etc., as fast as possible. And how do we do that? And like the way I would think we should do that is basically to automate the process which started with Kepler, automate the process of doing science, automate the process of scientific discovery. And so that's sort of what I'm trying to do. And a big motivation for me was this book by Art Quaife, who did PhD like more than 20 years ago at Berkeley, doing basically automated theorem proving of basic mathematical theorems. And he has a beautiful foreword in that book saying that he's basically doing it to automate science, the automation of mathematics, like the development of strong automated mathematicians is the way how to basically start automating the rest of the sciences. And so, sort of that brings me to this like slightly controversial topic, hopefully, and that's in automated reasoning. Like if you go back to the founders like Martin Davis, and read, for example, the early history of automated reasoning by him, he makes a very nice distinction between the sort of logicist and the sort of more heuristic approach to automated reasoning, and possibly even to artificial intelligence, like you have the NEETs and the Scraffies, right? But like he, for example, makes a comment about like this, probably the first AI system by Newell and Simon, the logic theorist, which was a heuristic system for proving statements in propositional logic, versus the DPLL, the Davis-Putnam Lovelace procedure that Martin Davis sort of started to develop at that time, and which today is superhuman. It's better than whatever humans can do. And the idea that we would be writing heuristic problem solvers for propositional logic is today utterly ridiculous to basically everybody in the field. But it wasn't at that time. So in some sense, it's almost like probably not as much but it's in a similar way superhuman or inhuman as the modern implementations of the artificial neural networks. Like they might be more like biologically inspired, but like I guess you all know probably even better than me that they are not exactly what's going on in our brains. So we have and we will use superhuman algorithms for some parts of automated reasoning, and there's basically no way back there to some biologically inspired architectures. And so this is, and you can, like, I'm sort of the contrarian in the automated reasoning conferences, where I'm the guy who says, you guys have gone too much to the logic-inspired approach. You do too much thinking on your own, and you should do much more learning and much more combinations of learning and reasoning in various feedback loops. But like here, I feel like I should say and give credit to these people, because they have really been doing amazing job. Like Seth is really sort of decided in favor of these logicist approaches. It's extremely hard. It is possible, but it's extremely hard to, for example, put some machine learning reinforcement learning architectures into such solving today. And similarly, like there have been a bunch of really good improvements in the sort of logicist attack on like more complex logical calculi, like first order logic, high order logic, etc. So for example, Andrei Voronkov has this avatar architecture, like the advanced vampire automated reasoning architecture that really broke new ground like five years ago. I may say something about it. So for me, like yeah, maybe it's on the next slide. So there is a bunch of these things. Like for example, there was talk about embodiment a couple of times here, and like the interesting question on the first line, like when Robinson saw the first sort of embodied geometry machine by Galanter, he was a logician and he knew Herbrandt's work. He immediately realized that it can be generalized to crazy abstract spaces called Herbrandt universes, that the sort of our embodied thing in the Euclidean plane or space is just a particular case of that, and fine, like we may have a lot of like evolutionary space intuition, but we can basically what Galanter was doing can be like a general reasoning, like theorem proving procedure, usable for anything, any math basically. And then it's sort of hard to make the case that it's embodied, right? Like it's a nice open question, like how much the mathematicians who think about set theory or whatever are internalizing those things, and how much they connect it to some intuition-based, like older evolutionary parts of their brain or whatever. So why should we care? If we imagine that we are in the sort of Werner Vinci shipwreck scenario and we want to quickly get out of the planet Earth to our home galaxy, like I don't really care how we do it. Like I just want to do it. So in some sense, like this, I think it's in the title. This sort of human level thing for me is is not the main thing. Like for me, the main thing is the first thing, the automation of math and science. And obviously, you can argue from the other side, right? Like the sort of logicist people, they have tried too hard and they failed quite a lot in many cases to sort of fully design some algorithm which would be complete and it would solve it all. And if they are worse than human mathematicians, well, then they should probably learn something from them, right? So definitely, like I've been arguing the other point for more than 20 years. But again, like I can see a lot of sort of inhuman ideas in the automated reasoning, like I mentioned Voronkov's avatar, where basically the SAT solver is used as some sort of high-level planning / decomposition algorithm, which is sort of chasing the sort of more complicated first-order prover on the components that it creates, and it's really very, very powerful. So for me, for example, this like good and I like Kahneman, etc. Like idea about system 1 and system 2. It seems, and I'm sort of giving you feedback. I might be wrong from my sort of more AI position. Seems quite a bit connected to the human architecture already. Like I can imagine like complicated inhuman architectures that might be better than for example, the system 1 and system 2 idea. But I could be wrong. I'm not saying I'm an expert. So the conclusion that I sort of made a long time ago when I was going through all these ways, how the hell should I do some sort of more human-like automated mathematicians, is that this is an experimental science, and I should be suspicious of both sort of the logicist and the sort of humanoid or whatever opinions and the sort of little voices in myself, and I should really just do it experimentally. Like obviously there is a ton of ideas out there and we are aware of those ideas, but like it's Leibniz, it's calculimus. Like in the end we calculate and the person who calculates better wins, right? Like he's right. So I'm much in favor of this. Like let's be the Turings and the hackers rather than the Wittgensteins and the philosophers. And my sort of experimental methodology here is that I basically got my hands on the largest formal math corpus around 2000, which is called MISAR, and I translated it for all these tools that could sort of run on it. And I basically started to evaluate how the various systems do and create like more complicated systems, etc., etc. And today we basically have done this for all the major formal mathematical libraries that are out there, and we can really very rigorously evaluate what works and what doesn't work. So you can like I will show you later. We have this set of something like 60,000 top-level MISAR problems that nobody tuned for something to show something. Like it's basically mathematicians' attempt to verify as much, I don't know, undergraduate, graduate, PhD level mathematics as possible with all sorts of means, like the technology in making mathematics understandable and proof checkable to computers is non-trivial. So like all of this is developing, but we have a fairly advanced mathematics today. Like for example, the formal proof of the Kepler conjecture is one of those. So that's this. And I would say like if I compare well, like what I hear from you with sort of where we are, I would say we are pretty primitive today. Like we did, I would say, the basic sort of AlphaZero Monte Carlo tree search reinforcement learning loop for the first simple prover about 3 years ago. And it sort of started to work. I think I was talking about it at the AGI in 2018. And like 1 year after that, we started to reasonably improve the state-of-the-art automated theorem provers, like by some sort of reinforcement learning procedures. But it's not very, I would say, sophisticated today, like compared to the architectures that like I can sort of hear about at this conference. It's very simple. So if I would say I invite you, like if you feel strongly about your ideas and architectures, throw them at us. Like show us that the sort of cognitive architecture is better than some stupid brute force search, right? Or stupid human-made heuristics or whatever. It's not easy, but I think it's also not too hard yet today. Like the things that we have done, we are very happy that they started to work quite recently, but they are not at the level of this conference. Like I would say, you are like one level more sophisticated than we are. And yeah, well, I would say we definitely like a lot of the work, because the symbolic solvers are so good and so well engineered, is sort of good architectural design, good implementation work. Like if you just say, okay, GPT will do it all for me, then you will fail very miserably. Like if you don't adjust for the fact that you might not be right, that you need to backtrack, and that the systems that backtrack can recover from their mistakes, then you will be much worse than the symbolic systems. And like I just want to make one final philosophizing note about a talk that I listened to with interest yesterday. So most of the talks here, and you sort of might be used to it pretty much, but at the like automated reasoning or formal theorem proving conferences, a lot of the talks are sort of talks in the code. Like when I'm reviewing the papers, I'm actually running a proof checker on the formalizations that people do. Like here, all talks practically, including mine, except from the talk yesterday by Sam Alexander, were natural language, and it would be hard for me to think like how to make them executionable, like how to turn them into math, how to verify the math. But the sort of probably old news for most of you is that math is today really at the level where we can mostly turn it into code, when we can verify it and we can quite often run it. And like I said during the panel, like there's this symbolic logic which actually has been sort of turned into computers in some weird twist of events. And we are now using the computers, like these symbolic logic machines, to basically do math on them and basically verify arbitrary math. And this process, even though it took a lot of time, is today becoming pretty like serious. So the mathematicians are really coming on board more and more, and very serious mathematicians. So Mike Beeson, who lives nearby, called this the QED singularity 5-6 years ago when we did the QED workshop after 20 years. And it's this idea that whichever way we will do it, like we will probably have some, I know, like I'm bashing GPT, but GPT might be one of the tools that will help us to do it because it's extremely good at translating from one language to another. So it could be that we will have such automation tools that will basically, as we speak, as we are talking math or writing math, it will be turning it into like formal proof checkable code, and it will be calling our symbolic machines to proof check that sort of stuff. So I would say this may be, I don't know how far is some sort of singularity in terms of us producing machines that will be better than mathematicians, but this seems to be pretty close. And like I'm sort of the guy who started it about 6 years ago when we basically started this automated like training of systems, like initially just context-free grammars, but then we started to use recurrent neural networks and transformers combined with various semantic methods like type checking and theorem proving. I can show you demo if there will be time. To do this, like to do this translation from the natural language, the mathematical natural language, to the sort of formal logic. And it seems that this is really something that is not very distant, and that this sort of QED singularity might come sooner than everybody was thinking, that this might happen in a decade or 2 decades, and we will suddenly live in a very different world, like in a world where a lot of the sort of scientific stuff that we say will be immediately computer actionable, like semantically annotated, disambiguated, and the computers will be doing crazy stuff on top of that. So
now we take for granted we have a calculator.
Yeah.
And we can write scripts, and it does then your whole life.
Yeah.
Calculate 100 digit of
Yeah. Yeah.
That will make a lot of other things different possible.
Yeah. I'm really, I didn't think that it would be so fast, but the systems don't seem to be so complicated that are doing that's. Like obviously you can always come up with some like sophisticated counterexample, but that's not the point. Like the point is that 80-90% of our, let's say, mathematical discourse might be really quite reasonably easy turnable into something symbolic, something formal on which machines can help us. So this was, I think, the philosophizing. Now I'm showing you my sort of standard overview of how, like, what are the various things that we are today doing to use like various machine learning / AI methods to help automated theorem proving. So the like the most established thing that we can do is that you give us a really large corpus of mathematical knowledge, and we train on the proofs that are in the corpus. And when you give us the next conjecture, we are quite competent in sort of pinning down what will be the knowledge that will be relevant for proving your new conjecture. So this has been done for more than 15 years now. And like the systems are improving, and the methods today work quite nicely. Like there is a bunch of other high level methods, like for example, selecting different theorem provers or different strategies or different portfolios of solvers when you are given some problem. So that's also like can really influence a lot your capability to solve the problem. What was the focus of most of the work recently is this sort of low-level guidance. When you take like the best automated theorem prover that you have, and you try to guide it, so these systems are fairly explosive. They are also fairly fast, and if you can tell them like where they should go and where they shouldn't go, and if you are not horribly slow, so that when you are not totally perfect, you can still reasonably backtrack, then there is sort of a niche where these systems can be improved quite a lot, at least like systems that do first order logic or high order logic. Then there are systems that are sort of working on a bit higher level. So those are systems that are guiding the so-called interactive theorem provers. And there you typically have some tactics in the interactive theorem prover. And the tactics are like bigger components that are telling you, well, now do induction on this, or now just do proof by contradiction, or something like that. So once you have these bigger blocks in these sort of formal proof assistants, you can train like various methods to guide your tactical applications based on your current proof state. So you can again do something like AlphaZero, for example. You have some state, you have some actions. Now you can run some Monte Carlo tree search, etc. That also seems to be quite working quite nicely these days. And like you can do like more AI-ish things. Like I will hopefully have some time to show you a bit of that. So like theory exploration is this basically uncontrolled conjecturing. So you may get some axioms of some theory, and now you would like to state the interesting lemmas in the theory, and maybe they are too hard for you. So maybe you want to state some other lemmas that will possibly lead you to those lemmas, etc., etc. So these are quite hard things to do. We are not very successful in them, but I can show you some funny initial experiments on them. So let me try to show you what Zar gave me recently. This is actually very cool. Can you see it, or should I increase the font size?
Perhaps zoom in a little bit.
Plus. Oh, okay. I'll just leave it at this. So, let me go to the top. If I know how to do it here. Just a minute. This will take too long. Yeah. So this is like an intro to what to the proof that I'm going to show you. It might be too small, but I don't know how to increase the font size. So for about 1 year, maybe a bit more, we have been running some sort of reinforcement learning loop where we take like the best open source state-of-the-art automated theorem prover on these 60,000 mathematical problems slash theorems in this corpus that has been created by mathematicians interested in formalizing math. And like initially, the automated theorem prover without any learning can solve about 15,000 of the problems in that corpus. And like what we are doing is called Enigma, like the efficient learning-based inference guiding machine. So we on the 15,000 initial proofs, we train some predictors, something that tells us in some situation what sort of inferences we should be doing. Like it's a sort of biases the search. We sort of plug that predictor into the automated theorem prover, and then we run it again on the problems. And that way, like we basically generate more and more proofs. Like typically we also generate like different proofs for the problems that we have already proved. And the body, like somewhere down here, we go from whatever 15,000 proofs to something like I think we are almost at 45,000 proof out of these 58,000 today. So it's like 2 times, 3 times more. Like it's approximate because there is a lot of technical issues which I'm sort of glossing over. Like I said, it took to get from the initial 15,000 to something like 45,000 took us a year or maybe a year and a half of running the learning and the theorem proving in various ways, and like continuously like implementing new things, like how to combine the learning with the theorem proving and the guidance with the theorem proving. And like initially we had 15,000 proofs. Today we might have like, I don't know, 3 million proofs. So the full corpus from which we are learning is much bigger, and it actually costs you more to train something. But once you retrain it, it is typically better. The proof I wanted to show you, just to give you some sample of what I'm sort of talking about. I don't know what happened now. I'm not a Mac person.
We still hear you. But we see a blank screen.
You want to go to Chrome?
Yeah. But there was the PDF, and inside it looked like it loaded Chrome, and now it's sort of disappeared. I pressed this arrow.
Oh, so this.
Cool. Okay, and then if I how do I go back to the PDF?
You're in the PDF.
But it loaded the HTML.
This is the reading you were showing us. So let's go back to the presentation.
Well, I wanted to click it again because I got lost here. Can you get me back to just to the presentation?
You mean this?
No, this is the HTML,
PDF.
The PDF.
I can pull it up again.
I just clicked on the link in the PDF and it did this, so it looked intelligent. Oh, cool. Yeah, thanks.
Okay. I was confused.
About that, that's what I did, but it didn't work for some strange reason. Thank you. So now I will probably do the same thing again, and it will break again. Let me. Can you wait here for a minute? So if I do it, and now I click this. Is that correct?
Arrow. The arrow back. Yeah.
No.
I don't know. So what did you click?
This one. So sorry.
4.
Click again.
Which link?
I'll link in the PDF. Oh yeah. You managed to do it. But I don't know how you did it.
Click the back arrow, nothing happens.
Oh, okay. Now it probably needs Matt's fingers, because when I do it, it doesn't react to me. Congratulations. Okay, so I'll go again to the proof which Zar gave me. Yeah, this is really weird. Oh, so here's one proof. I'll try to click on it. Oh, okay, something's happening here. Can you? Yeah, I just need to click on it so that it unpacks.
So it what?
Like if you click on this proof keyword, it's
Oh, okay.
Well, maybe I'll just show it like this then. So
this keyword, like right here.
This proof, I can put it here. Oh, okay, now it worked magically.
Yeah, you just need to hover over it.
Okay, thank you.
Not click.
Oh, okay. So
it scrolls off. So.
Good. Now that's what I want. So it's probably too small for the people in the room, but hopefully at least the people who watch this via Zoom. So this is a theorem that we got like, I don't know, maybe 2 months ago when we implemented like a combination of the guiding and learning methods, which basically combine like a graph neural network, which is the slow thing, and they combine like 2 ways of using gradient boosted trees, which are the sort of fast feature-based classifiers, which are telling to the automated theorem provers what it should be doing and what it definitely shouldn't be doing. So the proof is about. So I will try to say what it is, because you probably cannot see it. So it says that if you take a subset of the real line and you take 2 real numbers, a and b, a smaller than b, and you take the set of rational numbers between a and b, then the closure of this set of rational numbers between a and b is the closed interval of real numbers between a and b. So the proof is quite long. So this is some sort of natural deduction proof written by a human, which basically needs to argue by some sort of doing one inclusion, like that the closure is in the interval and that the interval is in the closure. And one of the cases is easier and one of the cases is harder. For one of the cases, you need to do quite a bit of like calculation, like arithmetic, like that's all these like multiplications and divisions, etc., inequalities. And in order to do that, you need about, I think it's about 80 lines of this like human written code. I probably do not know how to click here. Just get back in the browser. Cool, thanks. Oh, yeah, so here's some statistics about the proof. So what's what you possibly can see here is that the proof initially got 100 axioms. Out of them, it used something like 40 to basically 60 of them were unnecessary. The proof is like 359 steps long, and it additionally does like 200 some simplifying inferences. So it's not too long, but it's also not totally short. So it's altogether it maybe something like 600 reasoning steps to get it. And the sort of interesting thing here for you, like to compare with some sort of human architecture, is this number, which says that when when the theorem prover was working, it generated almost 500,000 inferences, almost like 500,000 new facts. And now, so it sort of tell you how explosive this is. Like you give it 100 axioms in the beginning, and it within something like 4 minutes, it can generate 500,000 more facts, basically. And the sort of hard part of what we are doing is to choose out of these 500,000 the ones that will lead you to these 500 that is the actual proof. So the factor here is 1 to 1,000. Like you need 500 for the proof, but you generated 500,000. So that's in this case, it's the task for the for the machine learning, for the various layers of the machine learning guidance, which are telling the automated theorem prover on which new facts to basically focus. And then in this case, like so this is something done by Zar. He's using something called parental guidance, which basically immediately kills, I don't know, one third of the generated clauses, because they look very much like junk to the trained classifier. On top of that, so that's the very fast classifier. On top of that, there is something very logical in that. It's called subsumption. You probably heard that in various contexts. So in first logic, it really just means that one clause is subsumed by another one. Like it's more concrete than the other one. And these particular systems, they know that there is like a more concrete clause, they can safely throw it out. But this is also slightly expensive, because you have 500,000 clauses, and now you basically need to check against all of them if your newly generated clause is already subsumed by some of them. So it's like here you can sort of see actually the two methods are sort of, if reasonably implemented, are equally fast, I would say, today. So both the sort of very logical method of pruning out the junk, thanks to like all these logical theorems that we know that are telling us that the calculus is complete even with the subsumption reduction, is equally fast as this sort of heuristic machine learning based methods, which has no formal guarantee on it, which we can be wrong. If the predictor is wrong and it throws out the wrong clause, then either we are done or we need to recover by finding some alternative proof. And that's just the first phase. So after that come like more expensive machine learning steps, like for example, feeding all the currently prioritized clauses with the newly generated good clauses to a graph neural network. And the graph neural network then basically does its own neural inference, like it thinks hard about a collection of 2,000, 3,000 clauses together. It does some message passing among them. And based on that message passing, well, it will say, okay, so with respect to the context of the clauses that I already chose, these, I don't know, 100 clauses will be the good ones that will most likely lead me to the proof. So that's sort of the current most sophisticated architecture that we are using to get these sort of proofs. I wonder when should I finish? Oh, okay. So I sort of hopefully showed you how the data looks and explained how at least one of these methods look. And I can now sort of go arbitrarily long, but the links are sort of in the presentation. I would like to.
I was just here to help.
Thanks. I still do not know how to click to get back. How do you do that?
Up in this arrow.
Yeah, I know, but I think my clicking capability here is really impaired. Yeah. So 5-10 minutes. Thank you. Okay, cool. So I will probably skip the rest of the demos because you can get to them later. So as I said, like this system we have been developing for like 4 to 5 years. You take like one of these state-of-the-art systems that is called eProver. It proceeds by this sort of generation of facts, like very fast generation of facts, and you are trying to learn from the proof runs, from the successful proof runs that it did. What are the positive and what are the negative examples? And in particular, like the best method that we have today is a graph neural network, which has one interesting property, which might be sort of interesting for you when, for example, people are talking about analogizing, like the analogizing problem is not solved and that it's hard, etc. So the graph neural network that we are using is totally concept independent. Like it doesn't see the names of the symbols. It only knows that some symbol is shared in the graph structure, in the term structure. So when we did that, when one of our guys did that graph neural network, we actually tested the graph neural network, what it thinks about the names of the symbol. So if you give it a large enough graph, you can then ask like, what's your opinion? Like, is this like real plus, or is this complex multiplication, or is this some lattice operation? And the neural network actually has some quite decent guessing capability. Like it can say, okay, so 70% times it guesses like the names of the symbols correctly. But it can also really, for example, mistake complex multiplication for real multiplication if you trained it a lot on complex data rather than on real data, and the formulas look isomorphic. So with this respect, especially when you are in the causal setting, you might have heard of Solomonization, which is something that basically turns the existential quantifiers into new constants or functions in your sort of universe. And then, like typically these column constants do not have a good fixed name, and they are like 50% of your symbols in these problems. So if you do not know how to handle them sufficiently abstractly, like how to learn from those symbols, then it obviously works much worse than if you do. So that's probably one disadvantage of using transformers for this sort of task, because they are very name dependent. Like they always work with particular names when you are encoding things. I'll probably skip this. And like this just shows you the sort of reinforcement learning loop. So this is the experiment we did like 2 years ago when it started to work. So we start with these adversarial, with these 15,000 problems proved by the initial automated theorem proof without any learning. And then it sort of shows you how we progress. Like after the first learning, the system gets stronger in 2 different ways. And then we learn again from the union of those proofs, and it gets even stronger, etc. So in the end, we get like 70% improvement. So I'll just skip this. And I'll probably go. Yeah, I just want to quickly show you some funny stuff with the conjecturing before we get to the questions. So about 2 years ago, we find like there is quite some history to using like probabilistic context-free grammars and recurrent neural networks to generate math. Like you may know these Andrei Karpathy's RNN experiments where he actually used some LaTeX math texts and like the Linux kernel code, etc. And if you are not a mathematician or an expert in that field, you will maybe even think that he produced math, right? Like that's the problem, is the transformer also. So when I used that when he did the blog post, it was really bad. But about 2 years ago, when OpenAI released GPT-2, I did it again, and I can show you sort of what it does on math, because like math is more semantic than natural text. Oh, so this is like a fake GPT-2 proof that was generated by me training GPT-2 for about a month on the full library, and yeah, I think we now need to somehow switch back to the slides in the Zoom. Yeah, I'm almost done. I just want to show this funny proof. But like if it doesn't work, we can. Almost. Yeah, I think you need to click on desktop and then switch to the slides. Yeah, it's somewhere in the browser, I think. Yeah. Yeah, maybe you need to click on it. Huh. Cool. Okay. Yeah. If you can go to the very bottom. Oh, yeah. Okay, I'll take it from you. Thanks a lot. Yeah. So we wanted this thing. Yeah. The interesting thing is that, like here, the GPT-2, first of all, it proposed by itself a theorem, which is actually true. So it says if you have two finite sets, one of them X is non-empty and X is a subset of Y, and their cardinalities are equal, then the two sets are equal. And the other funny thing is that it added this non-empty-net assumption for the set X, which is unnecessary, right? Like you can prove it without the non-emptiness assumption, and it is actually in the Mizar library without that non-emptiness assumption. So that happens quite often. Like at least that's my experience when I was playing with GPT-2. That it sort of stochastically, probabilistically changes like these additional assumptions, and sometimes it simply throws an assumption there which is unnecessary based on how frequently they appeared in like similar texts. So that's one thing. The other thing is with the proof. So the proof has sort of decent natural deduction structure. So what it learned is that if you start with a universal quantification, then the proof needs to start by saying, well, let X and Y be some arbitrary but fixed finite sets. So that's a sort of natural deduction step. And then it also like reasonably treats the rest of the natural deduction steps, because they are like very syntactic, like they sort of match the structure of the theorem you are proving. So in my opinion, like GPT-2 is pretty good in sort of learning this syntactic correspondence between the sort of skeleton of the proof and the theorem you are proving. What is like totally fake is actually the steps which the mathematician needs to do at some point, which sort of fall from the sky. So for example, at some point, I think here, it says, well, cardinality of y minus x equals cardinality of y minus 1 minus cardinality of x. Like there is absolutely no reason to say that thing at that point in the proof. It's wrong. It's yeah. So here is basically something which looks like syntactically correct. It looks like a piece of mathematics, but anybody who sort of understands the proof and knows what needs to be done here, like this very much looks like being copied from some context where induction of finite sets was used. When you sort of need to decrease your size of the finite set by 1 to sort of eventually get to the base case of the induction, but like that's not really happening here. Yeah. So for me, like looking at this sort of proofs, like what was quite interesting because it's sort of in this sort of very semantic world of mathematics where we not only see the tokens, the syntax, but we also like understand, like we have some semantic understanding what needs to be done at that point of the proof. It shows you, in my opinion, better than in some sort of linguistic scenarios what it can do and what it cannot do. Yeah. So this was this example. Yeah. So I also so sometimes, like just by this sort of statistical change of the assumptions to adding something plausible there, it actually generates something that is new and provable. So that's what I'm showing here. Like I'm getting a GPT proposed theorem, and then I'm using the sort of automated theorem proving technology to actually get it proved. So it works sometimes. You can see it here. And what even happened is that it generated conjecture by playing with these assumptions. So there is a theorem about finite groups in the Mizar library that can be generalized to arbitrary groups by removing the finiteness assumption. And the automation that we had, like I didn't use anything too strong. I was running off the mill eProver, couldn't prove the generalization, and I'm stupid enough not to know whether it's provable. So I actually asked Michael Kenyon and David Stanovsky, and they confirmed that this is actually a provable generalization of the theorem proved for this finite case. So you can see that already something like fairly non-semantic, just by playing some sort of probabilistic game. Like I have very often seen that when I'm working with the groups, sometimes they need to be finite, sometimes they don't need to be finite. So why wouldn't I ask the question whether I can generalize this theorem to the non-finite case? So just sort of playing this game is good enough, like GPT is good enough to produce like syntactically correct, like well-typed pieces of mathematics, which are occasionally actually provable and interesting. So that's sort of the positive side of this. And I actually think that this is quite good, right? Like it's like we didn't have things like this like 10 years ago. So that's it. I'm probably out of time. Yeah, we have used RNNs also for other stuff. So I'll just switch to my propaganda. So if you sort of interested in this sort of intersection of AI and theorem proving, we have a friendly conference which is happening every year. So that's it. Thanks for your attention.
Thank you so much, Joseph. Any questions from within the room? And I know we have at least one question from online. So you want to step in here and face the camera and say your name?
Sure. My name is Linus Vepstus, and in Lockhart's Lament, I know that he makes a good cause, a good argument that doing mathematics is kind of like a musician choosing what notes to play while making music. That what a mathematician does, he works on the things that he's interested in. And so what this system seems to be doing is they're helping mathematicians to be even more artistic in what they do. But it also seems to say sort of like, well, look at this pretty picture that I found, or look at this pretty song that I wrote. That somehow to me seems to cheapen mathematics. Is that right or not? And that's part one. Part two is all of us have opened math books and wondered, what the heck is this thing about? It's so complicated, it's without reading the book, you have no idea. What do we do with these when these systems start proving theorems that are so complicated that we don't even understand what that theorem is about? And where do we go from there?
Very computer interface.
Yeah, so I would say like the second question is definitely very interesting for everybody in the field, right? Like we chose some level of abstraction, like we chose to we have basically decided, like if we manage to do math by some hack, right? But just by running some sort of AlphaZero thing, right? And like the AlphaZero also, like what does it know about the game of Go, right? Like it's a universe, right? So in some sense, we are playing the game of Go or the game of chess with a much more infinite game, but it's still a very it's funny, right? Because it's a very closed, narrow AI in some sense. It's just a linguistic game with its rules and grammars, etc. But then we have this strong belief, at least many scientists and mathematicians have that belief, is that this closed, narrow universe has huge applications outside of itself. And you are totally right that when we are doing, for example, just running the sort of AlphaZero loop on it, we are not teaching it anything about the relation to the outside universe. We are inside that mathematical virtual universe, and we are telling it, like, this is your universe, like deal with it, right? And is it good or bad? Like
it's like 3 moves in Go. That
yeah.
the Go master doesn't quite see why that was a.
Yeah, I think just to butt in and obnoxiously and comment on that, there would be a research avenue where you try to do theorem proving in a grounded context, right? Like you could imagine, say, a physics simulator that grounded things move, or a quantum chemistry simulator for that matter, like simulators that ground the movement of objects and unfolding of dynamical systems. And then you have theorems, say existence and uniqueness theorem about a differential equation that's then grounded in what's happening in a simulator with a dynamic evolving by that differential equation, right? So in that, and you could imagine even co-training neural models over what happens in the simulator and over like proofs about what happens in that simulator, right? And then the AI would be not only proving the theorems, it would be by connecting theorems with what happens in the simulation, it would learn how to connect theorems with what happens in the simulation we live in and are in right now, right? So that might
creating universes.
Well, whether that. So there's one question whether that would help guide theorem proving by providing some grounding that could help cut through combinatorial explosions. but that could also, you often slip between mathematics and science when talking, right? But doing this sort of multimodal training, right, would let the theorem proving then really become science and not just math. So I don't know if you know of any work in that vague direction, or have any thoughts on that sort of work.
Well, I can imagine that you go self-reflected inside the math universe. So already in the Mizar library, you have formalizations of set theoretical models. So you have formalizations of like Turing machines that compute. You are proving programs. So the formalizations done by the formal proof community have gone really crazily self-reflected in some cases. So you could say that it's good enough for doing the self-reflection part. It's not what you want, right? Like you want to interact with the quote unquote real world, even if it's a simulation, right?
Looking at theorems that say something about like a video game world would then perhaps train the AI to understand something about simulations, about cross between theorems and our physical world, which would involve some transfer learning to go from a simulator to the actual world. But you know, whether that would help with the actual theorem proving is not obvious, right? I mean, because our intuitions are often guided by the physical world, but our intuitions for theorem proving are often not that good either, right? Yeah. So, but it would probably help. Let's say you want a theorem prover to help design new engineering machines in the world, or something, right? And then that sort of co-training between theorems and simulators of machines could be interesting, which seems like if you're trying to design like nano machines or something, would maybe be the best approach, right? Because our intuitions are horrible for doing that, right?
CPU designers have been doing this for decades, in a certain sense.
Yeah, because it's a very limited sort of theorem proving, right? But yeah, true.
They use set solvers to design and verify anything. They don't actually hook wires together manually. They haven't done that for 30 years.
Right. So if you want to really design nano machines, right, then having a theorem prover that can crunch theorems about the differential equations from quantum mechanics, grounded in a quantum level simulator, will be quite interesting.
There are weird parts of mathematics where the mathematicians lose intuition if they ever had it very quickly, and in those parts, even like first order ultimate theorem proving, even those sort of explosive systems that we have today is sometimes super. Like Michael Pinion and Bober just proved that a big thing in like fuzzy group theory, and Michael Pinion is one of the top experts there, but he has like quite often like no intuition.
Yeah, because I mean, basically that goes back to Linus's point about incomprehensible mathematics, right? Like the teeny tiny region of math space that humans have bothered to explore is heavily biased toward those parts that our brains happen to have some intuition for, which only represents a tiny segment of the possibilities in the physical universe, let alone broader math space, right? And it's biased for the macroscopic world we grew up in. So if you're trying to design nano machines or prove things about these abstract algebra structures, our brains are going to be very bad at it, right? So,
Well, if you get them
yeah. Well, we can let someone else.
Yeah.
Okay, sure. Excellent discourse. Here, step in so the camera can see you and say your name.
Hi, Sam Alexander. I'll try to make this quick. There's two types of proofs. There's constructive proofs and non-constructive proofs. A constructive proof, the proof actually yields something concrete. One of my favorite examples is a classic theorem proved using Kleini's recursion theorem, and it says that there exists a computer program which prints itself. Now, if you prove that theorem constructively, then the proof gives you such a program. And what I wonder is, have you looked at the objects created by your automated theorem proving when it's constructive proofs? And have you thought about using those objects as a handhold for reinforcement learning? For example, reward the agent more if the object constructed is more elegant.
Oh, you are far ahead of us. Like we are like that was my general comment. Like you people are flying too high for us. Like we are just down there in the trenches implementing, like ask Zaire, like how long it takes. But yeah, so the formal math is full of constructive math. Like Calc, for example, is one of the biggest systems, and it's by default constructive. And like definitely people think that the sort of correspondence between algorithms and proofs can be exploited in all sorts of ways. I would say maybe one. It's I don't know the answer to what you are saying. Like some systems are automatically finding constructive proofs, and quite often it's not such a difference to the systems which search for the proofs classically. But a general comment on this, like whenever the proof starts to be quite close to synthesizing something, to synthesizing a relatively complicated object, then it gets much harder. So you can sort of be in the mode where you are not synthesizing too many objects or too complicated objects when you are doing the proof, and you can, for example, need to, like in some geometric constructions, you need to synthesize a sequence of objects like points and lines and circles, etc. And the longer is this sort of synthesis process, the more it seems to me that some reasonable guidance, like in the case of geometry grounded in some human intuition, is helpful. Like we have actually recently done like convolutional neural networks for the particular case of geometric constructions. So I would say that definitely like the case of synthesis, the case of constructing stuff in mathematical proofs is the very hard case. It's the case that is quite close to conjecturing, like when you also like need to say like, hey, here's my intermediate lemma that I will synthesize, like it will fall down from the sky. And we know that we sort of don't have to do that. Like the calculi that we are using are complete in the sense that we can get to the proof just by composing the axioms. And we don't need things like these cuts to fall down from the sky. But it seems that the humans somehow do that sort of thing. It's probably not falling from the sky. Like we are using all sorts of complicated procedures for that. So that's a very open topic, I would say.
Great, thanks. We have one question from online, and then we'll jump into a break, I think, unless there's any other questions online. So the question is from Robert. Is there a problem with generalizing to new areas of mathematics when the learning algorithms were trained on a set of proofs outside that area? If yes, can that be compensated for by generating proofs inside that area with traditional systems and then use that as new training data?
Oh, it's an excellent question. So yeah, so we like the sort of reinforcement learning loop that I was showing was basically started by doing by using the untrained automated theorem prover. It can, just by the human cleverness put into it or combined with brute force and reasonable search mechanisms, it can prove quite a lot today. So like on the slides, I have some numbers. We are about 60% better today than the unguided system, like with the best machine learning technology, which I was explaining. And that means like that 60% in terms of the proved theorems. So that translates to having like what the unguided system can prove has, for example, maximum length 10, like in terms of these natural deduction texts, and we can prove on average maximum length 20. So that's how much the machine learning helps us. What So it's true, like running just the unguided system helps. B, what I did very recently, like we have this old version of the library with the 60,000 theorems, and I just ran the trained system, which is totally symbol agnostic, on a library which is like 5 years newer, and is like 13,000 more theorems in it. So quite a bit. And like more than half of those theorems contain new symbols, like newly defined terminology. So again, like technology like transformer would totally fail. Like it would say, we are out of distribution. We haven't even trained on these tokens, go away. But because we are using machine learning, which is totally symbol agnostic, we are basically learning only on the graphs of these structures, only on the patterns. Then it really generalizes very nicely. So basically, on the set of new problems, we get the same ratio of the unguided system versus the guided system. So the unguided system can prove X, and the guided system can prove 1.6 times X. So in this case, it's sort of works quite nicely because of the way the machine learning is set up.
Great, thanks. It's coming through that we have one more question. Rob from Zoom. Rob, if you want to switch on your mic, and you're welcome to switch on your video if you'd like to speak up.
Okay, I think my video is on. Is my mic connecting?
Yes.
Yes.
Yeah. Okay. No. Cool. I think my question was actually quite similar to Linus's and Ben's comments at this sort of inside the universe aspect, and how you connect the what you're proving in a math proof to some kind of external reality. I mean, specifically, it was. I mean, did I understand correctly that when you said you're talking about a QED singularity, were you advocating a movement in AI back towards more logic in AI? And if that's the case, what's your opinion of things like the reasonably large Twitter debate last year about 2 + 2 = 5?
That sounds like Orwell. Oh, sorry. I'm not on Twitter, so I only know 2 + 2 = 5 from reading 1984 when it was forbidden in Czechoslovakia.
Just in terms of different axiomatization, giving you certainly different. I mean, so this fact that this idea that of being inside a different universe, which is actually kind of arbitrary, and you can make your own axioms.
So there has been discussions, for example, on the foundations of mathematics mailing lists about what people call the alien math. So what would the alien mathematicians accept, and what they wouldn't accept? Like, would they come up with the same math? Would they come up with the same sort of inference rule? Like is something like Turing computability like a universal thing in the universe with all sorts of other aliens? And yeah, I don't have a good opinion about that. Like I know that many mathematicians like to believe so, right? Like there's this question whether math is invented or discovered. I would hope that what the mathematicians are doing is fairly crazy already. But yeah, it's sort of hard. Like I don't know. Like we never know, right? Until we learn something new, right? So I'd say 2 + 2 = 5 sounds sort of weird to me in the sense that you probably assume that I already know what is 2 and what is plus and what is equality and what is 5. And then if you say a thing like that, then I need to think hard. Like, can I find some structure Yeah.
What I immediately thought of there, you mentioned 1984, Dostoevsky in Notes from the Underground, I think it was. Dostoevsky said, what makes humanity so beautiful is that a person can believe 2 + 2 = 5 if they want to, right? So then we have the question if being a correct theorem prover means the system cannot have fundamental humanity. Right? Well, I'll let you solve that.
It would be Orwell resistant, right? So I would actually think like maybe with respect to this QED singularity which you mentioned. So first of all, I think it was a bit of a joke from Mike Beeson when he said it, but on the other hand, like I think he's also a pretty serious guy, and the other comment on that, like I think like having what we are saying like in math, but I will do the slip to science, and maybe I will do the next slip to like society and to Twitter and all these things. Like having at least a bit of the discourse grounded in logic seems today to me, like especially in the last couple of years, like it would be quite beneficial to the humankind.
Okay, so that's all the time we have for questions. Round of applause for Josef Urban. So we normally had a 15-minute break, but we are very behind and they will boot us out of this hotel. So we'll ask everyone to do the break in 5 minutes and come back for the online Q&A for the papers. So right now it is 4:47. So if you can come back at 5:52, go.
I don't think we actually met. Like, I'm John. So,
Gabe, nice to meet you.
Cool.
We'll catch up. I'm gonna MC this thing right now, so we'll catch up. Are you heading out?
Yeah, but I'll see it maybe sooner or later or on the interweb.
Yeah, or we can connect online for sure.
Yeah, did you LinkedIn or what's
Yeah, just Gabriel Axel Montes. And my email is Gabriel Axel. Or just email it. Gabriel Axel Montes, Montes. Okay, everybody. Let's resume. So we have someone in Moscow. It's like 3 a.m, and he's been patiently staying up for this part of the talk. So he'll be going first. So we're gonna ask everyone to basically do a 5-minute hard cap talk about their paper, and Ibby has posted a nice sexy timer on the screen that we're all going to just keep an eye on. If you can even do less than 5 minutes, that's awesome. But no pressure, you have 5 minutes. So the first speaker is Vladimir Smolin from the KIAM, Russian Academy of Sciences in Moscow, Russia. And Vladimir's paper is called AI Future, from Internal Vectors to Simple Objects, States, Subspaces, and Maps. Okay, Vlad, if you're online, go for it.
Do you hear me?
Yes, we can hear you loud and clear.
So it's fine. So can I open my presentation? Unfortunately, I can't. Can you allow me to open my presentation?
Okay, try again.
Oh, yes, now I can.
Ibby's gonna definitely take care.
Okay, thank you.
Thanks. So.
Do you see both of them now?
So
Actually,
my...
I don't think so.
No. Do you see my presentation?
Yes, we see the slides.
Okay, fine. So here is my presentation. My name is Vladimir Smolin. I'm from Keldysh Institute of Applied Mathematics. And I just want to tell you a little of my ideas. Just thinking, if you would like to discuss some of them, you can contact me. It is easy now. I am in Moscow and it costs nothing to speak with me anyway. Okay, I will the most close my ideas to Yosha Benjo, that we are not stop only naming the objects. It should follow by vectors and then by set of vectors which describe these objects. So if we can describe some object with some vectors, not by one vector, it should be made hierarchically. And these vectors form some subspace, and this subspace can characterize such objects. But I would like to go some further on. So we should improve deep neural networks we have to AGI level. What should we do? We should improve approximation, improve decomposition, and hierarchical structure of these models. So the main next idea is that we should not think about the neural nets as making transformations of input signal into output signal. We should think of them as some sophisticated means for record and playback of information about the world. So the neurons are very simple objects, especially formal neurals, and we won't find some conscience in these elements. So the conscience is in information we wrote on neurons, and then we are able to read this information from neurons, and some sophisticated process is how organize this record and playback process. Just a skip, so the idea of making neural maps of simple objects is that the world is very complex, but there are some simple objects where you can make models. So, for example, if there are a ball on surface, there are only 2 coordinates to describe it, and map is also will be rather simple. Also, it should be hierarchical, And what I say later, that the main object of making AGI is not to describe all the world. It's impossible, but to describe, make it possible to describe simple objects in your surrounding. And if you can describe your surrounding with the models of simple objects, then you can live in this world and operate here. Okay, and this decomposition should be hierarchical because the world is complex and we divide it in simple models. We should coordinate between them. And so these simple parts should be organized in some hierarchy. It may be one or more steps, but if we make decomposition, we also should think about hierarchy. Okay, so also I make some tips here. And what we should do for understanding, how do you think if I understand something? You will tell me that we should make some model and to show that it works. So we can make models of different processes, but these models do not understand anything. How can we solve this problem? We should make such a model that can make another model that show that this model is understanding what it's doing, and that is so what I'm telling about the object states subspaces here. I won't stop this on this question because little time, but it is the way of making some models of simple objects and some ideas how to make the composition. Okay, so I also skipping some slides. And here is some simple formulas. Of course, it's not all the mathematics proof. No mathematics proof is just some ideas, but still it's not only words, but there is some mathematics under these ideas. Okay. And here is another idea I would like to tell you, that we are thinking that it's very difficult to make some goals for our artificial intelligence. So it can solve some tasks, but the goals should be set from outside for these agents. It's not true because when we choose our behavior, we are thinking how to do it better. So if we know that we need to live, need some energy, need to find some new information, it's quite enough to make some behavior. And it's quite enough to find good goals that will make our behavior come into this, to solve these tasks. It's also have some cultural components, of course, but our culture and civilization also aim to these tasks. Okay, and knowledge just the base of understanding. So if we, okay, how much time it's left? Okay.
Vladimir, actually, you're out of time. I'm so sorry.
Okay, so just two words.
Thank you.
We have possibilities that are like animals, and a lot of things we are talking about on this conference is not our properties, but the civilization knowledge. And the last slide I'm showing you that here is my coordinates. So if you find something interesting in my ideas, I would like to discuss them. It's easy, just write a letter and we can contact. Thank you.
All right. Thank you so much, Vladimir. And thank you for working within our time constraints. If anyone has any questions for Vladimir, please feel free to email him. I'm sure it's pretty late in Moscow now, so we'll let you rest. So okay, next up, you're welcome. Very welcome. The next speaker is Mohammadreza Ali Dost, who's an independent researcher. And Mohammadreza's paper is titled AGI Brain 2, the upgraded version with increased versatility. Mohammadreza, you have 5 minutes. Thank you so much for being on.
Thank you. Can you hear me?
Yes, we can hear you.
Can I share my screen?
You may if you like, yes.
Okay. Okay. Thank you for having me. I'm Ahmed Rezalidous, an independent researcher at AGI Brain, AGI in the AGI science, and I want to present my paper, which is entitled AGI Brain 2, the upgraded version with increased versatility index. In my paper, I propose a versatility index for AGI systems that can be used to measure the versatility of artificial general intelligence systems or for comparison purposes between different AGI systems. And then I described my previously proposed model called AGI Brain, and then the upgraded version, AGI Brain 2, which benefits from a new explicit memory, which is a modified Mamdani fuzzy inference associative memory called PROMEM. And then the two models were tested in 4 different environments, and based on their versatility index, they were compared, and we can see that AGI Brain 2 is more versatile than the previous version. And I start with the artificial general intelligence. I call it the art of building thinking machines, which are able to understand, learn, and perform an intellectual task that human can. And in contrast to AI, AGI treats intelligence as a whole, resulting in the construction of versatile and general-purpose intelligence systems that can learn, reason, plan, communicate, as well as any other task at the human-level intelligence, or perhaps ultimately well beyond it. Based on a statement based on a paper from Legg and Hutter, I proposed the versatility index. They said that AGI systems have to perform well in a very large range of environments. And I turned this statement into a formula in here. Versatility index is defined as a summation of the performances of an AGI system in each environment, which N denotes the number of the environments, and alpha I denotes the performance of each system. VI is a dimensionless positive real number, and the higher the VI, the more versatile an intelligent system is. And an example for, suppose that the AGI system A is able to perform in 3 different environments with performances 85, 62, and 93 respectively. And the VI for AGI system A is as follows, is a summation of them, and it's 240. Definition of VI has features. First one is the distinction between AI and AGI systems, and second one, it provides a quantitative ground for comparison between different AGI systems. Since AI systems are problem specific, their VI value will obviously be low, and we can, with the benefit from VI, we can compare different AGI systems with each other. And then I proposed my previously proposed model, AGI Brain, which has roots in modern control theory. And because of time, I have to pass these slides. And it has 3 learning stages. One I called infancy stage, and then the decision-making stage, which the model has to solve this optimization problem using its memory, explicit memory. And then it has an expert stage, which it uses an implicit memory. And then we have the structure. We have the structure of AGI Brain. We have the structure of AGI Brain and AGI Brain 2. The difference between these 2 models are there only in their explicit memory, which in AGI Brain it is made up of artificial neural networks, and in AGI Brain 2 it's made up of modified fuzzy Mamdani system. And the model, and I call it PROMEM. It is a modified Mamdani fuzzy inference system, and it turns AGI Brain to an upgraded version that is more versatile. The model, the 2 models were tested in 4 different environments, in 4 different scenarios, which are completely described in my 2 articles, my 2 contributions in AGI conferences, and they were they were compared based on their performances. And AGI Brain 2 performed, these are the performances of AGI Brain and AGI Brain 2, and their VI is computed based on their values. And AGI Brain has VI about 365, and the AGI Brain 2 about 370. And this is the conclusion and future works of my works. AGI Brain 2 is still far from being a real AGI, and it has to undergo some other developmental stages, and like delayed environments and the environments with intelligent opponents like games. Thank you if you have any questions.
Thank you so much, Mohammad Reza, for the excellent presentation. Yes, anyone feel free to reach out to Mohammad Reza, and we will have some time for questions at the end for all the speakers. If you wish to stick around, you're welcome to. So next up, we have one author with 3 papers submitted. So Michael Timothy Bennett from the Australian National University, ANU. First paper is titled Compression, the Fermi Paradox and Artificial Superintelligence. The second paper is called Symbol Emergence and the Solutions to Any Task. The third paper is called The Artificial Scientists, Logicists, Emergentists, and Universalist Approaches to Artificial General Intelligence. Michael, welcome. Since you have 3 papers, you can go a little longer, just being mindful of the time as well. So welcome, Michael.
Thanks very much. I'm just trying to get my, there we go. Finally got the camera working. Hi, everyone. Yes, thanks, Matt. I do have 3 papers. Unfortunately, I only managed to get videos done for 2 of them. They pretty much all stem from this one paper, Symbol Emergence and the Solutions to Any Task, which formalizes an arbitrary task and then examines its solutions, specifically by looking at them as a statement from which you can adopt goal-satisfying responses. So you'd learn an arbitrary goal from an extensive set of example goal-satisfying states. And as a result of this, you have, sorry, I wasn't prepared for a presentation in this. I thought it was just going to be Q&A, so it's a little rusty. But yeah, that first one formalizes Occam's razor in terms of a statement rather than a program. And so then you have this sort of spectrum of weaker statements, some of which are more generalized better than others. So this would be related to the way Shalette was talking about abstraction earlier. And then it talks about symbol emergence as instead of simply being the meaning of a symbol described dyadically, as you would have with a programming language or something like that, meaning in natural language would then be the significance of stimuli in terms of a goal. And as you learn a goal by learning this arbitrary task, it means that the stimuli has a particular significance for your future decisions as an agent. Yeah, how that relates to the compression and Fermi paradox one, which I didn't manage to get a video done for. Essentially, the Fermi paradox one just looks at the idea of how you'd communicate with an agent who was engaged in a different task overall. So say you could describe the task of being human as sort of an arbitrary task we're faced with, which is sort of stipulated by the compulsions we have to live under, pleasure, pain, the desire for, continued existence, status, all of those things. Yeah, that was a short paper that I think it is going in the proceedings, even though I didn't manage to get a video presentation done for it. And the final paper was called The Artificial Scientist, which was just a bit of a survey of different methods or different approaches for AGI and how they would apply in the context of trying to create an artificial scientist. So divided that into sort of what I called logicist methods, which are, your standard things like symbolic representation, inductive logic programming. Then emergentist methods, things like neural networks, subsymbolic processes hoping to give rise to, say, an abstract symbol system through, and then finally, universalist methods. So this was obviously a sort of an extension of Goetzel's 2014 survey of AGI. And then I related that to the theory of tasks, and also another similar theory, which I stumbled upon, which was Richard Evans of DeepMind's work into what he called them. Sorry, I think someone's got their microphone on.
Well,
But
I muted that person.
okay, cheers. Yeah, so that again was just looking into Richard Evans's work and its significance in terms of making an artificial scientist. In particular, his work was focused more on predicting a sensory sequence as opposed to looking at sensory motor states, where you're looking at the sort of motor side of things as well as the sensory side of things. And so from the perspective of creating an artificial scientist, we'd need something more focused on interaction and intervention, sort of in the style of Judea Pearl's work into causality, for example. Yeah, all right, I will leave the rest to any questions. If anyone wants my opinion on which paper to read, it's the symbol emergence and the solutions to any task one. Not the other two, kind of, they're sort of stem out from that. So yeah, I'll hand it back to Matt or Evie. Thanks very much.
Great. Thanks so much, Michael. That was brilliant. Thank you for sharing a bit about all your 3 papers on such short notice or no notice. So did we have a video for Michael, or is that not happening anymore? I'm just asking our online moderators.
I think we can go on to the next one because I don't have it at hand right now.
Okay, sure, no problem. So, all right, thank you, Michael. And there'll be questions at the end, or feel free to contact Michael by whatever way is most convenient. Michael, thank you so much. So next speaker is Robert Freeman, independent researcher of chaoticlanguage.com. Robert's paper title is Parsing Using a Grammar of Word Association Vectors. So Robert, welcome aboard. And yes, you have 5 minutes to share your brilliance with us.
My brilliance. Okay. One minute should suffice for that. Okay. So I won't share my slides. There's actually two presentations of that. One was at Anton Kolinen's interpretable NLP workshop. And the other one I contributed talk. I was presented on for about 50 minutes, I think, actually, with both of them. But to summarize in a word, I think it's actually the whole theme of what I was trying to present there is very much centered around what I was my comment question to Joseph Urban's talk just previously, and actually centered on this issue of mathematical decidability or decidability in general. And it came from work I was doing actually 20 years ago, trying to learn grammar from corpora, from data, from raw language. And what I found was I got contradictions. And I think this relates to issues of decidability, contradictions, paradox, actually kind of similar to this whole 2 + 2 = 5 issue, where you get these different, these contradictions which are possible depending on how you define your formal system. Just a little note, I believe 2 + 2 = 5, I believe it actually stemmed back to a Soviet era poster where there was a 5-year plan which had been achieved in 4 years, and they had a big poster saying 2 + 2 = 5 because the 5-year plan had been achieved earlier according to their claims. So there was, you can find sense for almost anything. And certainly in grammar you find contradictions. And that's what I found, and it got me thinking about what we were trying to do with grammar. If we're trying to abstract it, but you get contradictions, I felt that actually we perhaps should start looking at grammar as an expansion of language and data. Expansion which embraced contradictions, but the contradictions are resolved in the context that generates them. So that's the central theme of what I was trying to present with the vector parser 20 years ago. This idea that you get contradictions. I believe it's related to issues of decidability, and I'm very happy to see now that decidability does seem to be coming to the fore in some areas of AI research. I'm seeing it, I saw it also for the first time actually during the conference in Yoshin Bak's presentation, where he was talking about a kind of a quantum collapse which is necessary. He was saying the quantum collapse would take place via an attention agent. But I think this is the same issue. I think that we have to start thinking about some kind of collapse into different possibilities. That actually a single logically consistent representation may not be possible, but that it is actually very easy. It is actually a very easy solution if we look at it from the point of view of generating representation from data. You generate these contradictions automatically. And I think these new, so I'm seeing it with Bob Koch's work on some sort of quantum formalism for natural language structure. I see it in some things recently that Linus Webster has written on the decidability, that representation is not decidable. And I saw it for the first time at this conference with Yoshin Bak's quantum formalization of representation, that it needs to be collapsed. So I'm seeing now for the first time 20 years later, some kind of wider embrace for this idea of decidability means that perhaps we should look at representation as an expansion. But I think still these modern embraces of it are perhaps still too trapped in formalism. Actually, we can get a much easier solution simply by different abstractions of data. Machine learning actually drives us to embrace this kind of contradiction. And there is a very easy solution if we simply embrace contradiction. That's what I tried to do with vector parser. I encourage you to have a look at the very long presentations that I made, and please contact me if you're interested. I think I've got 25 seconds left. I'll give them to you. That's all.
Thank you. We're waiting for the other room.
All right. Thank you so much.
Go for another 20 seconds.
Fantastic. Is the video on for us, Ibby?
Yes.
Not sure how that happened. Okay, so thank you so much, Robert. Just a quick announcement. Many of the contributed papers have recorded presentations on the SingularityNET channel in a playlist for this conference. You're more than welcome to jump on that if you'd like. So our next paper is by Roman Janbolsky, who is at the Speed School of Engineering and the Cybersecurity Laboratory at the University of Louisville, Kentucky in the United States. The title of his paper, and I am just scrolling up here for, I think it's the AGI control problem. So let's go with Roman, please welcome. You have 5 minutes to share with us a bit about your paper.
Thanks. So you already covered who I am and what my paper is. I have a video recorded, and I strongly encourage you to actually read the paper. What I did is to survey literature on the subject of AI control problems, specifically as it relates to AGI and superintelligence. The question, the AI control problem, is basically whatever or not it's possible to control indefinitely behavior of a much smarter agent for humanity. So we would like to get the benefits from those systems, but while remaining safely in control. If we don't like something, it should be possible to undo what the system is doing. There is not much published on that subject. There is some blog posts, a little bit of forum comments. So I surveyed everything I could find. And basically the conclusion is it's unlikely that we as humans can indefinitely control much more intelligent systems. I have a number of complementary papers which show why it's the case. There are a number of capabilities we need to have this control ability. We need to understand the system. We need to be able to predict its behavior. We need to be able to communicate with it in a non-ambiguous language. And for all those, I show some impossibility results. You cannot get an explainability out of a much more complex system, which is both true and comprehensible to a human mind. So you have to sacrifice either how reliable is the explanation or whatever or not we can actually understand what the explanation says. In terms of prediction, you can probably predict general direction in which the system is working, but you cannot predict specific decisions it makes, side effects of its process of getting to that goal. Likewise, there are impossibility results related to mathematics, physics, economics, public choice policy. So there are famous results about voting systems. It's impossible to design a voting system which satisfies everyone's preferences. In fact, the paper I submitted is a small subset of a much larger paper which covers all those results. It's about a 70-page survey, and I'm really hope that we can get some feedback and people will either say, okay, this is why there is a mistake and we can bypass this issue, or there is some verification of those results. And then of course the question becomes, what should we do if we now agree that we cannot control those systems? I don't have any slides prepared for this short 2-minute intro. So if you have any questions, I'm happy to answer them now, or maybe I'll stick around. We'll see. Definitely email me if you have questions, if you're interested in collaborating. I have a number of upcoming papers with our impossibility results, which I think a lot of people will find interesting to both read or collaborate on. Thank you.
Thank you so much, Roman. As always, pleasure to have you. Yes, and if anybody does not have a formal presentation prepared, that's perfectly fine. We don't expect slides. If you just want to make a few comments about your paper and defer to the paper itself or a video, you're more than welcome to, whatever works best for you. So the next person is Yoshihiro Maruyama from the Australian National University and Moonshot Research and Development Program. And the title of the talk is Categorical Artificial Intelligence, the Integration of Symbolic and Statistical AI for Verifiable, Ethical, and Trustworthy AI. Take it away. Thanks so much.
I think Yoshi's not here yet. He's just teaching a class. But myself and another of his students are here. Can we reschedule this one for a bit later when he arrives?
That should be okay. I'm just waiting for the next person to come through from our online awesome moderators who have been awesome the past all the days of the conference across many time zones. So yes, no problem. We can delay that one. Just be in touch with the folks on with the moderators. So the next talk is by Alexei Samsonovich. If Alexei, you're around, Alexei is from the Krasno Institute for Advanced Study at George Mason University.
Not anymore. Sorry, I am currently in Moscow in the National Nuclear Research University. So let me briefly present you.
Sure, thank you.
My slides. You have the paper, you have my video, which is actually on a different topic. So to be very brief, we are currently studying a number of paradigms, including those shown here, like virtual partner, virtual dance partner, virtual pet, penguin, virtual clownery, virtual interlocutor, and also thinking about others like virtual classroom, virtual conference presenter, virtual registrator, and so on. So what unifies all these approaches is that we use one and the same cognitive model, biologically inspired cognitive architecture with emotional capabilities that we call e-BICA. And I have no time to tell you what the model is, but the thing is that recently we understood that it would be more beneficial for us to start using deep learning. And so I will try to illustrate this idea using this example of virtual clownery. Like imagine that you have an environment in which there are 15 objects, including like a trash container, a table, a chair, vodka, and so on. And there are two persons who are performing here. And basically each of them has like 72 actions to do. They can choose any action at their own please, and they can be in different moods, in different relationships with each other. The actions have appraisals. So basically, this is how the model decides which action to perform. So after we train, let's say we have the model implemented in some kind of code that generates the scenario of action in this room. Then we use neural network, or let's say LSTM, that learns to generate similar scenario based on model generated data, because we cannot have so many human written scenarios. We have to generate them using cognitive model. So here is an example of a scenario generated by the model, trained on the scenarios. Sorry, this is the scenario generated by LSTM, trained on scenarios generated by the cognitive model. And what you can see that the logic usually holds, and behavior makes sense, but there is no very good artistic quality in it. So what we do after that, we incrementally train this network on human generated data, which is very few, but it turns out that after training this model on human generated data, we can achieve something new, like some nice idea, or maybe an unexpected twist in this scenario. Like in this case, the clown, when he got really upset, he started doing something crazy. So he stumbled on the hammer. He stumbled on the bottle of vodka. And then what would happen next, like according to the original ideas, he would step on the rake and the rake would hit his head. Instead of that, he takes the hammer and starts beating teeth out of the rake with the hammer, so that it would never happen. And this is something that I did not expect. Like the model, it seems like it anticipated, the clone anticipated this possibility and started doing something funny that was not really expected. So, okay, I admit this could happen by chance, but actually this happened in the very second run of this implementation. And so it indicates to me that there is some kind of potential here to explore. Maybe this is how we should proceed. This is one of the possibilities to combine deep neural networks and symbolic cognitive modeling. Okay, then what about applications? As I mentioned in my brief video presentation posted on your site, one possibility is to have similar to an instant remote thermometer, some kind of instant remote psychometer, an artificial person that would briefly interact with you when you enter a building or register for something. And during this time, it would determine who you are, in what mood you are, what you are capable of. And this might many possible uses in our society, I think. So this is actually a problem, how to find those applications that will help us to get this approach started. Okay, thank you. I guess I'm done on this slide.
Thank you so much, Alexei. Everyone can find Alexei's paper online along with all the other papers. So the next speaker is Vignav Ramesh and also Anton Kolonin. The title of the paper is Unsupervised Context-Driven Question. And this is coming out of SingularityNET Foundation and AIGents.com, AIGENTS.com. Take it away, gentlemen.
Thank you. Yeah, so Anton Kolonin couldn't be here right now. I think he's asleep, but I'm Vignav and I'll be presenting our work. Let me go ahead and share my screen. Okay, can you see this?
Yes, we can.
Okay, awesome, thank you. So for a bit of background, NLG is the task of producing linguistic content from semantic and/or non-linguistic data. And we focus on surface realization, which is concerned with the construction of sentences from the underlying content of a text, usually structured as a list of tokens. And essentially, our QA architecture relies on a component for NLG, and we only use grammatical knowledge. So we don't use morphological, phonological knowledge, etc. So this is a diagram of an explainable QA pipeline. And we see here that there are two components, natural language comprehension, or NLC, and natural language generation, or NLG. And our current work is concerned with the more basic version of QA, in which the query is proposed as a list of seed words in natural language, and the answer is a grammatically valid sentence that correctly captures the relationships between the seed words. In this sense, our work replaces the semantic interpretation and query execution components of this QA pipeline with an extended version of sentence generation based on the context of the question and the scope of textual data to search for an answer. So essentially, our work is mimicking the kind of queries you see on online search engine platforms like Google, Bing, Yahoo, things like that. So this is a background of linked grammar, which is the formal grammar behind our QA architecture. And for sake of time, I won't go too much into this, but just know that linked grammar, or LG, is founded upon the idea that each word is defined by a set of connectors and disjuncts associating those connectors. And disjuncts constitute the legal use of a given word. And really, the more important takeaway from this slide is that the human readable and editable nature of LG allows our grammar induction algorithm to comprehend and process text under the premise of unsupervised language learning, and thereby better serve as an INLP method, which means interpretable natural language processing method, for the purposes of the QA task. And actually, if you're interested in INLP as a whole, Anton and I ran a workshop on INLP that I think Rob mentioned earlier, and the recording of that is available on the SingularityNET channel, so you can check it out if you're interested. Okay, so to perform QA in an unsupervised and interpretable manner, we adopt and extend the generator architecture that we proposed in one of our previous papers. So essentially how that works is, after calling this thing called the loader, which is utility infrastructure to store the LG dictionary in memory, the generator performs surface realization with 3 steps. So first, given a list of words, the generator computes a subset of all orderings of those words that satisfies initial checks of the planarity and connectivity meta rules, which are 2 rules imposed by linked grammar. Then the generator checks if each ordering is grammatically valid by ensuring that every pair of consecutive tokens can be linked via a pair of connectable disjuncts. And there are exceptions to that, but I won't get into that since I only have 5 minutes. And finally, the generator formats those orderings that are valid into sentences. So our work for QA is to propose a contextual generator, or CG architecture, that extends our prior generator model. So the CG performs closed domain question answering on queries structured as lists of seed words, and it operates in these three steps. So first, the CG calls the loader to store the LG dictionary and corpus lexicon, as well as extract a context lexicon from a given document. And then step 2, the CG recursively calls the generator to determine valid sentence constructions from a list containing all seed words and n additional words from a subset of words in the context lexicon that satisfy initial checks of the planarity and connectivity meta rules. And the n addition permutations are tested in order of decreasing Zipf-ian frequency, and I'll get to what that means in a second, corresponding to the current context. So when step 2 is first executed, n equals 1, imposing the constraint that the answer is of minimum length. And step 3, if no sentences have been generated after testing all valid subsets, the CG increases n by 1 and repeats step 2. So on the previous slide, we saw that the CG checks n addition permutations in order of decreasing Zipf-ian frequency. To motivate this, consider this example query, mom cake, so just 2 seed words, along with the context specifying the food preferences of family members. If the CG were to use context word frequencies without modification rather than Zipf-ian frequencies, it would perceive the sentence cake was a mom as more contextually appropriate than mom likes cake, which of course is the ground truth answer. And this is due to a phenomenon known as Zipf's law, which states that the rank frequency distribution of words in a given lexicon is an inverse relation. So determiners and linking verbs are more common in any corpus, regardless of context, than more semantically appropriate words, such as likes in this example. So we use Zipf's law instead of the context frequencies, which is calculated as shown here. And really quickly, to go over the results, we report these 4 metrics. So blue, word to vec cosine similarity, WER, and TER. Our results do outperform these 4 baselines that we've implemented, which is BERT models, BERT, Electra, Distilbert, and Roberta models that were trained on the Stanford question answering data set and then fine-tuned on the POC English corpus, which is what we ran our tests on. And as you can see, we outperformed all these models in terms of blue, WVCS, and TER, and we got competitive WER scores. Just really quickly for 10 seconds, I'll just explain the one problem that our results face, which is the grammatical ambiguity problem. Basically, this is a problem where the same word can take on different roles in a sentence, and implementing semantic disambiguation to solve this problem will be part of our future work. And yeah, that's all I have. Thank you.
All right. Thank you so much, Vignav. Excellent presentation. And thanks everyone again for operating within the 5-minute constraints. You're doing wonderfully. So the next topic is by Klaas Stranegard, the ecosystem path. Klaas is at the, if I pronounce that correctly, I apologize if I didn't, is at the Chalmers University of Technology in Sweden. Take it away, Klaas.
Thank you so much. Yes, that's the correct pronunciation. Okay, so I'm going to talk about an idea that we call the ecosystem path to AGI. So first of all, why would we be interested in modeling ecosystems? Well, there are several reasons. One is to understand ecology. Here's the classic Lotka-Volterra equations and the fluctuating population dynamics. Here is an example from Google DeepMind, Peter Sunehag, where they are looking into animal behavior simulated with reinforcement learning models. Here is another example about obtaining sustainable fishing policies. And it's based on the ecosystem simulator EcoPath, which is in wide use throughout the world. We'd like to add another possible reason for studying ecosystem simulators, which is to model the emergence of natural intelligence. So natural intelligence, as we all know, emerged as the result of an evolutionary process that took place in a big ecosystem, which is our planet. And there we have an automatic selection pressure on all organisms concerning their ability to survive and reproduce. And part of that selection pressure targets adaptive behavior and in particular intelligent behavior. So the ecosystem path to AGI that we are suggesting is to develop large-scale ecosystem simulators that emphasize animal cognition. And then we must make sure not to forget any of the two big forces of adaptation, which are evolution and learning. And the idea is to let the simulator run without any human interference. And there will be no need to provide tasks or training data because it is all inside the ecosystem. And in that way, we will exploit the built-in selection pressure towards more intelligence. So it's really like an aquarium or something else, a delimited ecosystem where we have a lot of species interacting and collaborating, competing, and arms races between predator and prey, etc., going on. A lot of challenges all the time for all the species. So to do this, to make this, to follow this strategy requires more powerful ecosystem simulators than we have today. So here's a wish list of properties that we want such an ecosystem to have. So it should support evolution and learning, genotypes and phenotypes, sexual and asexual reproduction, broad model of nervous system, individual and lifelong reinforcement learning, reflexes, and so on. So we try to develop such an ecosystem simulator, which we call EcoTwin. And it's an open source simulator, which is based on the game engine Unity. A prototype is available on GitLab. And I'd like to focus a little bit on the nervous system model that we're using. So we are putting together 4 different neural networks with different roles. One is a reflex network. Another is the policy network, which is used for reinforcement learning. And then we have a happiness network, which computes at all points in time the level of happiness of the animal. And we have a prediction network, which enables us to predict the next state. And we use the happiness function or the happiness network to compute the reward signal in a simple way. So here's an example of such a happiness network for a lamb in this case, which takes in glucose levels, water levels, those are internal signals, and then smell of sheep, smell of wolves, for example. And all of those 4 components will be combined into a happiness signal. Okay, so finally, I'd like to show you 3 different ecosystems that illustrate emergent adaptive behavior that we obtain with our simulator. The first one is a 3-species variation of the Lotka-Volterra dynamics with grass, wolves, and deers. Here we have a diel vertical migration pattern, in which plankton migrates to the surface and down to the bottom every 24 hours. And here we have a population of different goats with different genomes, and we see how the goats that have genes encoding reflexes that prevent them from eating deadly objects will take over in the population. So from that, we can conclude actually that the combination of reinforcement learning and evolution is more powerful than reinforcement learning only. Okay, so for contact and more information, we have a project website, and don't hesitate to contact us. Thanks very much.
Thank you, class. Wonderful presentation. So the next speaker is Tom Su and Yoshihiro Maruyama from ANU in Australia and Moonshot Research and Development Program. The title of the paper is Neural String Diagrams, a Universal Modeling Language for Categorical Deep Learning. So Tom and Yoshihiro, if you're there, feel free to jump on in. Welcome. I think you're muted, Tom.
Hi, can you hear me now? I think you can.
Yes, we can. Go for it.
Sorry about that. Yeah, so yeah, my name is Tom, and I developed this work with my supervisor, Yoshihiro Maruyama. The title is Neural String Diagrams, a universal modeling language for categorical deep learning. So essentially, this is a categorical approach to deep learning. And also the neural string diagrams we proposed is kind of used to kind of more formalize the neural network architectures into more mathematically rigorous diagrams. All right, so let me just jump. So this, you can find my presentation online, I suppose. But here's the outline of my presentation. I introduced some background information of category theory. Then I just want to quickly go through the category theory approach to deep learning in this short presentation. So category theory is great. So if you're interested, definitely look into that. But I don't have the time to explain that. So our category theory approach to deep learning is essentially recognizing that category theory is all about compositionality. It's about generalizing things and abstracting ideas and comparing the abstract structures between different systems. It can be applied in different sciences, in physics, in computer science, in obviously mathematics. So with this power, we're thinking, so we can utilize this to turn these informal neural network architecture pictures into formally explainable, mathematically verifiable, and systematically composable entities in their own rights. So essentially, whenever we look at a neural network architecture, we see these informal pictures. They're great to illustrate what is going on, but by themselves, people choose different styles. People use different, different words for different things. So usually these are not mathematically rigorous. So our work is to look at these and turn them into neural string diagrams, which I can show you quickly for CNN. So our version of CNN will look like this. So this is very simple CNN architecture. So we just have one convolutional layer with two filters. So filter one, filter two, and you convolute with the input. Then you go through ReLU and pooling, and here's the concatenation and things like that. And then we would have a transformer neural network architecture in neural string diagrams. Yeah, so you can find all of this in my paper, and I'll quickly stop here and hand it back to the organizers. Thank you very much.
Thank you, Tom, for your speedy presentation. Excellent presentation. So the next presentation is by King-Yin Yan, independent researcher, and the title is AGI via combining logic with deep learning. Take it away, King-Yin.
Hi, can you hear me?
Hello? We can hear you. There may be a little bit of a buzz, unless that's my microphone suddenly.
Or maybe it's my phone, but is it better now if I talk?
Yeah, there is a bit of a buzz in that microphone. Do you have something else, maybe?
You mean change the phone?
Well, we can, if you have an immediate solution, go for it, but we can hear you and you do sound like you're merging with robotic intelligence. So for this conference, I think that's okay.
Okay, maybe I'll make it shorter.
Sure, as you like.
So my talk has two parts, and So in the first part, I'm just trying to combine BERT with classical AI model like this one. It's a logic-based AI, and I try to combine the information inside BERT with this kind of architecture. For example, in the last talk, we can write the neural string diagram of BERT and try to figure out what kind of structure or symmetries it has. So this is, but many people have done similar things in this conference, and I would like to discuss with that, but I'll make it short. So and another part of my presentation is about the brain, and I compare the basal ganglia and the neocortex. This is a theory based on the book on the left mainly. So it explains the basal ganglia as determining some actions for an organism, for an animal to choose. And this mechanism is similar to the one in the neocortex, but they are two evolutionarily kind of, one is earlier and one is later. So, and then I have this idea. I mean, this is not my idea, but there's this theory about neocortical learning, which is based on some associations between actions and their goals, as opposed to traditional reinforcement learning based on dopamine, which is a single reward. And supposedly the neocortical approach is more efficient than traditional reinforcement learning. And this is one point I want to raise. Running out of time, so I'm glad to see other friends and new friends here, and maybe we can discuss more. And I'll hand it back to the organizers. Thank you.
Thank you, Tom. Wonderful. So that is it for all the speakers that are online right now. So there are more papers than were presented, I believe, at least a few more. So those are all, again, found online on the website. There are YouTube videos that were shared with us for presentations that we're organizing. And over the course of the next week, those will probably be all done and organized. So before the conference comes to a close, we'd like to invite questions on any of the papers that were presented from anyone in the room and also anyone online. So feel free to ask away.
Hi, I want to ask the first question to Tom Su. Can you prove the equivariance of the transformer basing on the string diagram? And if the answer is yes, then I guess it shows that the string diagram captures the symmetries of the transformer. And this kind of inductive bias is like if you heard Yoshia Bengio's talk, he talks about this kind of inductive bias, and it's the main point of his theory. So I guess it would be important. Thank you.
Oh, thank you for your question. Unfortunately, I don't think our work currently is looking into proving equilibriums of transformers. But certainly, I believe that's possible through the string diagram approach. So what we're proposing actually is the kind of a method of turning architectures into string diagrams. Then whatever you do with string diagrams, because that's mathematically rigorous already, you can try to utilize the category theory side of things to prove your I guess all kinds of theorems, and certainly you can try to start formulating at least these questions or these theorems via string diagrams. Thank you.
Okay, thank you. I want to add that if you also can do this with the classical logic, a structure, like for all x something, that kind of structure, perhaps also with string diagrams. And then you can compare the symmetries inherent in the logic and also in, for example, transformers, things like that. So this is interesting research, and I hope to learn more from you. And
that's all right here.
Thank you. Yeah, that does sounds very interesting. And indeed, we are looking into bringing the quantifiers into our research as well. Thanks.
Cool. Any more questions? There's nothing coming from online at the moment. Are there any questions between the different presenters, between all of you or anybody else from within the room? Before we go on to Ben, no rush. Okay, but Ben is headed to the airport, so we are going to hand it to Ben.
Yeah. Thanks. Thanks everyone who has stuck it out to the end of AGI-21. This has been a real lot of fun. I was sort of doubting whether it made sense to do a face-to-face event in the pandemic situation, but I'm really glad we did. It's been a lot of fun for those of us here in Palo Alto, and also amazing to have so much participation online. And really the speed of progress in the field, well, not what I think it's going to be in a few years when we start actually creating human level AGIs. I mean, the speed of progress in the field is very exciting to see compared to like 2006, 7, 8, and so on when we started with this. So definitely a really fun time to be doing AGI. So I want to thank, before going, everyone who made this happen. I mean, the sponsors of the event, Springer Verlag publisher, SingularityNET, and then our spinoff, True AGI, that's commercializing Hyperon. All the amazing speakers, the keynotes and contributed speakers, and paper contributors, everyone who came here and showed up online. Of course, the AGI Society is the organization which hosts the conference every year and has been doing this since 2006. The SingularityNET marketing and media team put in a huge amount of work just in pulling all this off. I mean, Ibby, Benali, Max, Haley, and Rainier on the streaming team and making the whole online expert aspect work. Gabriel, Axel running around doing every random thing that needed to be done here in Palo Alto. Matt Eclay and Alexei Potapov organizing the proceedings and the papers, and Matt organizing like 100,000 other things. Sarah Isaacson, my daughter Scheherazade, helping with all sorts of organizational aspects. Lisa Rain for co-hosting the online piece of it and providing the music we heard in the breaks. And finally, the future post-singularity AGIs for coming back in time and causing us to have this conference to facilitate their creation. Right. So thanks to all of you. And yeah, come back next year.